Good morning and welcome back to day 2 of KiCon North America. I am still Seth, and I am happy to welcome you back. I figured on the second day, people are a little, we're a little more comfortable. We're maybe rolling in a little bit later. So, the first talk today, I'm going to talk to you about custom design rules in KiCad. So we'll warm ourselves up before we get into the meat of our presentations today. So my talk is on leveling up your custom design rules. This is an incredibly powerful feature in KiCad that is ever so slightly hard to use. But only because we don't fully immediately understand it as a textual language. And so I'm going to give you some details today on how you can implement custom design rules in your designs to potentially save yourself some respins, make Amit happier because you're not going to be causing him headache, or your fabrication house of choice, and make KiCad do the things that you want it to do. Every now and again, you want KiCad to go beyond what is immediately apparent in the dialogues. And there is always a command that will get you the level of detail that you want in custom design rules. So, first of all, let's define this, because this custom design rules were new in version 8 and expanded in version 9. So, what are custom design rules? They're DRC, but maybe a little bit. Sometimes they will affect your DRC, and sometimes they won't. And which one it is going to depend on the rule. So it's up to us to define where that line is. So here's a rough flow chart on what that could look like, or more or less what that looks like. So if your rule is going to affect a zone fill, well, then it's probably not DRC. Then what is it? Well, it changes how your zones fill, and so changes what the output of your board is going to look like. And if it doesn't affect the zone fill, then you're going to see the result when you check. Now, this is mostly true, not 100% true, because things like clearances will hit both, right? Clearances are going to change how the router behaves, and if you violate them, they will come up in DRC. So they're a DRC rule as well. But zone fills generally, what you're going to see is the refilled zone change. Either you're going to have greater clearance, or you're going to have an area that's completely clear of zones, or the zone type itself is going to change, or the connection to the pads is going to change based on your custom rules. Now, these connections to the pads based on your custom rules are not going to pop up in the DRC check. They're only going to come up when you refill your zones, in which case you end up seeing the result of your custom rule and the output on the board. So as a basic dividing line, this is where we'll cut it. Now, is a custom rule a DRC? There's a couple other things. Look down in the bottom here. You're probably familiar with this. This here, these are the connections. This is connections tab in a pad properties. Down in the bottom here, the connection to the copper zones, note down there, that pad connection and the zone knockout, thermal relief overrides, how thick the thermal reliefs are, spoke angles, all of these properties can be modified by custom rules and they are not DRC. So if you're going to divide it out, these pad properties are not DRC. What else is not DRC? Your pad clearance here, that could be caught by DRC, but will also, if you refill the zones, will properly exclude the clearance there. Your solder mask expansion, solder paste clearance, these elements are also going to be going to change, and that's not going to change in the DRC or in the zone fill. Your solder paste and your solder mask changes, these are absolute changes that immediately affect the pad and the output, whether it's Gerber, 2581, ODB++, any of these outputs are going to be affected by these changes, and you'll see them immediately in both the 3D viewer and the immediate 2D view for PCB editor. Where else? Now this is where we get a little bit shady, right? So mostly not DRC in this zone fill. However, electrical properties, the one in the top, you are going to end up with, that is going to get called out in DRC. So clearance, absolutely. If you get too close to a zone and you don't refill it, DRC is going to pop that error for you. But anything else, your outline display, corner smoothing, each of these are properties of what the zone looks like when you fill it. And you can change it with your custom rules. You don't really see this for DRC. So this is our dividing line. So once we have this separate in our mind, so let's think about what can we do with this information. Well, you'll notice custom DRC rules are changing the same things that you put into the dialogues. So you have two, which one wins? Right? We've put two different properties in there, assuming we made a custom rule that's going to affect these properties. Which one wins? Here's a general rule. So how we stack up the priority of which property wins where generally looks like this. We start in the net classes and the zone properties. These are going to be the lowest priority. Up above that, solder paste and solder mask defaults. These are the ones that will set in pad properties. So this is large, going to smaller. There were more specific. Then custom rules. Custom rules fit mostly in the middle there. Above the custom rules, if you are setting an override, even more specific, you're going to override some of that, and then the highest priority, the thing that was going to set your baseline cannot go past this level, are going to be your board setup constraints. And these are the ones that you should get from your manufacturer. You can't make this, this is going to be a physical limitation. So your board setup constraint should be that physical limitation that you can't go past. And then within that, you set up your preferred net class clearance. But maybe you need to override that net class clearance for a BGA breakout. You want to make your traces smaller in the BGA breakout and have a neck down in there. That area-based override is going to sit right in the middle. And then if you have a pad in that BGA breakout that needs to have a thicker trace, you can override that with the pad local override. So this is how we structure our priority in rule-based design. Now, let's talk about what a custom rule is composed of. Custom rules are composed of constraints and application. So our constraints, we can set these constraints tighter than board-wide constraints. So things we can make them we can make the constraints harder to achieve. In other words, if you're placing a tighter constraint than the board-wide, you are taking, say, the board-wide constraint requires a minimum clearance of 0.3 mil, and if you then want to tighten that, you can set a tighter constraint. You can say that that your clearance is going to for a specific area or for a specific part is going to be tighter than that. Net classes, you can loosen or tighten. You can go either way with this modification on the net classes, and you can create entirely new constraints. And on the right, you see a list of the possible constraints. So annular width, excuse me, connection width, courtyard clearance, diff pair gaps, all the way through skews, text heights. You can affect every single part of your board, and some of these constraints are going to apply to some objects and not to others. So this list of constraints is not going to apply to every object, but because of how we have structured the custom rules, you should be able to read the constraint name and immediately see where it applies. That should be obvious. Where it's not obvious, that's something that we want to address. Now, constraints are those things, those elements of the board that you're able to control. This is as opposed to what objects on the board you want the constraints applied to. Those are called conditions. So you can test conditions based on object properties. Every object, we start from a board-wide object. We'll just call it board object. Inside that board object, you'll have different properties. One property is that board object is a track. And that same property, board object, is a pad. These are two different objects that have two different properties, and we separate out which object we want our constraint to apply to using these conditions. They'll limit the scope of the application. And you can test this, right? So if you have a constraint that applies to one object only, then you're going to refer to that object by the nomenclature here, A. A is the first object, and if you have a single object constraint, so for example, track width, right? This is a constraint that you can set that applies to a single object at a time. And if you want to refer to that object, you refer to that object's properties with A.property. A is the first object. But some constraints are a relationship between two objects. Clearance is a really good example. Clearance is going to be a relationship between two objects. You might want to set a clearance between two objects that have different properties. So what you would do is you would say A property equals value 1 and B property equals value 2. So if you say A type equals track and A and B type equals pad, you are going to set a constraint between any object that is a pad and an object that is a track. Right? So B is going to refer to the second one. And these are commutative. So you don't have to make two rules that says A equals a pad and B equals a track and A equals a track and B equals a pad. You just make the one rule because the relationship between the two is the same, no matter which one you call A and which one you call B. So, what are some useful conditions here? Areas. Areas are super useful conditions because you'll have a part of the board that you want to designate with different rules than the board as a whole. Think of, for example, high voltage areas on your board. You want a higher clearance on areas that you are designating for high voltage input. So you want to set off a specific keep out area. You can do this with areas. You might want to have an area that an area could be, we're at UCSD here. So maybe you have an area of the board that is being exposed to higher levels of radiation. You want a DRC rule that is going to keep your specific components out of this area, and you want to check that. You can draw the area, name the area, and then assign a rule to that area itself. So how do you do this? You draw the rule area. This is on your toolbar in PCB editor, or under the place section, you place a rule area. And you can put this rule area on any layer that you want, but I usually recommend you put it on one of the user layers. So eco or one of your user 1, user 2, you can create an arbitrary number of user layers and specify them here. So you put an area name there, and that area name up there, this one says no HV, that area name is going to let you assign a property based on that name. With a name, you can now create a basic rule. All rules have titles. This allows us to refer to them in DRC and allows you to know which rule is being applied, because we're going to refer to it by its name. So you name the rule, no HV by connectors. And the condition is going to be where A, right? So A is our first item, intersects an area called no HV. Here we're referring to the name of the area that we would have created here, and A's net class is the HV net class. So you assign a net class to your high voltage nets, and then you say, I don't want them anywhere near these connectors. So only net class HV tracks, traces, pads, anything associated with that net class are going to be excluded from the area underneath the no HV. And in the bottom, the constraint is no. Right? So in this case, all we're saying is if you meet both of those conditions, that's an error. Right? So we're not setting a clearance. We're not saying you have to stay a certain distance away from this. What we're saying is you can't meet this condition. If you meet the condition, KiCad will throw a DRC error for you, and this will alert you in your DRC check that your design is something's wrong. Something's wrong. You need to fix it, and it will prevent you from experiencing the potentially bad results from violating this error. Now, with so let's take a look at the difference here. You have some similarities and some differences that you can apply in this. So both of these rules, no HV by connectors, one is A's enclosed by the area, and one is intersects the area. So enclosed by the area is going to be, it has to be fully inside this area, and intersects just means it has to cross over, or it has to be somewhere touching the area. These two will allow you to closely specify what exactly you mean by staying out, but otherwise entirely equivalent rules. Now, you want to be careful, because remember the priorities in our stack up. We need to check for overrides, because you can override these with very with specific pad level changes. Now, pad level changes will override custom rules, but you might not want that to happen. That might not be the behavior that you want in your board, and you want to make sure that your assistant designer didn't take a shortcut and accidentally change the pad connection properties, or maybe you changed pad connection properties when the connector was over here and you moved it over a little ways, and now you would be violating this rule, but you don't see it. So we need to check for it. So you can use your DRC rules to also check to see if your overrides are in place. How do you do this? You disallow these overrides by checking here. The constraint looks for the zone connection style is inherited. This is what we would require. We'd require, so zone connection style is either none, force it to be thermal relief, force it to be solid, or from parent footprint means inherited. So it's coming down from our normal inheritance chart that we have. If it is, you're great, right? That is the constraint, and the condition is that A is a pad. So it's going to check all of the pads for the zone connection style, and it needs to be inherited. If it's not, this is an error, right? So our assertion, our constraint is an assertion. This is true. Where it's not, it'll raise a DRC error. And suddenly, your DRC errors are now not only able to modify what that check is, but we're also able to check to make sure that no one else has modified this from what you expected it to be. So, super useful here for verifying your behavior as you intend it to be. Now, some other options. One of the things that we're working on in KiCad right now, or Wayne is working on in KiCad right now, is the ability to have variance, or I should say, the ability to more easily work with variance in KiCad. However, this means that you're going to you could be putting multiple footprints in the exact same location. Right now in KiCad, if you do this, we're gonna kind of throw an error, right? This is overlapping courtyards. Overlapping courtyards would be an error if you're gonna put both of them on there at the same time. We might want to allow that right now if one is populated and one is not. So here we can allow this overlap. We set our constraint for courtyard clearance to -1 millimeter. If you set a constraint to negative, it's disabled, right? You cannot be that close. So your constraint is always going to be satisfied. We're always going to satisfy that constraint if the do not populate flag for the first one is not the same as the do not populate flag for the second one. So in this case, if A is populated and B isn't, we're good. If B is populated and A isn't, we're good. And if they're both populated, well, then we have an issue. Now, of course, we also have an issue if you look here closely, eagle-eyed viewers will see we might have an issue if we don't populate either of them, and the error would be maybe a little bit confusing. If you wanted to avoid that, you could put another Boolean here and say and. So ampersand for the and A dot do not populate or B dot do not populate is true. So you have to require one or the other to be true, but they can't both be true at the same time. So this is entirely feasible right now. Some other things. Our footprints, we want to keep them keep them a specific distance away from the edge cuts. Potentially, you have a larger footprint or taller footprint that you want specifically to keep away from that. You can specify which footprint you want to avoid keeping it away from the edge cuts. And here, your two objects that you're comparing are going to be an object on the edge cuts layer and an object on the front courtyard layer. These can be any two objects, but if your courtyard gets too close to your edge cut, this is when we're going to say this is an error. And we set this up as a different kind of clearance. This is a physical clearance, which is distinct from our electrical clearance. So the physical clearance here is going to prevent any object from being too close to the edge cuts, any object on a specific layer. So these conditions will allow you to specifically modify that. Some other things we've seen people do with this, non-plated through holes inside SMD pads. Some people like to do this. It is a use case that exists, and we don't necessarily directly support this in KiCad because it seems a little bit off. But if you need this, then you really need it. And you can make it happen by overriding the normal DRC error. So in this case, we set up our rule with the condition we're going to intersect the courtyard of a specific component that we say, all right, we're going to put some non-plated through holes here in this component and say that both of the objects are part of the same footprint. So A and B are both part of the same footprint. And in this case, we're not going to call out an error for the hole clearance, which is the normal error that we would have. If your hole gets too close to an SMD pad, that is a hole clearance error in the DRC, and we can turn that off if that hole is part of the footprint. So we do that for very specific items where we say, all right, we know that we know that L2 needs to have these non-plated through holes in order to properly secure it in place without going down through the electrically through the pad. Some other things that we can do. Silkscreen obviously doesn't adhere where there isn't a mask. You can't put silkscreen, Amit was just talking to us about this yesterday, you can't put silkscreen on copper. Now this basic silkscreen checks will only come up when you are doing silk to silk items, but you want to actually check this with a specific rule, so you can write these sorts of things out. Now, when you write these out, we want to change our specific clearance, and we have more rules here. Exists on layer. We can set exists on layer to change these elements on which layer we want to directly apply this to. All of these examples are part of the larger structure of the custom rules within KiCad. And we are only just brushing the surface with some of these examples. Now, where do you go to find the larger examples? Well, you go to within KiCad. Now, this is where this presentation gets particularly dangerous because, as everyone knows, doing on-screen presentations is always going to be potentially problematic. So we're going to live dangerously here, and I'm going to open up all of those. I'm going to open up one of our demo projects, and we're going to open up here our VME Ren, because VME Ren, everyone should look at this project. This is an amazing project that CERN put together for their high energy systems in Geneva. Now, as we open this project, it'll take just a moment while we tessellate our copper zones, and then we're going to be able to look at this. Let's see here. Yes, okay, so here we are. A nice, happy little 12-layer board with lots of complex elements in it. If I go to board setup and then down to custom rules, this is where you find all of your custom rules. And here this one is actually distributed with KiCad. And so you'll be able to look at all of the different custom rules that they have come up with as well and adapt some of these to your use cases. So things that they have put together here are conditions here. For example, the differential pair should have a max uncoupled length here for differential pairs on inner layers, right? This rule is going to check to make sure that you're not violating some basic rules that are going to cause issues with your signal integrity. If you're not sure, there are a couple things that you can do. Number one, some people haven't seen this here, but in the top right-hand corner, there's this tiny little underlined hyperlink called Syntax Help. You should definitely click on this. Oh, and then it, of course, shows up on the wrong monitor. You should definitely click on this, and then you get a Syntax Help here. This is a wonderful document, nicely written. It is directly copied from or copied to the docs that are maintained at docs.kicad.org, which you should definitely go to and take a look. However, you don't have to be online to get that. You can see your rule clauses and constraints all the way here, but the important part is down at the bottom. Scroll down. These are all constraints. Scroll down. There are a lot of constraints. Now, just what we talked about, items, you can set the severity of the warning, and then we get down to examples. The examples are where you want to be, right? Because it's so much easier to write a rule starting from the examples and editing it to do what you want than to look at a blank screen and say, okay, I need to start typing rule, right? Copy and paste this stuff. You have some examples here for that, and you say, oh, that's just 4 examples. Yeah, there are 42 different constraints there, and we only got 4 examples. Keep scrolling. Now, notice properties of objects are available for testing, right? And we'll give you a link to the docs website, because we really think docs website, docs.kicad.org, is super cool and really awesome. Graham's done an amazing job with it, so please go take a look at it. You will thank me after you do, and Graham. So our expressions, a number of different expressions, but if we keep scrolling, you see we're only halfway down this little help window. Keep scrolling. And down here we get more examples. Now we're getting into the more complex ones. And now we have a whole list of complex examples with comments on what we're trying to do, how you would use this, and when it's important. So keep going. Look through this list and find the ones that are interesting to you and use them. Put them in your boards and test them out, because they are really powerful and they can save you time and money. So with that little advertisement, and we're still scrolling through examples here, so there's a lot there. we'll close this down and we'll go back here. There's also another aspect of this custom rule editor that you should be aware of. Namely, that when you start typing, we try to make this easy for you. If I start typing here, I get autocomplete. You don't have to remember everything. Rule, new, whoops. I should, let's see here. New, there we go, got my fingers in the right place. Rule. Now, what happens here? I need to open a parentheses. As soon as I open a parentheses, these are the 4 things I could put there. I can put a condition, a constraint, a layer, and a severity. I can choose any one of those, but my autocomplete is going to tell me which ones are valid for where I am right now. So I'm going to set this one to be on a layer. What layers can I do? I push spacebar and I get the list of the layers I can do. This is what you should be looking at as you're writing these custom rules, because these are going to help you write accurate and correct ones. So you can set rules here, inner, outer, or a specific layer. So we'll do outer layers here. And each of these are going to be enclosed in parentheses. Now, on the next one, what do we want this layer to? What do we want this to do? On the outer layers, we want to make sure that, for example, we don't. Let's see, outer layers. We'll make an example here that sets up a minimum track width size for all of the all the tracks in the outer layers. We can have them thinner on the inner, but we want to have a thicker track width size on the outer layer. So we open up our parentheses again, and now we get this outside again. Our element here is going to be first. You can either do a constraint or a condition first. It doesn't matter which one. Like the order doesn't matter here. It's just the content within the rule. So we'll do a condition. Now the condition here is going to be, what do we want? Well, layer has already set the condition that the layer has to be on the outer layer. So what are we interested in setting a condition for? We might want a net class, or we might want an area-based rule. So we can set any kind of condition we want, but the conditions all go in quotes. After the quote, we start with, what are we doing? Well, we're referring to a condition should refer to a property of the object. So that property always starts with A and then a period. All right, now we're talking. Now a period gets us now this autocomplete list. How do we define what it is that we're interested in? All of these are going to be the properties of A that we can constrain this condition to. So we are talking about say tracks. So we might want to have any of these items. The end X and Y exists on layer. So some of these properties, for example, fill and fill mode, aren't going to relate to tracks, but it doesn't know yet that we're talking about tracks with A, right? So we could say type. A type equals, and now what type? So now the outer syntax has double quotes. So if we're going to specify a type inside, we need a different quote on the inside. So we'll use single quotes on the inside. When we do the single quotes, now we have all of the types. These are the types that KiCad knows about. Bitmaps, dimensions, footprints, graphics, groups, leaders, pads, targets, text box, tracks, vias, and zones. What do we want to set here? If we want to have type text. Here now what we're doing is we're setting some kind of condition on text objects that exist on the outer layer. At this point, we can set that constraint, and the constraint now, as soon as I press space, now we're ready to show the next thing. What do we want to constrain about this? Well, on the outer layer, obviously, text on the inner layer. Maybe you could have copper text on the inner layer. So on the outer layer, the text should only be a specific text height. Right? So now we can set the text height equal to, whoops, and we can type in any string we want, so 1.5 millimeters. So now, what we're saying here, did I constraint text height? Whoops, sorry about that. This is open quote, minimum text height, right? Because you can set minimum and max separately. So minimum text height is going to be 1 millimeter, and maximum, then maximum, and we don't care about optimum, so we're going to leave that alone. Maximum is going to be 10 millimeters. So we don't want text bigger than 10 millimeters, and we don't want text smaller than 1 millimeter. And now we have everything we need for this new text rule, but we want to check one last thing. Down here, this button right here is going to check your rule syntax. It won't work if it's improper syntax. So, when we click here, it says unrecognized item rule, expected constraint, condition, or disallow. So what we found here is that we have in our system here we have a problematic syntax. So we messed something up. What did we what did we mess up here? We have likely.
You forgot you're in Lisp. You're missing brackets. Line 17.
Thank you. There we are. That's what happened. Oops. I probably clicked on something like that. There we go. That's exactly what happened. Notice how when I close the parentheses, it's going to highlight the opening parentheses. So now, each of these, so much better. Whew. I was worried for a moment with this live demonstration that we were going to crash and burn, but now we are, in fact, no errors found, and we're able to say okay, and then we can run our DRC check. I'm not going to refill all the zones here because this board, refilling the zones, will take a couple seconds. But we can run our DRC check, and this is actually going to now check to make sure that none of our texts are actually outside of this exclusion zone. That's double. And survey says almost. So when I run KiCad on my machine, I'm usually running it in debug mode, which gives us a little bit more, takes a little longer to run on this, but of course we're also dealing with the 12-layer board running, I believe at this point, upwards of 1,500 individual checks at one time. So now we have a number of warnings and a number of potential errors. Questionable solder mask, track length. So these elements are going to pull out. So notice what this says here. Track length out of range because of this rule. So if we take a look and see which one this is, it is going to refer to, this is what you actually want it to do. You want it to refer to the custom rule, the name of the custom rule. This is length DDR byte 2, the custom rule here. And which ones are violating this? It's going to be this pad, this pad. So two pads are the start and end pads, and then the tracks between them. Our minimum length is, if I expand this, the minimum length is 39, and the actual was 38 and a half. So it's going to catch each of these. There are hundreds of custom rules in this on a massive board, and they're all were checked very quickly while we were just sitting here on a laptop with a debug build. On your machines, this runs much faster. It's a super fast, super easy way to get all sorts of rules verified and contained in your designs to prevent these kinds of errors from creeping into production. So with that, I want to thank you for your attention. I'll open it up to questions.
We actually have a question in the chat here. The first question is, can you add an AI model to KiCad?
I love the topical questions. So the question is, can we add an AI model to KiCad? Yes, you can you can AI all of the things. I don't know what you're going to get from it. In fact, I think this question might actually be more appropriately answered by a talk later on today. Where is Jeremy? Oh, there he is. All right, so tune in later today for Jeremy's talk on exactly some ways that AI might be helpful, potentially, to your KiCad models. But if you just toss a large language model onto your KiCad design, you're going to get garbage, because KiCad is not English, and where it's been trained on all of the publicly available text out there, it's going to get all of the publicly available mistakes out there. So your garbage in, garbage out principle will apply, and you definitely need to approach this with caution and define the use case that you want AI to solve. Do you want it to solve custom rules? There's a potential there if we were to train a large language model with the comments and the rules that come out of it. However, this is going to not replace the work that goes on in between your ears. It might get you to a text that looks plausible faster, but I would definitely not send it to Amit before you actually double check your AI output. So I hope that answered the question, but definitely tune in later and learn. Yep. Tune in later, and you will find some better use cases for how you might want to try AI in the context of KiCad.
Hi, Seth. Could you describe if there's any thinking on how to effectively test new rules that you're applying to some complicated board you have? How to check that the filter, I guess what you're calling the conditions, really apply to just the objects you want to, or in fact include all the objects you want to, and that the results that the rule provides are doing what you expect.
Right. So the question is that is there a way to preview which objects are going to be captured by the conditions and whether or not the elements are going to be properly applied. So the answer to the first is not yet in a easy way. So we're not able, we don't have a way at the moment to show which objects are directly captured. However, you can find an object that you know should be, and we'll look at it. However, This is a temporary issue because we do have an open work package that we are building right now for our friends at CERN to do exactly that, to show the elements that are applied in individual rules. So look for that in version 10. And for right now, what we would do, for example, in this case, we're interested in what rules might apply to this object, or rather, you have written a rule and you say, this rule should be applied to this track because it's in the right area or it belongs to the right net class or that or any elements there. Under the inspect dialog, you can check clearance and constraints. So clearance is anything between two objects, and constraints obviously only applies to a single object. So in this case, if I want to know what applies to this object, I go to my constraints and I click on it, open it up, and we can see the constraints that could apply to this are track width, keep outs, and assertions. And down here, we're going to check this, and we say unconditional constraint applied. Checking net class. Membership is not applied, right? Membership not satisfied, constraint ignored. As we continue to scroll down, we will find that all of these are ignored except for, well, here. Checking net class DDR4 byte 2 track width, constraint applied. Well, now we know that this DDR4 byte 2 net class constraint does apply to this track, which means that KiCad thinks that this belongs to that net class, and it will apply the constraint to that net class. So this dialog is where you would find whether or not an individual item applies to that, and whether or not it is in fact being applied without having to run the whole DRC dialog. Obviously, the other way to check is to cause a violation and see that and make sure that it comes up in your DRC the way you're expecting it to. And you might do that with something like a keep out area. If you're keeping out HV, you just put an HV pad in there and say, okay, let me make sure that if I do make a mistake in the future, it's going to cause it to pop up. Right, but that's not really repeatable. Definitely not really repeatable. This is a way to check that the conditions are satisfied, the constraints are applied. You can do the same thing with the clearance. You can see that the clearances are applied based on the conditions that you have set out in the rules. And then in version 10, we'll be able to highlight individual elements where our conditions match. Does that answer your question? Yeah. Okay.
Yeah, next question. I wanted to ask you whether we can reference text variables inside the rules.
So the question is, can you reference text variables inside the rules? So which text variables are you considering in that?
Well, if you wanted to globally set something but change it from design without changing the rule, so you might put a number in somewhere, for example, and have the number come from a variable and apply in the rule.
So if the variable were to say 5 millimeter or something like this, and can we dereference those text variables at the moment? At the moment, that's not. We don't call out those individual, or we won't resolve those into the custom rules, and the reason for that is we check that the text is compiles correctly for the design, and missing variables we would need to put in an additional check to see that the variables are actually defined in there. It's not in there yet. That sounds like a really good idea. So I would encourage you to submit that wish list, and we'll see if we can get the engine.
Thank you.
And if I'm answering this incorrectly, Graham's going to raise his hand and point out that that is in fact documented on page 47 of docs.kicad.org.
got a quick question. The actual text, when you like check your design into GitHub and you, let's say, had somebody else make a pull request against your design rules, I was just curious if you can talk about like where the design rules actually stored in the project, and does that show up? Is it easily diffable? Does it? It looks like text to me, more like code. So I'm just curious if it
Looks
was
like text to me too. It is text, and let me show you where that is. Pull up here. Let's see here. Where's my? There we go. If we pull up our dialog here, if you look right here, this file, this is vme-ren.kicad_dru. DRU stands for Design Rules. We name our acronyms in the same way that most physics experiments will name their acronyms. We pick the letters that we like. So this file here, if I right-click, I can edit it in a text editor. Oh, if it could find Vim. So right-click on that and open it in a text editor, and it will show you the exact same text that I showed you in the board setup. That is then certainly diffable. However, if you're going to merge a pull request, I would highly recommend running it through the check in PCB editor before merging, obviously, because otherwise you run into things like I was just typing in there. A missing parenthesis is going to mix up our syntax in a way that might not be entirely obvious.
Can you run that check through the CLI, like as part of the CI check?
The question is, can we run the check through KiCad-CLI to verify that? So the syntax check, I don't believe is directly available separately. However, running DRC is available, and so if you run DRC and you get an error that says invalid syntax, that's going to that's going to tip you off that don't merge that pull request. Okay, thank you very much. Let me pull up our next talk. If you know who you are, feel free. Oh, there. All right. So let's see. I'll just swap out. Do you have your laptop with you? Oh, you already have it. Okay, great. Let me just grab this here. Move out of your way.
Great, thanks, Seth. This is your water, too.
Oh, yeah, thanks.
Thank you. All right. Good morning, everyone. Okay, great. Yeah, it'll take a second to set up, too. Thank you.
All right. So our next speakers, plural, are Dr. Karcher Morris and Dr. Colin Zyskowski. I really apologize if I got that one wrong. They are professors at UCSD, and they have worked in the School of Engineering, and as in working to build PCBs for student university-based projects. Karcher Morris has earned his Ph.D. mechanical engineering, working with the Talkie Lab for biomedical devices, and focuses on design, numerical methods, and control theories, while Colin Zyskowski considers himself to be a maker at heart and is, although not formally trained as an engineer, he has spent almost 20 years learning by doing, and so fits very closely in with the rest of us. And Colin has worked at Envision Maker Studio for the past 7 years. So please give a warm welcome to Karcher Morris and Colin Zyskowski.
All right, thanks everyone. Good morning. Super happy to be here. I think before Colin and I get started, we'd like to kind of set the stage a little bit. We'd like to share a little bit about our backgrounds, the university, a little bit about ourselves, and makerspaces too. So maybe let me get us going here. So hopefully you've had a little bit of time to walk around campus. I'm a big fan. I'm a big fan of our campus. I hope that you didn't have too much trouble parking. I think a lot of you have been walking around because of the parking issues. That's one of my biggest complaints about the campus, but at least walking around all the way from the medical center across the freeway down to the pier, it's a super beautiful spot. So a little bit about me. I'm a teaching professor, so my focus is in teaching. I very much enjoy teaching. I'm in the electrical and computer engineering department. I'm a huge advocate for project-based learning, makerspace courses. My research focus is more in engineering education and medical devices. There's a big conference in Montreal, American Society for Engineering Education, if you're interested in checking it out, in a few weeks. Medical device design. Here on our campus, we have 3 different hospitals. We have the VA, Scripps, and the Jacobs Medical Center. And there's tons of medical doctors with lots of problems. So it's a lot of fun just like working with them on different activities, solving different problems for them and for their patients. So it's a really good community that I think a lot of our making experiences kind of get into, and it's fun. I also spend some time in service. So that's kind of the teaching professor role. So teaching the focus, a little research, and then service. We have on-campus service, but I also spend a lot of time with community colleges close by and high schools, and we have a good alumni network too. So just a little bit about me there. But our school, our Jacobs School of Engineering, that's where you're at right now. And here's just a few of the buildings that we have. A ton of buildings, a ton of people in them. This building that we're in actually right now didn't make the cut of some of these. A lot of these are new, updated, kind of good spot. We have 6 different engineering departments, so they're spread across all these different buildings. Although we have these different departments, I think it's kind of interesting that we have a lot of electrical engineers that are in the bioengineering department. We have a lot of bioengineers that are in the structural engineering department. We have a lot of structural engineers in the aerospace department, right? So even though it's there, it kind of helps mostly with our students, kind of guiding them through in a different department, giving some themes. Let me give a few more numbers on our school. We have a lot of faculty. So we have almost 300 faculty just in the Jacobs School of Engineering. In just the last 11 years, about 2/3 of them were hired. So we've been growing a lot. I'm glad to be, one of those, but I think it's nice that we have been growing a lot. It's been a pretty big impact. We have a lot of research expenditures. Naturally, this is a big research hub. Hundreds of millions of dollars each year go into research here, and a good mix. I know federal spending is a challenge at the moment, right? But 50% about come from there, and the rest, we have really good relations with industry and philanthropists in the region. So we have a good mix of support kind of driving a lot of the energy. But really driving it, naturally, we have lots of great students. This is where I spend a lot of my time, is with the students. Almost 10,000 engineering students. This is a big hub of engineering students. And I would say we actually impact more. There's a lot of cognitive scientists, math students, physics students, that are able to, we're lucky to hang out with them too in our engineering spaces as well. So, and visual artists, I should throw that out too. We got a good, strong group of them in our world too. And I think what's important about that is they're getting degrees, right? So it's so important for us to be figuring out how to prepare them to escape the school and influence and hang out with all of you folks in industry. So it is our job to figure that out and prepare them for it. So this is an important step for us to kind of figure this out with our courses. And in a moment, we'll be getting into it. But I did want to take a moment to kind of share this big initiative that started in 2016 by the then dean and also still now dean, Al Pisano. he had this big push for experiencing engineering. And we call it the E4 initiative. We say that because we want all our students to experience projects, hands-on education, not just in their senior capstone, but each of the 4 years that they are a student here, right? We want them engaging with projects and knowing what side of the soldering iron to grab and things like that. Very important, right? Not at the last quarter. So this has really been a big part of my energy. I've been able to ride this wave, and a lot of other things on campus, educational activities have kind of geared up because of this. A lot of time, energy, money has gone into this world with our partners and maker spaces. So one of those maker spaces is actually down here. I spent a lot of time here. It's a nice maker space and teaching facility. It's on the 3rd floor of the Structural and Material Engineering building, SME building. It's kind of by the trolley. If you've used the trolley, you could even just probably walk up there. We have a pretty public campus, so it's a good spot. And in this spot, I've been very fortunate to work with some great students, talented, ambitious, caring, project-focused students who are building, making, breaking things all day, every day in there. And the director of that spot, super talented. I've been lucky to work with him on my classes, and many other instructors work with him on theirs. He is Dr. Colin Zyskowski. So I'd like him to come up and share a little bit about his energy in this space and spot. So maybe we can give him a nice round of applause, too.
Thanks, Karcher. Hello, everybody. My name is Colin, and I am the director of the Envision Arts and Engineering Maker Studio here at UCSD. I am not actually, as was mentioned previously, a professor. So I do, no, it's all right. But, you know, figured I should make that clarification. I do engage in a little bit of teaching. Thanks to Karcher, we have engaged in some sort of extracurricular projects that involve PCB design and circuit board building, things like that, that I'll get into in a little bit. But yeah, I guess today I'm going to talk very briefly about 3 specific topics. First is Envision and what we do there, the kind of makeup of the space and whatnot. Second, I'm going to talk about a project that Karcher and I have been working on for the past couple of years, I guess, and is now sort of wonderfully coming to fruition. And that is the Envision Tools for Imagination boards. So that's topic number 2. And then third, I just want to give a brief shout out to KiCad and the open source community and how it's benefited our students. So yeah, a little bit about me. As I said, I am the director of Envision Maker Studio. My primary task there is to support the student staff. So we have a couple members of our esteemed staff and community present today. Thanks for coming. And really, I am there to support and enable the students and the culture that I guess we hope that thrives in Envision. We are, well, actually, I'll get into that in a moment, but my specific interests lie mostly with PCB design. So my background is actually in the arts. I have a bachelor's in English literature, I have a master's in media arts, and I have a Ph.D. in music. All of which make me really good at designing circuit boards. So I'll talk about how I got there a little bit at the end of the talk. But I'm really interested, of course, in digital music and designing controllers and digital instruments. Engineering education is, of course, not just engineering, but arts education as well, is really important to me. and then just studying interactivity, how humans interact with machines and computers. That's something that I really find fascinating, and it's largely what my dissertation was on, networked robotics and sound source localization. But yeah, I also really love just dealing and hanging out with and working with students. And I tried to do as much of that as possible through supporting student orgs and working with individual students on personal projects and things like that. So now a bit about Envision. We are a makerspace on campus. We're one of several. We're not the biggest, we're not the fanciest, but we are definitely the hippest, as you can tell. But yeah, we are sort of half engineering and half visual arts focused. We have a lot of resources to support both of those pursuits. So we are a crucial part of the E4 initiative that Karcher talked about earlier. So we were one of the first concrete steps towards realizing that goal. And we opened up in 2016 as your basic makerspace with things like 3D printers, laser cutters. We have some woodworking tools. We have, I just remembered that I have notes. So we have some basic woodworking tools. We have a CNC router. We have, resin printers, all of that kind of stuff. We have a whole craft area that is, not used for any classes necessarily, but gets a ton of use for personal projects. All told, we have 5,627 square feet of makerspace and classroom. And while we are extremely engineering-centric, we have a large focus on visual arts, we're getting more music students involved in the space now. We have a lot of cognitive scientists who come in. We really have students from all over campus who use the space. A lot of it is for classroom use, but we're really proud that tons of students come in just to use things for personal projects and to make things that they think are just fun and cool. And we try to support that as much as possible. We have a really incredible large community of makers, designers, artists, engineers. This is students, this is staff, this is faculty. There's just a great variety of people who hang out in the makerspace and who are just interested in seeing what other people are making, what other people are interested in. It's how I, just by interacting with students and other faculty, it's how I, think I stay on top of things, even if I'm a couple decades behind. But yeah, we just, as you can see, have really amazing people. Hey, I know that person. You can see Karcher. He is available, by the way, for private violin lessons if anybody is interested. Yeah, so it's just a really awesome space. You are welcome, if you have time this afternoon to come by and just walk through the space. It's not huge, it's not fancy, but it's pretty cool. Yeah, quickly, I'd like to say one last thing about Envision, and a very important thing, is that our primary focus, our primary purpose, our raison d'etre, is to serve as a classroom for engineering and arts classes. So one half of our studio, one half of that 5,627 square feet is actually classroom space. It is the space over there on the lower right. So it's a large space that can be, all rooms combined into one large 90-seat classroom, or they can be split up into 3 individual 30-seat classrooms with nice AV hookups and all of that. So that's where the lectures happen. That's where students go to listen to people like Karcher and the other faculty tell them how to, incorporate theory and all of that. And then they go across the hall and they have, 2,700 feet of makerspace to hang out in and build in and work in. And it's a very unique spot on campus for that reason, because we have combined the classroom and the makerspace into one integrated unit. And I think it's probably one of the few rare cases of that existing anywhere. So we're very proud of it. And we're also proud of some of the projects that we've initiated, such as the Tools for Imagination, which I'm going to talk about now. That was the classroom slide. Okay, so the Envision Tools for Imagination. These are circuit boards that we have designed in-house at Envision, and they are meant to teach circuit board, PCB design and development and building. So these are meant to be as simple as possible. They are currently, the ones that we have functional right now are all based on the ESP32 microcontroller. Most of them use the S3 Mini chip. We have one that requires Bluetooth, which uses the Rover, and I'll show you all the boards in a moment. But yeah, it's proven to be a great way to introduce circuits and PCBs to undergraduate education. Karcher is going to talk specifically about the application in the classroom, but I'll just go over what the boards are and what they do. So the main board that we have as part of this larger ecosystem is the S3 dev board, and it is an incredibly basic, very simple circuit board that is just meant to serve as a basic microcontroller. It, of course, has built-in Wi-Fi and Bluetooth, and it's got a very basic charging circuit on it, so if you have it plugged in via battery and plug the USB, it will automatically charge. It's got a simple power switch, 2 user buttons, 2 user LEDs, and that's it. A boot button, a reset button. Yeah. Basic as that. All of the components are 0805 sized, which makes it really easy for students to build. And Karcher is going to talk about that process, I think, in ECE 186. But yeah, so that's the main board that we have as the sort of brain of the Tools for Imagination. The next is a very simple shield that works with the S3 dev board, and that is just a VU meter. So all that we have on this board is a very basic microphone component, and then 11 LEDs. These are fairly large LEDs, and what makes it great is that you can teach students how to do SMD soldering with a soldering iron using this board, which for me was a sort of incredibly important part of the process of prototyping electronics, was just learning how to build a circuit board that had surface mount parts with a soldering iron. It's not fun necessarily, it's not easy or quick, but it is, I think, really incredibly important to know. And as college students are getting into this fast prototyping of electronics, it's incredibly useful. So that was sort of the purpose of that board. And then once it's built, they can just do, the very most basic forms of interaction with it. So the microphone listens to audio in a room, and the LEDs respond, and it's a volume unit meter. So yeah, cool, simple projects for programming and interaction and PCB building. Then we start getting into more fun stuff like motor control. This is another shield, the motion shield that we have for the ESP32S3 dev board. And of course, this focuses on motor control and motion sensing. So it's got two really nice dual motor drivers, 24-volt input, which is great if you want a car to go really fast or a quadcopter to fly really high. It's got 6-volt servo power. You can see the 3x8 grid there of through-hole components, and that is for servo connection. And then we've got the motor driver outputs at the bottom there. Those are, you can hook up, 2-stepper motors, 4 DC motors, up to 8 servos. So very fun, useful board for doing any sort of autonomous vehicle stuff or obstacle avoiding robots or maybe line following robots. But it also has a really nice IMU on it. It's got the BNO 086 motion sensor, which has the accelerometer, gyroscope, and magnetometer. And yeah, is super functional and great for students to use for any sort of entry robotics projects. Next, we have the sensor shield. This one is kind of still in development, but getting close to where we want it, and we'll have some students working on it over the summer. Wink, wink, nudge, nudge. And yeah, it's great for getting students into interactivity, really sensing a ton of different stuff, but it's got the APDS 9960, which is a pretty cool gesture sensor and color sensor. It's got another less expensive IMU on it. It's got the I2S microphone. It's got an IR sensor, the RGB LED for visual output, a couple user buttons. It's really just a great tool for programming, interaction, and coming up with, interactive projects. Lastly, we've got the BLAMP, which obviously stands for Bluetooth Amplifier. And this is a project using the ESP32 rover, which is required because it is full Bluetooth capable. And this is a project that we designed for students to start working with some basic audio programming, and also some design beyond just the circuit board. So Karcher and I worked on another project where we taught a program called the PATHS program, which is for underrepresented students who want to get into STEM. And so the project that we came up with was to have them build a Bluetooth speaker. So they actually build this circuit board themselves. Again, this board uses only 0805 components and larger. And we can use this to teach students who have never even seen a circuit board before how to build the circuit board. So yeah, we have cog-sci students, math majors come in and build this circuit board and then create their own Bluetooth speakers. So yeah, it's proven to be a lot of fun. Students seem to really enjoy it. They walk away from the course with their own custom Bluetooth speaker, which they can, they also learn a little bit of CAD maybe, or 3D design, and maybe even some woodworking. Yeah, it's a really fun, all-around project. So yeah, those are the current tools for imagination that we have in our toolbox at the moment. And Karcher is going to, of course, talk more about how he uses them in the classroom and the types of projects that students are doing with them. But yeah, just wanted to give you some background on what they are. And yeah, that's about it on the tools for imagination. Lastly, I just wanted to say a word about KiCad and open source philosophy. And yeah, just how important it is. First, I mean, to everyone, but how important it was to me personally. And so, as I mentioned, you know, I have a lot of background in music and the arts. I have zero formal training as an engineer, but because of programs like KiCad and because of you know, people who believe in sharing and in open source philosophies, it was possible for me to, you know, after I was 30 years old, which is when I went to grad school, it was possible for me to get into circuit board design and to start working with PCBs and electronics. And I was able to, you know, I had never even, I think, seen a schematic until I was 34. I'm 47 now, by the way, to give a little bit of context. But yeah, I was able to do it because, you know, people share and people are okay with not having everything be proprietary. And that, of course, had an immense impact on my life. We're fortunate, as you know, we are in universities and taking college courses, that this stuff can be, that we can afford to do that sort of thing. But there are a lot of people out there who can't. And you know, the openness and availability of programs like KiCad and things like GitHub, they're just incredible, and we should do as much as we can to support them. And I want to say, you know, thanks to KiCad for putting on this conference and for having us speak here, because it's really awesome and, you know, helps to get out that open source vibe and support it. So thanks.
All right, thanks, Colin. Thanks, Colin, for all you've done and all you do still. Yeah, it is a fun environment to be in, and it is cool to see all these students engage in such a way. Yesterday, I had a couple good conversations, and it got brought up that, you know, this ECE thing, you know, what is ECE anymore? I think it's interesting, right? We have a lot of students graduating with the electrical engineering degree, and they're all over the place. It is great. We have so many different depths and areas that students could delve into. Maybe I'll just go back. I love asking this question in my class. In both of my classes on the project end, the beginning and the end, and I'll talk about those in a second. But it's an important question because I think if I went to ask all our different faculty, we have over 60 in the ECE department, I'd get over 60 answers to what ECE is. And I like that, right? I mean, there is no right thing. We may be leaning after the last few years a little bit more on the machine learning end of things, but that's nice too, right? We're getting pushed and pulled as the years go by, and I am fortunate to be a part of that push and pull, and Colin too. So yeah, we have so many different depths and areas. It is tough to define. When I ask students to define it to their peers and explain it, I expect that this changes over the years, right? It's our job to influence every faculty, every peer is going to influence in all these different ways. Oh, let me get to this. Since that E4 initiative, the EC department really has pushed. These are a few of the hands-on classes. I just put pictures there, but they're building pinball machines. They're working with LabVIEW and makerspace projects, building like Ferris wheels and all this stuff, autonomous cars and vehicles, working on both the the front and back end of all these different. We have art of product design, rapid prototyping. EC5 and 196 is where I wanted to focus a little bit more time on. And EC5, we do have a poster out here if you want me to delve in any more on these classes. I know there's a lot of weeds to get into, but this class I've been super happy to be a part of and grow and influence in different ways. But the idea is we're trying to explore all those different depths. There's so many different ones. We try to make it make some sense by having a series of, we call them labs, but they're really projects that they work on. There's a lab 0 too, where it's just intro to microcontrollers. You actually see some up there. Those are the Arduino Megas. We've just switched over. Colin has talked about it, but this last quarter they were all using the Tools for Imagination boards, and it's been really nice making that making that switch over for the students in the class. But again, they go through a series of labs. So you can see us covering communication theory. That's big here. We have, Qualcomm. Erwin Jacobs was an EC faculty, and obviously he started Qualcomm and is a huge philanthropist in the area. So our school has benefited greatly from him. So it's nice to actually start. We have a lot of faculty in the information theory and communication area. So it's good to kind of talk a little bit about the theory in the lecture, but get into that maker space and actually build some things related to it. Lab 2, they start with some like high pass, low pass filters using O-scopes, virtual benches. We were using the NI virtual benches, so it's easy to use in the maker space. But they end with building their own speaker, and it's not just following a diagram. They actually start to understand, how these high pass filters and low pass filters influence their build there. And then, being hardware for a little while, we turn a little software. We use MATLAB or Python, depending on the quarter, where they dig into signals, right? Digital signals this time. So we could see 1D and 2D signals and do some image processing, and that's pretty nice. And we end the 10-week quarter, super fast-paced class in this spot. We end it with a robot. So they learn some controls, some PID, they get to build it, they get to integrate some of the things they've learned, some soldering, 3D printing, and all these things, and they end the quarter with a competition. So I think they like the idea of not having a final exam. They put a lot of energy into that project, but they soon learn that projects take a lot more time and energy, but are rewarding in so many different ways. So just in that Maker Studio, just in this class, it's 300 students. There's 20 classes in there, Colin, or so, something like that. You think of how many students are being pumped through this makerspace, but I'm glad we require it, right? It's a good requirement to include, and that's, again, what the initiative has been doing in so many ways. I just wanted to pull up a couple things, give a couple of shout-outs here, too. To Anurag, he was a Project in a Box. That's a student organization on our campus. We have phenomenal student org energy on our campus. Project in a Box, PIB, he created one of these for our class, and we actually had 2 students showing off some of their new designs that we're going to influence for next year that were all built in KiCad. And they designed these out, and what's cool is they don't just design them and then they're done with them. Hundreds of students have now used this to learn how to solder. So there's a nice little area on the top, a little soldering playground to do their first header pins ever, maybe a resistor and a jumper wire or something like that. And then they go slowly through this build and get to solder these parts and get to see this work. So it's a really good way to, Anurag is now a master's student, but when he did this, it was an undergrad, and for him to work on the design skills and influence such a great group. So that's just an example of, learning to solder in the class. It can be fun when we use these PCBs. KiCad, I want to zero in a little bit more on Lab 2 there. So before Lab 2, we have a workshop that's focused on KiCad. So students will go through, they'll watch a few videos, we'll do an in-class walkthrough. And then what I like is they get to see this kind of workflow a little bit. Again, we're covering a lot of things in class, so it's hard to get into too many details, but I think it's motivating. Going through, for them, if they just saw that schematic, that's crazy, right? You can imagine your first year, you're 18 years old, digging into this for the first time. But they build it out on a breadboard. They test it with a function generator and O-scope. They see the signals flowing through. They're learning what hertz are, right? And to be able to see that and hear it is wonderful, and go from a breadboard to those perf boards. Reed had a great presentation yesterday. He was sharing how difficult that process is, right? So just being able to engage and struggle there, but to take it further. Before COVID, we required it. Since we've made it an extra credit assignment just because of timing, but we'll see if we could get it on board. But extra credit is they would design in KiCad, or designing in KiCad was a requirement for this circuit just to practice KiCad a little bit more. But if they wanted to actually go through, pre-COVID, we used Oshpark codes. They gave us all these codes and we were able to order through them. So the students would go on there, put their PCB and order it. And it'd be, again, just to do that in a few weeks. Pretty amazing experience, in my view, that I certainly did not have when I was an undergrad. So I guess just one quick thing is there's all these other classes, right? UCSD prides ourselves in theory. I'm probably going to go a couple minutes into the coffee break, Seth. I hope that's okay. I'm sorry, everyone. I guess you could just leave if you're bored. But thanks. Yeah, sorry about that. But no, I just like to share a little bit more. But our school prides ourselves in theory. We're very good at the math and the physics, right? That's so important. But we have found that these classes can complement. In this case, EC5 kind of brings this up. You know, we start saying, hey, if you really like this lab too, you should check out some of these classes. A couple of them are required, but most of them, we have so many different classes that they could go in that depth and that direction and strengthen those skills. And I think that's really nice that we have all these different faculty able to teach these different areas. But one thing on the other end, so now after they've taken all these classes, they have these different depths from left to right. I have this 196 course that we've been able to kind of reinvigorate, redesign over the years. This is the course description. I kind of just put that there. But for time, I'll just jump to what I tell the students the class is more about. And I like to say that they should build an awesome. I like the word relevant. I don't get overly excited about novel. I think, you know, having a relevant project in this class is really nice. Hands-on project, of course. That they work on a team, that, you know, there's pros and cons of that, right? It's challenging to work on a team, but very rewarding. They work on teams of 3. They get to work on technical skills, and they really get to think about, you know, a lot of them are going to be entering the job market in the next year or so. They should be working on a project that really that they could put on their resume, right? Those things are important. They could bring the skills that they've had. So this is a senior design class, and the design method that I like to share with them and force upon them in a way is the double diamond of design. I think engineers love solutions, right? We really like solving problems, but sometimes we forget about the problem part. So I like that there's a little bit of a focus when I bring this up on really understanding a problem well when you're going through the design process, you know, at that high level. We are trying to cram this into 10 weeks, so a little difficult. So we kind of looks more like this, just because we do like solutions a lot. So I think it's very much worth the 2 weeks, but just giving you kind of an idea that these teams, they form in the first 3 weeks. We explore problems, or in the first 2 weeks, and then they have to define that problem very well before they could really venture off into solving it. So the way we kind of set this up, I've tried to keep this timeline to help us. But you can kind of see we have these mini projects. This is where the tools for imagination really come in. And then we have the final project. They're thinking about the final project from the beginning with the problem, but really we get their skills kind of worked up in the first few weeks. And I'll zero in on the VU meter. That's what Colin shared a moment ago. And again, if you want to check out the booth a little later, I could show you some of these examples. But just starting with the light shield, we actually, day one is not a syllabus day, right? We don't just sit there and talk about the syllabus. They actually get these these printed circuit boards, and they have to hand solder this. So they are SMD components there, but for many of them, some of them don't actually come from a pure EE or have taken EC5. So for some of them, just getting soldering again going is good. But I love that they see that on day one. Then day two, what Colin was sharing, he actually comes in and gives a demo on day two, and it's they build out, they assemble that dev board. So in EC5 we use the dev board, we don't assemble it, we actually get them assembled for the class, but then in this class they actually assemble it. In those 2 days, it's a little challenging to go through that. We're improving on how many people get the first one right, but even just getting the solder paste on and having that experience to get intimate with those 0805 components, being able to get a feel for that is huge, because what we learned in the class, this kind of almost flipped approach to PCB design, this is super valuable. If you just start with KiCad and going for the circuit, they're not yet thinking of these things in the layout. So we really love on the first week this just being super aggressive and fun, and giving them some deadlines, engaging with the makerspace. And so I think once they get the board plugged in, we do a little circuit Python for this. Instead of C, we do have some tutorials in C for the spinning and blinking part, motors and GUI that I won't talk about here. But I like, again, the kind of aggressiveness here that we start with the class, that the students are just diving in deep immediately into these PCBs. So going back to the final project, almost through a few more slides. Thanks, everyone. So going back to this final project deal, let me kind of jump here, is week 3, we actually do a KiCad, more so KiCad tutorial. We have some videos, but we do a walkthrough in class to kind of show them where the B button is and, all these things to walk them through. They get a feel for that, but then in week 4, they really have a good idea of what they need to do for their problem. For solving their problem. This motivates them solidifying it more. I mean, we only have 10 weeks and they need to order parts. We have 17 this quarter, 17 different projects going on, very different problems. So they're all kind of figuring out what sensors, what actuators. When they're designing their PCB, that plays the huge role, right? Which microcontroller are they even going to use? All these things come into play. They're thinking about it in week 4 and week 5. They have peer-to-peer evaluations. We have some phenomenal instructional assistants that are here that know KiCad way better than I do for sure, and they're able to help all the students kind of iterate on their designs. At the end of week 5, halfway through, we submit this to get them manufactured, fabbed, and sent back to us. So we usually get them in week 7 sometime. That turnaround needs to be quick because of the quarter system, but I'm glad logistically I think we figured it out. I think it's a challenging experience for the students and, even just the ordering experience, but it's working really well in our class. I was able to take Andrew, who's from Portland State, who's somewhere in here. He walked over yesterday and checked this out. I wasn't going to show a week 9 picture because usually that's when students are especially stressed and worried about their project. But there were a few in there right then, showing them the PCB, kind of working through it. Pretty cool setup. So that was in the Maker Studio yesterday. And then you hope you have some happy students at the end. They are. The experience is definitely a learning experience, and they get to show off their work with a big demo day at the end. And that demo day, we have these posters. They get to show off how they solved that problem and actually demo it, talk about their different designs. And me trying to go a little quicker is zooming into one of those posters. You can see what they're showing off, right? This is where they've been able to go through this PCB design assembly workflow themselves. They get these stencils themselves and put it all together. They figure out how to solve that problem with these integrated PCBs. And maybe I'll just share here too that, I think here is that this is a great part for ECE. Maybe I could just say here, I wanted to go back to this, what is ECE? Students are all over the place. And actually the PCB is just a great spot to ground the students, whether they're software or hardware. Sometimes the teams will lean one way or the other, but this PCB, the microcontroller, the embedded system, this is where that rubber meets the road, right? They're able to actually connect with one another and maybe veer a little left or right depending on their interests. But I really like that has kind of kept the teams together. They work on it together, but they may shoot again more in the software or maybe even the back end side of things and have a lot of energy there, or maybe more hardware. And maybe they don't even have a microcontroller, right? Maybe they just want to be very much on the hardware end of things. And that still works for there. Maybe I'll just say that what is ECE? It's going to be changing. It's always going to be changing. I think there is certainly a place in our educational system to help them kind of define and work on teams. This makerspace initiative, this engineering, exploring engineering initiative, being able to experience it is a huge deal, right? And we love theory, we love math, and we know it could actually be a lot better when we have these projects kind of complementing in different ways. So I will allow everyone to leave in one moment, but I was really gearing up for some feedback. I wasn't sure where we'd land on time, and I have been so fortunate to be able to talk with you today, with you yesterday, and I hope we can continue those conversations. I think for us, Colin kind of shared that we just kind of started integrating this. It's an iterative process. We're still learning on how to do this well, how to do this better. We're very glad it's happening. It's impacting hundreds and hundreds of students, not just in ECE, across a lot of those Envision Maker Studio classes, and I expect it to continue to influence many classes across the nation. So I look forward to being a part of that. I'll add just another picture. That's always good. I did want to make sure, again, Colin did a good job too, but that we do say thank you maybe I'll start here. We have a lot of phenomenal instructional assistants. I did want to take a moment for these two. I don't know if we would have so aggressively pushed this coming out of COVID if it wasn't for their talents. They are, fortunately or unfortunately, in industry now, doing super well, but their extra energy. I mean, we have unions, so they definitely did not work extra, but they cared so much, right, about this class and this mission. I'd like to say it was from the top down, me and Colin. It wasn't. The students want to do this. We have so much energy to engage with this type of this community PCB design in the classroom, and they were the ones who were pushing KiCad even more than us, right? And I think that was huge. And I will say, though, for sure, KiCad, this community is huge. Access is the biggest thing in education. We need students to have access. They can't, I mean, just to pick on the Mac thing, right? When half of our students have Macs, I'm glad they do, but they need to have access in that way. There's students in so many different groups. They want to go home and work on this. They want to be able to download all their computers. They want to be able to use it after school. They don't want to wait. If they graduate, they don't want to have to figure out how to switch. Being able to use KiCad has been a fuel for our community, and I think it's, again, going to be a fuel for many others. I'd very much like to thank Seth for setting this up and making this happen. Seth, thank you very much for inviting us and letting us be a part of this. Yeah, he deserves certainly a round of applause. And I know, Seth, I know you represent the whole KiCad community, and you work so well with them. It's been so nice engaging with you. I hope to continue that. I hope we can continue to grow as a community and impact so many students in the future. So, again, thank you so much for a great 2 days here, or 3 days, and I hope for many more days in the future. Thanks, everyone. Oh, there's questions. I forgot. I was hoping you guys could get to coffee. Of
Well,
course,
yeah, you can leave. Well,
there
I
is the
could
coffee
actually,
break.
I
but-
could probably speak with
yeah.
both of you
No, thank you. I appreciate
for about
the
8
questions.
hours. So I had the opportunity to kind of be a rogue professor at Penn State. I had a appointment at a research lab, but when the research professors didn't want to teach the hands-on, they would find people in the engineers in the lab to do it. But I really appreciate, somewhat flipping the traditional model of getting hands-on early, because at Penn State, it's like your traditional 2 years. You haven't actually seen anything yet. But so I had the opportunity to kind of like go rogue, and like one of my first experiences was EE300 was like, devices, diodes, transistors, and they were the type of classes too where you might have 300 students across in a big room, and you had to follow curriculum. But the one thing, and I didn't realize the impact on it because some of these students were computer engineering, is you start with a diode, right? There's diode, the physics, there's diode, the PN junction, there's diode, the schematic drawing. And I realized, and there's diode, like the small signal model, that I went back to the lab and I found every diode, big, small, whatever, put on a piece of cardboard and passed it around and said, these are all diodes. And that had like an incredible effect, because that was the first time there was a visceral, tangible feeling that like connecting this model, which really isn't reality, it's like some perception of it, to the real thing. And that like went really far, especially in like a blend where it's like some comp eng and some like electrical. But the other experience I found out I had, kind of going rogue a little bit, I taught an FPGA course.
Redirect you to the question.
Yeah. Well, I should say,
Thank you for sharing.
I just want to give you positive feedback, is that the
appreciate it.
project-based learning, but I found that testing through projects is such a good thing. Like, we didn't do midterms and finals, we did project presentations and proposals. Flipping testing based upon what you're interested in implementing was huge. So I just want to
thank
give
you.
positive feedback. I love the approach.
No, thank
So-
you. I'd like to give you feedback on your feedback.
yeah, okay.
Yeah.
But keep doing it. It's just, don't stop. Like, and if anyone gives you flack, just tell them someone from PA said keep going.
I appreciate it. My comment on that, though, thank you so much for sharing, is that we're fortunate in education. We get to see those experiences daily, right? These students are using these projects in their interviews, and they come back to us and share with us the similar things, right? How valuable these experiences are. So I think we're lucky to hear this type of feedback commonly. I think if you haven't worked too much in the education space, check it out. You know, maybe even hang out with us every once in a while if you'd be willing. We have so many eager students wanting to hear your stories too about your transition into industry and impact that it would really make a big difference for them hearing that early. They are engaging with these projects, and we're trying to do that better. So again, I appreciate the feedback, and I hope Colin and I and all the students here, I hope we could have a lot more of it. So thank you again for that. Thanks. Another question, thanks. Thank you.
I was just curious, as the students are kind of learning electronics and picking up KiCad for the first time, what do you think has been the hardest thing for them to learn? Or the hardest thing to overcome in that process?
Yeah, I mean, I'd like to thank Graham again for documentation related things. That's an important aspect of it. I think what has happened in the last few years has been more of me having difficulties supporting. I think we have such a good group of instructional assistants. In the first class, EC5, it's getting them comfortable with just raising their hand and asking. I think most of the level of questions have been very straightforward. It's in 196 that the diversity really comes out. That their projects are just so all over the place and needing different things. I just had a talk with another Graham about things that I didn't even understand related to MLCC capacitors changing and their capacitance dependent on voltage. And maybe I see some people nodding their heads. I don't know much about that, right? And for me, there's so many little things that start to pop up that are important for us to figure out. And I think this is where again, more feedback if we had time or later when we have chances to talk, what are some of the things we should really be highlighting early? I think the hardest thing for me has been on the logistical side, being able to make sure the students are able to submit this as soon as possible with good reviews. Of course, the assembler will be able to get some feedback to us and we can make some change there, but that also delays the parts coming back to us. And if it delays even a week, sometimes it has, how do you kind of make that still, them be able to have a positive engineering experience and ensure it is a success, and however we want to define that, that could be a little bit more challenging for me. But I think at the low level, we've been grateful for a lot of the documentation has changed recently. So I think that's been kind of a big play. I would say one last thing is one of our IAs, JPAC, made some really nice videos that our EC5 students have been using a lot, and that has changed it. We do they do a pre-lab videos where they learn kind of step by step. They go through it with him, and then they come into class and we do it together as a class. So having kind of multimodal experiential learning is helpful. But yeah, thanks for the question too. Great.
Hi. Wait, can you hear me? Yeah, okay. Sorry. So I'm from Cal Poly Pomona. I'm in my starting my fourth year, and we're running from our, research lab / club, Bronco Space. And we have a program called Blade where students basically make CubeSats. For about 8 months, they do the whole design process. And I'm kind of wondering from an E perspective, if there's a freshman or somebody who has not learned anything about PCB design and is starting completely from scratch, what is kind of your design process or your curriculum process to kind of getting students on board with the idea of actually producing one and being comfortable with that? Because I feel like this year and even last year when I participated in this program, first as a student and then secondly actually running the program, so many students are incredibly reluctant to even start or consider the idea because it seems so overwhelming. What would you recommend as to what are the key steps towards getting them ready to start to actually make something on their own?
Wow, wonderful. Thank you for the question. And yeah, 99.999% of students coming in have not built and assembled their own PCB, right? So it's a super common thing. And there's that reluctance that you spoke to really nicely. That's super common. And not everyone built their own radio coming into EC. A lot of students chose EC because they're good at math, they're good at physics. Maybe they had a mentor that kind of pushed them in that direction. It's not always the build a radio moment, and we're glad to give it to them. Them being empowered of being able just to plug in a jumper wire on day one I know it sounds kind of basic maybe to many of us, we're blinking an LED, but when they blink an LED, and they did that themselves, they knew that line of code, they changed it, they wrote that code that made it blink faster, they figured out that the diode, the LED needed to be flipped over. You know, those things are huge and help with that reluctance. When it comes to PCB design, I think in EC5, we're just happy we do it. I think instructors maybe should have a lower bar if they're in those first year classes. Don't feel like you need to have this whole PCB design curriculum. I feel like here, you know, of course there's a lot of energy and I'm sure criticisms on my approach and technique. And if you looked, you know, at the details, maybe there'd be way more criticisms. But I think the idea, I'm super happy it happens. And I think the students are too, just being forced, you know, to overcome that and plug in that jumper wire or open up KiCad just to download it, to look at a document themselves and try to look at a schematic and turn it into a schematic file and then a board file, and being able to go through that is huge. And it is really rewarding when we can follow up with that actual build, when you get that in your hands and you see even the difference, because breadboards too, you know, we're dealing with audio signals. It's sometimes a little rough. You have all these wires are kind of circled together. Then you get on the PCB, or actually the soldering, it already helps, right? Going from that step, the prototyping with soldering helps. You know, it's a better, more reliable board. It sounds better. And then you get to the PCB and it's a whole nother level. So them going through that progression, it is challenging to fit into a classroom experience. That's why I was kind of talking a lot about time and depths, because there's so many different interests. But I do think every student should just have a chance to try it out and, you know, be forced to try it out, I guess. And then they get to pick. If they want to go more towards software, machine learning, DSP, there are tons of opportunities there, and that's great. But sometimes even they find out 10 years from now that, wow, they're happy that they did do that 10 years ago, and now they're getting back into it, and KiCad will still be there, right? So that's good. Happy about that. Seth talked about the bus factor yesterday. So.
Okay, if people have further questions for Karcher will be out at the break with the coffee and the snacks. So please, we're about, what are we at? We're about 15 minutes behind schedule, so we will reconvene at 11:25 for the at mid-morning talks.
Thank you so much again, everyone. Thank you.
Ceramic capacitors. Okay? They came in and they promoted them and they told us, you know, typical ceramic cap, low value may have 10 or 20 layers in it, but these new ones had 200 or 300 layers in them. So you could have an 805 or 603 that has 300 layers. Okay, so we learned then that there was a voltage sensitivity, or voltage coefficient, and pressed voltage affects the value of the capacitor. It's a piezoelectric device. So they do change.
They change shape.
They do indeed change. So we could have a 5 volt 10 microfarad capacitor. You run it at 3.3 volts, you don't get 10 microfarads, you get like 2.
Yeah,
we didn't need it. Yeah, but it was that fire really helped the ceramic capacitors because now they're ubiquitous. You know, they're everywhere. Before that, the large value parts are always tantalums. But yeah, there is a voltage coefficient. It very seldom shows up on the data sheets, and some dielectrics are more prone to it than others, and you kind of have to dig for it in some of the data sheets. Some of it's almost negligible. Other ones, it is there, and you need to be aware of it.
Where in Japan was that again?
It was somewhere in Japan.
Or what kind of?
It was a tantalum.
Okay, tantalum. Just tantalum.
Like the main factory that produced the tantalum or the tantalum capacitors burned down. You know, big opportunity. I work a lot on frequency control, synthesizers and references and things. So there's a ASIC company or a semiconductor company in Japan called AKM, They make a lot of audio chips and things. They also made a temperature compensation ASIC for TCXO oscillators, temperature controlled oscillator. That burned down about 5 years ago.
Wow.
Okay. Almost
What we learned there.
almost everybody that makes quartz TCXOs, small TCXOs, were dependent on that factory. Okay. The only one that did not, that makes small TCXOs, was Raycon, and they're in New Zealand. They bought CMAC in the UK. They have their own proprietary Pluto ASIC. Everybody else, Vectron, you name it, they were all stuck with nothing. Okay, now the MEMS oscillators made by SciTime, they were in the catbird seat, and now their market expanded immensely. So almost everybody now is shifting over to MEMS, and quartz is like on the outs, kind of like, except for special applications. Kind of like the tantalum capacitors, you know, they lost market share. So it was fortuitous for those guys that were sitting there waiting when those fires happened, but
Yeah, you got to be aware of these fires. So you don't want to have start your electronics supplying company in San Diego, probably.
fire suppression system up to date and working, right?
Thanks, Scott.
all the food and other stuff from the other house in the mini, and I had to leave. I was running late. So, what else is in there? You know, that means the vest and the helmet. Where are you supposed to be going? Except I've already paid for parking for the whole day for the Fusion. You could. I'm in La Jolla off Genesee. So you would probably pretty much be driving past. Did Delta take all the food and other stuff out of the Mini yet?
No, not yet. I just asked him to help me do that. So we will take that stuff out. That's why I didn't take his stuff out.
I want both of you guys to stop leaving things in the cars. It's not good to leave anything in cars.
I haven't left anything in the cars.
Well, but you did. You left the stuff you need today in the car.
And like gas, yes.
Seth, don't leave your other stuff in the car. The car technically belongs to me, and you don't know when I might need it. The same goes for the Mini Delta. Don't leave things in the cars. Both of you do it all the time. It's a bad habit. It's laziness. Take your things out of it when you get out of it when you get home. Meanwhile, if you want to come by,
I'm gonna have to.
I think I can tell you where it is, but I would probably have to meet you there because I think we only have one key right now and it's in my pocket. So just let me know. Do you know roughly what time you'd be going down?
The address is right here, calculate that.
It's well, it's in a car park at UCSD. I'll tell you the pantry where it should have been. Hang on a sec. I'm just concentrating on making a pin to send you. There, I just sent you a pin of exactly where the car is.
Okay. Well, I need to leave. So I calculated to get to where I'm going by 1 o'clock. I should be leaving at any time to go. I have a little bit just
You need some buffer, yes.
I need to leave in like 20 minutes, which means we'll be there in like 45 minutes.
Yeah, right about when I'll be probably breaking for lunch or something, I guess.
Are you the next speaker?
Yeah, I am.
I just sent it to you.
Are you plugged in already?
Make sure you
I believe so.
Are you in HDMI or USB-C?
In the HDMI.
Okay, let me check if ever.
Okay.
I extended the screen so I could have some of my own notes up without showing everything to everybody.
Okay. I'll meet you at the car then, or as soon as I can. I have to rely on a shuttle bus to take me from where I am over there, and those run every 10 minutes.
Well, remember, I also know the code to the door, so you
Well,
won't have to need to.
okay, good. That's even better. But without the key, you'll just have to press the lock from the inside before you leave it again. Okay. All right. Cool. Yes, Seth. Oh, just call me or whatever if there's any issue. Okay. Drive safe. See you.
I feel your pain. My daughter just got her driver's license. We have to set her straight about whose car is whose. Zero are hers.
Yeah. I have a 21 and 19-year-old. And they both tend to forget that the cars don't belong to them.
Yeah. Which one of these buttons is going to be okay? It was lovely having my car insurance price more than double.
Oh my gosh, mine triple.
It's just,
forward to it.
I hope so. We'll see. We'll see if you're still happy with it after.
Oh, I'm sure it will be. Although you see, I've heard it all already.
Yeah, maybe bits and pieces. I've tried to restrain myself.
Haven't heard the properly strung together version.
Yeah. You know, I'm a decent speaker. I believe that like you should really know what you're talking about, because then you end up sounding like you were a good speaker.
You got to know the material, otherwise you shouldn't be there.
But on the other hand, I'm not. I don't like to get too hung up on like writing the whole thing out and memorizing the script, right?
Okay, ladies and gentlemen, welcome back to, I hope everyone has well caffeinated and enjoyed some of the Southern California sunshine. And we are ready for our second session of talks this morning. Next up is Jason Goldstein. He is a physicist, computer scientist, and electrical engineer with over 40 years of experience in computing. He's designed dozens, if not hundreds, of circuit boards with nearly every CAD tool in the marketplace. And given all of that experience, he has come here to tell us why he has chosen KiCad for his new company, NCX. So please give a warm welcome to Jason Goldstein.
Thanks to everyone. I want to give a particular shout out before I get started to my wife, who is probably streaming this at home. We are such great partners, and we rely on each other. And when I said, "Hey, I think I'm going to put in to give a talk, and I'm going to disappear for a few days right at the last week of school," and she said, "Great, go, do it." And if my kids are live streaming this, put down your phone, you're in school. You could watch it later. All right. I was going to title this talk something involving Altium and the horses they rode in on. I decided that not to do that, in part because I like horses and they don't deserve to have their reputation tarnished by being associated with Altium. After a brief intro to me and to NCX, I'll talk about how we came to pick Altium, because it's important to know why that even happened to start with, because I was the decider. I picked, and I thoroughly regret that decision. And then I'll talk about why we moved to KiCad. And then I'll change the tone dramatically, and I'm going to talk a little bit about how we deal with library management, because while you can just run the install and you can get the standard libraries, it's not quite clear exactly how you go about dealing with libraries that are yours internally that you can't reveal for privacy reasons or security reasons. And you don't want to be leaking what you're building indirectly by releasing your components into a public library. You may be able to do that after you've done loads of projects, and you might do a big dump of everything so no one could quite tell exactly what's going on. And then I'm also going to talk about output generation and how we're using the job sets now. This is a critical feature for me, and it works mostly. I'm glad to have in the audience the people who can do some things about that. Some of these things are small, and they'll go away. My goal is one-click output generation. Tons of files, one click, consistent, and ready for manufacture. All right. So the first thing is first. Oh, I got to come over to the other. Give the focus over here. All right. Why should you listen to me, right? This is the first thing. I'm about to tell you that you should dump a very expensive tool that perhaps your company is very committed to, that you have a lot of intellectual property intertwined with it. So I thought I'd let you know a little bit about myself and where I came from, my origin story. My father was the senior registrar for the graduate school for the City University of New York. And as you can imagine, as computing is just starting to happen, keeping track of classrooms, students, grades, courses, transcripts, this is like a really straightforward and obvious use of computing. And so even though he has a degree, or had, may he rest in peace, he had a degree in geography. He was a very early user of computing. And so, even as a kid, I would have to go to school with him school would be closed, there would be no one to watch me. I'd go into work with him, and he would go on his teletype, and he'd print out giant, Snoopy was one of them, and I would color for hours on his floor under his desk. And we had in our elementary school, we had a single Apple IIe that for an hour a week I got to program with a partner. We couldn't save anything, so you had to retype your program in every time. And I programmed in Logo, and we made drawings. And my father saw how excited I was about this, and he managed to find a class at Manhattan College for kids. And so I started to learn BASIC on a Commodore PET. And along the way, I'm playing next door with my buddy, and his father comes home. His father owned 3 pharmacies, and they sold Timex watches. And one quarter, he had a great quarter and sold a mess of watches, and Timex sent him a Sinclair. And so he comes home, and he tosses this Sinclair. He's exhausted, and he throws this thing at us, tosses it on the bed, and he says, I don't know what to do with this. Here, you have it. And both of us have been in computing ever since. I have told him how grateful. He doesn't even remember doing it. He was so tired. And so these were things that really helped. Now, in the mid-'80s, growing up in Yonkers, New York, the city, thanks to redlining and city policies on public housing, they utterly segregated the entire city. And Judge Sands put an end to that in 1985, which was right before I entered high school. And so they wanted to try and avoid the violence that occurred up in Boston when the schools were integrated. And so to get people to go to different schools willingly and to get on a school bus and cross the city, they created programs, magnet programs they called them. I see this term around now. It's not always used the same way. But they literally wanted to attract a student to get on a bus and go into a neighborhood, some of them not such great shape, let's just say, and be willing to do that. And so I don't know how this happened, but I am so grateful to Miss O'Rourke, Mr. Tooley, and Mr. Healy, because when I graduated high school from the computer science magnet program in 1989, I could program in Pascal, Fortran, COBOL, and I did a little bit of assembly language. And there was no IT staff, so we had rooms of IBM PCs, and we all learned how to fix them, which kept me employed when I got to college. This was just fantastic. When everybody else was making minimum wage, I was making like triple. So, all right, let me get back to the PowerPoint so I can move. Of course, that just did that. Got to find the little square all the way in the corner. There we go. All right. So, I founded 4 businesses. The first one of them was just a sole proprietorship. I'd been making telecommunications supercomputers that were all used to birth audio and video and data conferencing. Nothing has changed. 35 years, every call still starts off with, I can't hear you, can you hear me? Nothing has changed. And so we built DSP farms. And we had some really talented contractors at the company that I landed in that had designed the first one. I learned from them. And my degree is in physics. I took 2 electronics classes and then realized that I like to touch things. And that's why I didn't go into computer science when I got to Carnegie Mellon to start with. Something just didn't feel quite right, even though I was pretty talented at programming. And so after I spent a little stint there, I decided to leave there and form my own little contracting business. My goal was to start up. So I was mostly working with a bunch of people that I knew, and we were all trying to do it better than Cisco. Some were more successful than others. And eventually, I formed a company called Maygold, where we were going to basically utilize motorized blinds in tall buildings to run ads down the front of them, so that you can without bothering people. You turn all the lights on in the building and you open and close the blinds and you can make dot matrixy kind of images down the front. And we were just getting that business off the ground when I had a tremendous opportunity and I ended up taking it to go out to Seattle and work on one of Bill G's pet projects. And so I took all that knowledge of the DSP farms and I architected the machine vision system for the hardware for the machine vision system for the first Surface table. And I didn't like working at Microsoft so much, so I split off. Eventually they became a very good customer of mine. And that was where I formed Austin and play on my name, for those of you who know the periodic table. And I've done just a number of projects for them. First for the Applied Sciences group, which is not Microsoft Research. They're their own beast. And there I built force-sensitive touch sensors. I built 256 LEDs in a strip that run along a perfectly designed and highly calculated piece of plastic in the background. And with it, you could steer the beam of light coming through an LCD display. So you run the display at 240 or 480 hertz, and you could alternate the images you're showing, and you can basically project out to your 2 different eyes or to 4 different people. I mean, imagine playing a car game where everyone's playing and seeing their own full HD screen. It is a cool technology. It's super expensive. It's never going to be sold. And so I eventually I moved on, and I did some work for Oculus. I did work with Magic Leap. I eventually landed a gig with the hardware lab at Microsoft Research. You got like well over 1,000 computer scientists. Most of them don't know how to make hardware, but they have great ideas for hardware. And so rather than have to go and negotiate individual contracts with each company for each project and then deal with change orders and all of that sort of stuff, they have one group that's like it's a contract engineering firm with no contracts. And they operate on the first floor because of all the heavy machinery that's installed there. You don't want to shake the building. And it's part makerspace and part, like say, contract engineering service bureau. And so I worked there for several years picking up overflow work when the students would come in. They bring in hundreds of interns every summer. Sometimes it would be very hardware heavy, and there was no way the staff in the hardware lab could keep up with it. And so I was taking these overflow projects. This was fantastic. I have worked on so many varied things. I didn't just like land in an industry and kept working and had super depth, got wide breadth. And I've done beamforming, microphones, speaker arrays. I built a 64 microphone sphere, which we then put a 360-degree camera on, and we took it down to the middle of Pike Place Market, and we set it down right in the middle of literally in the middle of the street, and we recorded a bunch of stuff, and then you can come back and you can put on a helmet with headphones, and when you turn, the sound moves too, right? So if there's a siren over there, you hear it over there, and if you turn like this, it's still over there. It's really neat stuff. Gosh, we did all kinds of things from little piecing together Arduinos and whatever to build little sensors to I built a device there that combined a depth camera, thermal cameras, video cameras, audio, everything you could think of, and then we strapped this giant thing on your chest because it was to collect the data, right? The goal of research is to answer questions as fast as you can so you can publish your papers, right? And the work for Magic Leap, they were a great customer. They were doing some super, really advanced and great ideas on augmented reality displays. All that got upended with COVID, right? And so I also, through meeting some people at Microsoft, they weren't super excited to Microsoft themselves to bring out a product that was medical related. There's a lot of risk with a medical device is proportional to how much money you have. If you're a little company and you don't have a ton of money, then you might still screw up and you might still hurt someone and you might still have to try and make them whole. But if you're a big company with big money, then there's a lot more risk than ever the returns. So we spun off this little company, Evergreen Circuits, and with a couple of partners, I built the hardware. And so if you can't move, but you can move your eyes, you can drive your wheelchair. Super rewarding, didn't turn out as profitable as I'd hoped. All these businesses were upended at COVID. And so in 2001, my wife came out we had a lovely 7-acre lot. I miss the things I had there more than I think I miss the property. I had a 2,000 square foot workshop to myself, 22-foot ceilings, 40 by 50. The only body bothering me was my goats and the sheep who would occasionally butt heads and shake the whole place. And, you listen to the chickens from the neighbor. And it was a great place to set up for contract work. I just lay out one table after another. Customer came by, I can just throw a sheet right over the top of the other people's work, and I really loved living there. But my wife came out and she said, and this is, I'm bringing this up because this is relevant to how we've gone from Altium to KiCad. Okay, my wife came out and said to me, "Why are we here?" And within 15 minutes, the question was, "Where are we going?" Okay. And 100 days later, the house had been utterly polished, the floors sanded, repainted, and we were in North Carolina in Chapel Hill in a new house. Okay, 100 days. If you're going to do something, do it. My wife is a big influence on me for that. She's great at deciding rather than hemming and hawing. I can both. I'm a professional hemmer and hawer, no doubt. So, before I move on to this slide, I'm going to tell you some advice that I tell all my customers. I tell all of them. Trust your experts. You hire them for a reason. When your expert's saying, well, maybe you could ignore them. But when they're banging their shoe on the table like Khrushchev, and I'm dating myself a little bit, right? When they're banging their shoe on the table, listen. So when we landed in North Carolina, I had promised my wife I wouldn't start another business myself. So I found at that point, I guess I was employee 6 at the startup. And I was glad it was just really refreshing to find a place with founders and funding and exclusive, hard to construct, hard to compete with technologies. And so it was really just a great spot for me to land. NCX makes innovative X-ray tubes. There has been almost no change in the design of an X-ray tube since 1895. You heat a piece of tungsten on one end of an evacuated chamber. It's got to be ultra high vacuum. There can't be any particles in there. And you heat it up so hot that the electrons flowing in there that you're heating it with, they actually they leave the edge of the metal. They're not far, but they leave the edge of the metal. So if you put a high voltage across the way on an anode, you could rip those right off. When the electrons hit on the other side, they are going to return to ground because you got to make all your electrons go to ground. And they got to slow down. And when they slow down, they let go what's called Bremsstrahlung radiation. And it is a broad-based radiation. It's X-rays. You have to hit tungsten or rhenium. But you don't need a lot of that. So you attach that to a giant piece of copper and so that it doesn't overheat. And so the big difference is that if you have a traditional tube, you have to heat it up and cool it down. It takes a moment to heat up, takes a moment to cool down. You can't put two filaments next to one another because if you heat one, the other one will start to drip out electrons also. So it's hard to do basically tomography, right? Computer-aided tomography with a traditional X-ray tube. So what they do is they take one tube and they spin this thing on this multi-100-pound gantry. And if you ever watch a YouTube video of one of these with the cover off, you may never want to get in one again. It is amazing how much stuff is in there and how fast it's moving. And, just like you have two eyes and you can sense depth, right? You can, and I did this at Microsoft, you can make a depth sensor where you have two cameras, or one camera and two lights. You flash the one light in the infrared, you flash the other in the infrared, assuming that you're not standing outside where there's a lot of infrared, and you can piece together those two images and you can get depth. So with our devices, we can stick them extremely close together. They're a current-based device. They turn them on immediately. They're made out of carbon nanotubes that are little pipes that are 3 to 5 atoms thick. This is our special sauce. This is what NCX is on the map for, is how to make those nanotubes, how to attach them to the substrate. Everything else is pretty much the same. The biggest difference is now you've got something that resembles an LED. So it's the analogy from an incandescent bulb to an LED is really similar. And so these guys were super fortunate when I got there, and they said, we want to do massive arrays of current-based things that are pulsed. And I'm like, I made a 3D TV with 256 of these things. And so, let's see here. So that there on the right is my creation there. That was all those boards in there. There's 4 custom circuit boards. That box, we call it the MBCU, the multi-beam control unit, very originally named. That one does 64 of these devices. Unlike an LED, which you might do like that TV, was 256 3-amp LEDs. The heat sink on that was something else. And you only turn on like 20 at a time. And they're running maybe 3.5 to 4, maybe 3.8 volts, something like that. Our tubes are more like typically 20 milliamps. We go up to about 100. At a certain point, you're bombarding the tungsten with cathode with so many electrons per unit area that you start to make a drill. And so you'll obliterate the surface. And so there is a trade-off that affects all of the manufacturer. How small is your focus spot? The smaller the dot that you make on that target, the clearer, the higher the resolution is probably the best way of the image that you're going to make. If you have a big giant dot, you can get a lot more X-rays, but your image is going to be reduced in resolution proportionately. And there is absolutely some limits. Of course, every single customer asks us for something that, the laws of physics apply to us too, right? Not. So I got there, and I was the first electrical engineer. I am the electrical engineering department. I am the software development department. We have another physicist who does some computational work with Python. But this is a real-time system. There's a timing board based on a PSOC, which I love, and I wish Cypress had supported more, or now Infineon, or whoever owns them this week. I wish they kept those around. They're really lovely parts. I programmed some really nice custom stuff in that to get our timing unit to be able to produce all these pulses, to pick which one of the 64 that we're going to use. And then I have another board, which is the current sink. And that is the thing we generally say we have to regulate current. We're making current pulses, not voltage pulses. And in order to get the currents we need, we're typically between 500 and 2,500 volts, right? So this is a tricky game. Like the highest voltage FETs out there right now are 3,500 volts. If you have any inductive kickback or anything like that, you got to leave yourself a little leeway. Typically, our tubes are rated to run up to the 2,000 volt limits because the cathodes do decay over time, and they change with temperature, and each one's got a little different. And so you have to regulate that current. And I wrote all the software for the 2 different processors, as well as all this software on the PC. I've got a Python, multi-threaded Python program. I hope the GIL is thoroughly dead. For those of you who know what the global interlock in Python, I hope it dies a fast death this October with the next release of Python. It lets us visualize everything going on. We record everything, because if you have a failure at these kinds of voltages, there's damage, and you need to know what happened. You really need to know what happened. You need to, and this is going to eventually be, hitting human beings with X-rays. So you need to know that you have put out the exact amount of current that you think, that you're producing the exact amount of dose, which is proportional to the number of electrons that flow, and so you want to record everything. And in addition, we want to characterize our devices so that we can bring them through the manufacturing line. This is primarily a tool for us to use to produce the X-ray tubes. We are a manufacturing company, right? And so it's totally scalable. One of the holy grails of this technology is CAT scans with no moving parts. So if you're in an ideal world, you'd probably have one emitter per degree, 360 degrees, it's several hundred emitters. This absolutely will scale up on the software side on the PC. The hardware can be all interconnected to keep the timing as fast as you can. And we'd love to have a customer who would be willing to pay for us to build it. We are more focused on smaller things, like for dental x-rays is a really great advantage. There's some great studies that were done on early devices at UNC in Chapel Hill in conjunction with Duke. I guess I'm a little embarrassed. I'm not supposed to say Duke in a name if you live in Chapel Hill. And quite the rivalry, but they did some great work with dental x-rays where you can see a 3D image of your tooth. I mean, we've all gone to the dentist, and the dentist is like pointing at this blurry image because your tooth is irregularly shaped and the whole thing's been flattened out, and he's going, clearly you've got a cavity. And you're looking at it, how, right? With this, you see the holes. In the study, they found 38% more cavities, right, this is money for the dentists. And also, I've experienced this, unfortunately myself. You get a cavity in between your teeth, and sometimes it's not obvious which tooth the hole was in. And then they go and they drill a hole in the tooth, and it's not the right tooth. And then they have to fill that, first they have to tell you that, right? Get over the embarrassment, tell you that. Then they fill that tooth, they drill the other tooth, they bill for one tooth, right? This is going on all day long, all across the world. Dentists accidentally, for these kinds of tricky things. But you can take that tooth in the image and you could rotate it around and you could really see what's going on. So our technologies are relevant to anything that does x-rays now, from searching for, scanning a backpack left on the side of a road by the parade, right? To dental x-rays, to scanning your suitcases going through luggage. Everywhere x-rays are relevant. All that technology and all the advancement that's occurred there in computing and visualization, all that's utterly the same. And so, but what's not the same is the ability to stick 7 emitters in a device, yay big, with a 14 millimeter pitch, and produce these images in very rapidly with no wasted dosage on the way up and down, so that you reduce the dosage that's being experienced by the patient. Doesn't matter to your luggage, but it matters to people. And this is what NCX does. I've been there, it'll be, I guess, about 3.5 years. I've done 20 boards, 14 with Altium. Some of these were just revisions of the same thing. Some of these were super simple little interface boards with Zener diodes to protect us from shocks that are right up on top of the tubes versus this box, which is way down along lots of cabling, right? And others of them are super complex. Like the current sync has a 480 megahertz processor on there with a ton of RAM. It sits... Ben Franklin got the sign on the electrons wrong. And in electrical engineering, almost nobody cares. But when you're actually trying to shoot electrons at stuff, you care. And so we're at negative voltages. And so I have to float the whole circuit we generally float it at minus 2,000 volts and use a simple low side current sink to regulate that and produce the pulses. And this has got megahertz. We use the ST-H743, which has 3 2.5 megahertz 16-bit ADCs on there. It is the cheapest way to get high-speed, high-resolution ADCs out there for sure. But you got a lot of code to come with that, right? One of the other speakers was talking about how to simplify down your boards to teach new students. My God, the H7 is a 3,500-page document. 3,500 pages. It goes on and on and on and on. So I picked Altium, right? I was the first EE. No one else there knows this stuff. And I said to myself, all right, well, I don't want to play around. We have some funding. I'm going to pay to get a tool that I know and I trust, that I've used a lot. It was a pretty good value proposition back in the day, right? One tier, one price, all in. When I started stuff, you would get your schematic capture for $6,000, your layout for $12,000, right? You pay 25% per year for support after the first year, right, per seat. And so your engineers doing the schematics, you didn't want to buy them a license for the layout tool, because then you're paying for that tool to sit and rot for the most part. So you use external service bureaus to do your layout. And I always would go and sit with my bureau and do all the placement with them, right? But you can't do the placement at the same time as you're doing the schematic, which is kind of important because it can be iterative. You start doing the placement and then you realize, oh, geez, that resistor is way bigger than the part it's next to. Or, oh, geez, I got to stick this right over here or right over there, and there's just not as much space as I thought, right? And something Altium does a fairly good job with is dealing with multi-channels. When you have a highly repetitive circuit board, and I thought, oh my gosh, what if I have to do 16 or 24 of these on a board? We eventually chose 8 so that we could have little modules and we can scale in groups of 8. But what if I have to do 24? Oh my God, I'm going to have to lay out the same thing 24 times. I don't want to do it. And while I had seen that there was, I used KiCad for Evergreen because we were a little company with no money. And it worked. It was a simple board, and there was no problem. But there was some scripts to do multi-channel designs, but it wasn't perfect. Altium does a good job with that. I can't say they do a great job with it because you can't number your room, your channel from 0. It must start with 1. What? It must start with 1. And that is a flaw. I don't understand exactly how that happened with them. You know, I'd have to get into the code, which is a problem, right? And they also have their library's really extensive, and it's very easy to just search, find a part, grab it and pull it into your design. You can't always find everything, but you find most everything fairly easily. There are a lot of inconsistencies. That thing's been around a long time. It's not really been scrubbed great. Also, Altium does something that I don't like, where, it's like 1 resistor per part. And I'm like, no. There's a resistor, and then you put whatever value you need on it later. And so you might discover that you go and you grab the red LED, and then you grab the green LED, both from the same vendor. They vary with 1 letter in their part number. And they should be exactly the same, but the footprints are different because one was made by one guy and the other was made by somebody else years later, right? And so, I mean, it's all right. The electrons don't care how pretty your board are, right? I also thought to myself, and this is an important piece, right? And this is partly why I'm here, is because KiCad has to become popular for me to recruit people who already know KiCad. If I find someone with 20 years experience who's used 3 CAD tools before, I'll train them to use KiCad in a week, right? But what happens when you don't have money for a principal engineer? You only have money for someone more junior. Or what if the work you have is you just don't have work that will keep a principal engineer interested? And someone who's more junior is going to be excited for this high-tech stuff. You have to have a talent pool. And I thought, all right, well, these are the tick boxes. These are the important things. Altium does it. Let's just jump in. Now, I have to tell you, everything I'm about to say, I've said to Altium directly. I am angry at them. I have said it directly. When I canceled our subscription, I sent an email to the CEO of Renaissance. Now, this is my humble opinion. I think they got ripped off. And I think they are going to write down nearly the entirety of their investment in Altium after they devastate their customer base. Okay? My opinion. I hold no stock in them for good reason. I like Renaissance's parts, by the way. They have some very nice parts. And unlike the H7, their equivalent processor has one kind of timer, not 8 kinds of timers. Right? They're all 32-bit. They're all exactly the same. They're easy to work with. There's a lot to say for this company, but boy, not for Altium. If they had bought Altium and showed the CEO and the head of support and the head of software development the door, I might still be a customer, and I wouldn't be talking to you now. Yeah. So let's see here. Support back in the day was great. You guaranteed an answer rapidly. Then it was, well, only during the week. Okay. And then it was like, well, we'll get back to you in a day or so. I sent in a support request for a problem I was having and got 0 response for 6 weeks. 6 weeks. What was I paying for? They push you very hard to ask your questions first in the forum. Well, I don't want to leak my designs to the forum, right? I don't want to ask all my questions in public. Some of them I don't mind, but others are going to really have to reveal what's going on. Maybe I'm running into a bug. I got a problem in an output generator. I'm not going to go put my Gerbers up there and say, hey, can you open this up and tell me why it's broke? There's virtually no way to request a new feature there in private. The support staff is not equipped for that. They go out to our publicly thing, put your issue request on there, and do it in public, and make sure you give everyone that you also like a thumbs up so that we can ignore those whatsoever and do whatever the hell we want because we really don't care about you. They are fixated on getting your intellectual property locked up with them. Now, I'm not the one saying this. They are. If you read the documentation that they published to their investors on their acquisition, they said flat out, our customers are sticky. What I heard was, I'm stuck. I'm from New York City. I'm not sticking with nothing I don't want to. The software's riddled with bugs. It crashes 1 to 3 times a week. It is astonishing to me that a piece of software that old could crash that often. There is numerous inconsistencies in the UI. If you go to draw a room, which is a polygon, and then you go to draw a zone, which is a polygon, and you go to draw, there's 4 ways you can draw a polygon. 4 different ways you're drawing a polygon. The rooms one doesn't work worth a squat. If you start out with a square and then you decide you really want it to be shaped like a B or a P, oh no, you can't add any more points to it. I've reported this to them numerous times. I've told them if you don't fix these things, I'm not renewing. They ignore them. It is not my job as the electrical engineer paying several $100s a month to also be the software development engineer for Altium. It's not my job to also be the guy who is providing my own support. This is not right. That's the whole point of someone like me who's a user who is looking for this value add. I'm paying good money for a reason. There's a bug in the file output generation has been there for years. The whole point of this software is to generate the files. I got bit by said bug. I reported it. It was okay. I could work around it. Years. It's now in 2025. It's a terrible value proposition. There's 3 tiers. There's 3 prices, and they haven't added a single feature in the bottom end tier in well over a decade. There is nothing new and useful that will help you make a circuit board that has been added in at least a decade. You get less value for more money. Everything out of them is, hey, it's in our other tier. Enough. They will not get one more shiny penny from us. Not one more. So then the question is, why KiCad? Right? Because I have money. I could have gone to Mentor or Cadence or whoever. I could have bought something else. And, well, I used it in the past at Evergreen, and I was really impressed with it. It had some things that was missing, but in version 6, this was a viable tool. I was quite successful with that. I can say now, especially with the things added in version 9, there is not a single circuit board that I've worked on in my entire career that KiCad can't make. I've done a 138-page board, cell phone, this big, okay? We used every PCB manufacturing process that you could possibly think of. Tiny vias, any layer interstitial vias, so we had no through-hole vias. Everything's micro vias the whole way, that built the whole stack up one at a time. 1,500 components from 104 different vendors, right? I'm telling you, you can make that board in KiCad. I don't want to go all the way back to the beginning of my career, but let's just go back to, say, 2005, right? In 2005, I was not sitting around saying to myself, oh, if only the schematic capture could do this, or if only the layout can do that. The tools were fine. We were paying 20 grand a year. It was fine. They got the job done. KiCad is far better than everything that was sold back then. Now, everything that was sold back then is improved, except Altium. Right? But at this point, you got to customize rules. They work great. We do high voltages. We got all kinds of complicated rules. I got high voltages on the same board as tight pin pitches on a ball grid array because we couldn't get the part in a bigger package, right? Things went sideways for a while. If you've been in this industry more than 3 years, and you know the pain that happened after COVID. And it can do multi-channel designs. It's got output jobs now, so I can get my files pretty rapidly and consistently. When something doesn't work, I can go look at the code and discover, well, can I work around it? Maybe if I do something different, it'll be fine. Like this bug that I reported to Altium, the output generation, if you literally chose not a true type font, the problem went away, right? But how was I to know that? How do I know maybe it's just so broke, you're stopped? Okay, fine, I'll deal, right? But at least it gives me a chance to look at the code if I want to. Maybe I discover, oh, geez, I'm trying to use it in a way that's not the way the developers ever thought anyone would ever use it. And if I just use a different steps, I'll get the outcome I want. I love that the file formats are human readable. Because even from simple things that I do with KiCad, like I got multiple variations of the same X-ray tube, but the 125,000 volt tube has one pitch between the pins, and same number of pins, different radius for the 180,000 volt tube. And so I could just grab the file, I opened it up in Notepad++, I did a search and replace, I renamed everything, and bam, I got an exact duplicate of exactly what I changed, and then I opened it up and I modified the radius. And again, thanks to the output jobs, click, 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 which I'll get to later. There's 4 clicks. And you get what you want. And so, look, Altium's constantly pushing me to buy the Vault. Now, we buy a Vault from, our Mechis really love the Vault from Autodesk. They use Inventa. and they love it. And I have to say, it's pretty good. You can like just mark it up like you got a pen on a piece of paper. You could orient the thing the way you want it, and you go move this 20 millimeters to the left with an arrow, and then it's recorded so that not just that you get it fixed, but there's a record of everything that you've done. But, for the EE tools, why do you need a vault? You got Git. It's free. And, speaking of free, it's free. KiCad's free. Now, I'm going to tell you in a bit that, we're going to pay. Seth's going to land another customer. I came here in part to meet these guys and see if I was going to really get the kind of support I would want from paid support, because I need someone who can take my bugs with an NDA and recreate a new project that can be put in the public to report the bug so that it can get fixed. That's probably the most critical thing I want paid support for, because I don't want to be the QA department for my tools. I have another job. In fact, like I say, I'm the electrical engineer, the computer scientist. I have to do all the IT because I just couldn't take it anymore. And right, so I wear a lot of hats, and plus, as much as when I graduated from Carnegie Mellon, a couple months before I graduated, I went over to meet with my advisor, and I said, I just got an 18th percentile on the GRE. I don't really understand much of what you're trying to teach me about all this quantum mechanics. And it turns out much of their theories were wrong that they were trying to teach us, and so that's why we were confused. It's because these theories don't really work. We now know all these things later. And I said, my hopes and dreams of being a particle physicist are gone. And oh my God, I'm a particle physicist now. It's super low energy. It's funny to be here at KiCad, right? You got CERN, right? They're doing stuff at the teravolts, and we were only getting up to kilovolts. But I am absolutely shooting electrons at stuff and seeing what comes out. I could never have predicted that back then. I am amazed that I have come full circle. So we got to migrate. Migrate? What migrate? I'm not migrating. I got my existing boards. They work. One of them's got, God dang it, I crisscrossed my hardware handshaking on the UART, and there's isolators involved, and so you can't just use the software to flip the pins around. And we're going to survive because I want to upgrade that processor anyway to a dual core and with a wider memory bus and a different package because COVID is over and I can get parts in more packages. So I just ripped the Band-Aid off. I just said, that's it. I polished off all the latest revisions, corrected everything I could. The hardware handshaking resulted in a big upgrade. It wasn't just a little repair. We were really adding some bandwidth there, and so we went from 3 megabit to 18 megabit, and without hardware handshaking, you're just done. Really, even at a megabit, you really need hardware handshaking on your UART. We froze all the existing Altium boards. What are you trying to do? Oh, time. Okay. Oh, I'm over.
You're 10 minutes over right now.
I'm over. Well, you started me late, okay? You started me late, okay? So this is the big thing, right? At the bottom, I got to have support. You got to have paid support. Someone's got to be working, supporting KiCad for money because otherwise you can't maintain your privacy. So, I wanted to change the tone. I will skip through the next sections pretty quickly because I am over time and I'm eating into lunch. Some of the things I want to talk about are going to be gone quick, right? So the first thing is library management. How do we deal with that? Well, I replicated the same idea for our internal libraries as I did as what you get from KiCad. I don't download the libraries. Here's a feature request. I wish we didn't have to download the libraries every time you download a version. I appreciate having an official released version, but I want to pick up the libraries regularly. And so I structured them the same, and then I made a custom script. It's nothing too fancy. I started out creating my directory names like ncx internal.ncx because I thought my script would be super simple, and I would just use that little dot whatever as a prefix on all the variable names. But it turns out that's not what you want to do. You end up with a JSON file with a handful of things that you want to do. because you want to be able to move your directories around. Different users maybe have different drives or whatever. And I just followed the same thing that everybody else did. Or I say what the KiCad team did. I started with a prefix, but I'm realizing now, as I'm using this a little bit, that I really want a postfix, because when you go in to pull up a part in the library and they all come down, if you have a prefix, your stuff all ends up at the end, which maybe is desirable. But if you do a postfix, then if you have an MCU and an MCU, because I want to copy the directory structure the same, right? I don't believe in hidden pins. I think they're super, super, super dangerous. If you have a pin on your part, you should put them on your schematic. Can you imagine sitting on a stand in front of a jury and a judge and them saying, there's been property damaged and people injured? Why did you leave that pin off your schematic? And you say, oh, it was pretty. I wanted my schematic to be pretty. I cannot imagine that. But I want to harness all these libraries. So I start with the part, and I just pull off all those ground pins and whatever, and I add them on one extra thing. So I want to have almost the same structure as everything. So I want to just update. I'm sure within a couple of weeks I will have updated that script to postfix. I will update my few boards so that they now are well, I may not even have to because of the environment variables. If I change the environment variables, everything should move. Maybe some of the symbols need a little tweak. I have not automated adding this into. I get 3 output files, right? The footprint symbol library, the symbol footprint table, the symbol table, and another file which just got these environment variables. I copy those into the configuration file, wherever that may land on Windows. It's buried, right? At some point, if I had some staff to write some software for me, it would just put those right in there. But I don't want to get into opening that file, not ruining it. And what if there's already got the stuff in there? How do you deal with overwriting? You do this once when you install. It's not that big a deal to just copy and paste it in, right? When I build up the library tables, I scan the directories. Maybe I should look to see if there already is a symbol table in that directory and then keep that. But all the descriptions disappear. I don't find that a hardship. I know what I'm looking for. I'm not looking to my symbol table libraries to tell me what's exactly in them with a one sentence. So it's not a hardship, but I do lose them in the way I've done this. So I want to point that out. So there's going to be no time. The script is not rocket science. It's Python. It's really not that hard. You open a configuration file, you read out the things, you build up some dictionaries with the names of everything, and then you call a function that spits out the 3 files. Right? So with that, and I will really definitely try and pick the pace up here because I got quite a bit of slides, but I'm fond of saying that engineers don't make products, they make the files that other people use. They make the plans that your manufacturing staff uses to make what you want, right? So output files to me is critical. It is the whole reason I'm there. I want to generate them automatically. There's tons of files to generate. Depends on your manufacturer. You may need one thing or another, but maybe you make them all because depending on the board, you send them to this guy. Sometimes you send them to that guy, right? And you want it all to happen right away. So over the next couple of slides, I'm going to point out I'll go through it pretty quickly, but I'm going to point out there's some quirks in the way this is all working right now, right? I'm getting the evil eye over here. All my comments were for 9.0. Oh my God, 9.0.2 is already out. I I got on the airplane, it wasn't there. Here I am, it's there. This is great. There's some big bugs that were in the job sets in 9.0.0. Move on to at least .1 right away, because otherwise you may open your job set file and see nothing listed there. And that bug's fixed. I got 16 steps. And theoretically, you could have one click, except there's some quirks, and so it doesn't quite work. So I'm going to rip through these steps real fast. okay? I click on do first, and the first step is I make my output directories, a little bit of Python. I like the idea of putting the Python right there. I don't want to like call in this output job a separate Python file that now with the output job I got to pass little scripts. So this is great that I could just squeeze the whole thing in there. I do edit it in Notepad++ first, and I keep around a little file for me, but then I paste them right in there. All I'm doing is I look for stuff. If the directory's already there, I remove any files that are there, so I'm starting off clean. And then I'm assuming that when you get to the end, because I'm wiping this out each time, that you're archiving it. Either you're doing a check into Git or you're zipping it up and putting it elsewhere, that you're not going to accidentally wipe your own tools. The version of the files that you've already sent off to manufacturer. Okay. First, I generate an ERC. It's okay that you have errors. Every board I've ever made has ERCs and DRCs. You look at them and you go, that one's irrelevancy. Oh, your silk screen goes off the edge of the board. Yeah, but so does the connector. So who cares, right? There's certain errors, but don't do it blindly. Record it when you're making your output files, right? Now this is where there's a weird quirk. Okay, I want to generate a PDF of the schematics. If that says output directory, you cannot control the file name from this dialog box. You can only pick the directory. So for this one, for the schematics, I don't put in a directory because I'm going to rename it later with an execute command with a bit of Python, right? But for some reason, it doesn't show up until you actually exit your process. It's often a temporary directory. I found it, but it's temporary and it's named arbitrarily. And so you have to actually exit your little process there. So I stick that in the, everything's getting put under outputs, which you do in your project, right? I move on to the PCB. I do a DRC, same thing as before. It's okay to have them. Just write them down, keep track of them, right? So now I generate what I call my fabrication drawing. It's got the notes that Sierra or whoever likes to see. And again, it's going to be project name.pdf. That's what you're getting. So I stick this one in the PDF directory so I don't overwrite the schematic one from before, right? And then I get to my do second. And there you can see I set the destination path to outputs, right? So one line of Python, and I can grab the file name, and I could rename it. Instead of project name, I could say PCB top view, because I do a top view and a bottom view. I get dimensions all on there, so to go along with the step file, right? So now, my first step in the do second renames that one, and then I export the bottom. But I got to stop again, because it's going to have the wrong name. So I come down and I rename it. And now I'm in my last step, which does a lot of stuff. It's super fast. I'm really impressed with the pace at which you get output file generation here from KiCad. It's super fast. So I rename the other one to bottom view. And then I generate my BOM. Oh my God, this is such an art form. Some people demand it all happen in the schematic. I tend to think you're better off to do it in some other tool that's better capable of dealing with substitutions and all that other stuff. And in the same breath, I can tell you for sure, I know of a product, they make over 100,000 units roughly a month. And that whole thing is being done with Gerbers and an Excel spreadsheet, man. That's it. I mean, it's a $15 million robot that puts the product together, right? But the circuit boards, that's it. That's all it takes. You can do more. If you can, do it. I export a step file. This goes a long way to making your mechanical engineers happy. Otherwise, they're going to be looking at your little fabrication drawing and trying to make up something equivalent. In the same breath, put your dimensions on your fabrication drawing. It's important because they're going to be looking, in their 3D viewer, and they might want to just go, oh, geez, what is the pitch between those connectors? Oh, I put them on a 20 millimeter, right? And it's readily obvious. I love the component output filtering. A lot of boards only really need J star, right? Just your connectors exported, things that leave the board. That's it. Mounting holes, and that's it. And if you start pulling together, as I did, to make that MBCU, that sheet metal was done in FreeCAD because I don't know anything better, and I needed it done. And so, you start rotating around 5 circuit boards stuffed with components, and then I make an array of the other ones, and oh man, you really bog down your machine. So being able to just export what you need this is a great feature, missing from Altium. Now, I don't want to sound like I'm a guy who only throws around. I changed this last night. I don't want to sound negative. Right? I don't want to sound like I'm like the kind of guy who just walks around crapping on everybody, right? So I want to shout out a couple of my vendors here. I use out-of-the-box manufacturing. They're in Renton, Washington, just south of the airport. They're a nice factory. It's clean. They got plenty of lines. They can follow your ISO standards if you need. And I have done a number of projects with them, and they will do turnkey straight into a box if you just tell them what you want. I have not used that feature from them, but they are great. They are manufacturing a board for me as we speak. They ask for GenCAD if you're going to give them Gerbers. And so there is no GenCAD selection in the job sets right now. Glad to hear it. Because while this is great, I'm a programmer, right? So I look at that and I'm not phased. But not everybody has been doing this for 40 years. And they look at that, they just want a GUI. They just want to click on the boxes. So, hey, the star of the show, you generate your Gerbers, right? And this is great. I got nothing else to say about it. You pick the choices, you hit the button, you get your Gerbers, right? Here's where I got a little bit of a complaint. You go to generate your drill files, and they don't end up in the Gerber job file. And so another vendor that I've used a lot, Pentalogics, they started out making software for people doing fabrication, right? And so they ended up being like a contract broker for circuit boards because they had the software that can pull in these circuit boards, panelize them, and they piece together everyone's little jobs, and they have pretty great rates without going to Asia. And I've used them a lot over many years. In the same breath, they can go to Asia if you want. And I always believe that you should validate your outputs with some tool that's not the tool you made it with. So I've never opened up the Gerber viewer from KiCad. I've never used it. I've been using ViewMate forever. I trust it. I've made a lot of boards. When I look in there and it looks right, I get the board that is exactly what I like. The view is free. I encourage the development team to download it and try it because you'll see on the next slide there's some issues. ViewMate doesn't deal well when you grab the zip file with everything and it finds a Gerber job file. It assumes that if it's not in the job file, it doesn't exist. It doesn't continue to parse, so these extra files aren't found. And that's a minor annoyance. For circuit boards, too, I use Saturn Electronics in Michigan. They've done metal core circuit boards for that 3D TV. They do Flex also. I've used them here at NCX because we had some stuff that had tiny vias, and I just didn't want to throw it to a broker. He would have done it, this fellow Greg. It's nice to actually get human beings at Pentalogics, but I had to send it overseas. And this project I couldn't send overseas. And then if you're ever doing Flex and you need 1 mil vias on a 3 mil pad, I hate to tell you I needed that. Oh my God, your choice is MicroConnects or nobody. I am floored with the accuracy. And Flex, they move. When you start hitting with the laser, the Flex starts moving. How they get such tiny vias on such small pads, I don't know. They told me they could do it. I believed them, and it worked. Now, I'd love to move to IPC 2581 because I'm as done with Gerbers as everybody else. And I will wrap this up in a minute here, okay? But they don't open in ViewMate right. There's something not right, and they don't open up in the WISE 2581 viewer right. So again, my message, I'd like the team to grab a couple of these other viewers and try and view these netlists because they're not working right. And these will get resolved. These will get resolved. And I'm not hearing people saying, hey, I used the 2581 netlist from KiCad, it didn't work. I'm just saying I got nervous, and so I went back to Gerber's. I knew what they were going to do. Same thing, the ODB++, I know that's brand new, but it doesn't open up in ViewMate. And so, because I thought, well, if I can't do the 2581, I'll do ODB++. And that's the last step in the do last, right? So I got my 3 clicks, everything gets named, right? And then not everything shows up until it ends, so you gotta end. And I have this little bit of script that zips everything up so that I get one set of files from my fabricator and an additional set of files, includes the fabrication stuff, but other stuff too, that go off to the assembler. So I got the 4 buttons, and it's click, 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 done. This is fantastically important to me. And so this is my last slide, right? We do things with extremely high voltages. When things go wrong, we shoot literal lightning bolts. I destroyed $8,000 worth of equipment until we realized we weren't grounding a piece of nearby equipment. It was left floating, and then it would charge up capacitively under this massive multi-100,000-volt field that's nearby, and then whack. And oh my gosh, I'm sitting there, and I see it. I got a scope probe sitting on the desk, and it picks up a 500-volt peak-to-peak signal, right? So safety first. You know, I'm the EE. I'm the guy who's going to turn this thing on the first time. Safety first, right? We were luckily, everything was an enclosed lead room with an interlock, right? So we were just watching the aux shoot on video. But I would not use KiCad if I thought my life was in danger, because these things will kill you. 200,000 volts, there's no may, your heart may stop. Your heart will stop. I got a power supply, came 80,000 volt power supply. I kid you not. The cover page shows a picture of the supply. You open it up, 20 pages, how you do mouth-to-mouth resuscitation. Call for your ambulance first, right? Make sure you're not going to get shocked in addition, right? If it's good enough for us, it's good enough for you, right? So this is the end of my talk. You can contact me if it's work-related. You can contact me at NCX. If it's just more generic KiCad, this is my personal email that I use. I'll warn you, if you talk to me, I will be your friend. I cannot make enough friends in this world. I am an utterly social person. I will be taking the train to Old Town for some Mexican before I go to the airport later if anyone wants to join me. And so this is the end of my talk. Sorry I ate into your lunch period.
Thank you very much. We're going to rearrange our schedule just a little bit because there's food outside and we don't want it to get cold. So we are going to shift our lunch period to right now, and then we'll pick up after lunch where we left off. So please head on outside and enjoy some lunch. Thank you, Jason, again.
I built a bunch of Category 3 surge test equipment, 40 kV, half ohm source impedance. Yeah, the capacitor was about half the size of this electron.
Oh my God, the stuff we work with is, you go get a feed through to get, you want to take 180,000 volts, and you want to go through to get inside, right? It's this big. It's this big. Customers are saying, boy, your product is heavy. You're like, the cable, 180,000 volt cable, it's got a wire. I mean, we're at low currents, right? So we got like an 18 gauge wire with 2.5 inches of radius around it. Like, I'm telling you, for the wires, it's something else.
I got a fun one for you. What do you use to isolate your high voltage from your non-high voltage side of the world?
So the cathode, right? We are we buy those supplies, right? And right now we ground our gate, and then we go to the minus 2,000 volts. And so I'm using some parts from TI that I think are inductively or capacitively coupled isolators. They're good to 2350. We pushed them a little. They've told me flat out, they're like, look, we wouldn't tell you 2350 if it like broke at 2351. Are you kidding me?
So my question to ask you is, are they rated for DC or AC?
That is the DC working voltage for that
Okay,
one.
because I got bit by an optocoupler that had an AC rating of 6,000 volts and
Oh, yeah.
failed at 600 DC.
Yeah. So there's we buy some power supplies from a company called Recom, and on their website they have a calculator that will let you. It's a little table, so if you got an AC number, you can see the DC equivalent
No.
rating.
The failure mode was this was an active optocoupler.
Yep. Yep. Oh. Which isn't just gender; it's also just the personality.
It's partially gender.
It's gender and birth order and yes, yeah. And COVID. Oh yeah. Because I do a lot of this, like I mentioned, coaching sports, and the athletic directors I talk to, they say any age 17 through 20, 21 is 4 years development. So you look at them and you see the man child. Yeah. The reality is they're about 4 years back because they never had the help to play right fight. So they just really it's fascinating. Resilience, issues, all these things. And I told that to my friend. That was all just our sons. Plumbing in the water, entitled burn. It might be that still, but also. It might be that still, but still. But there's some contributing factors. But yeah, so that's how I thought.
Second system syndrome?
Second system. Yeah. Because that definitely resonates. That's software project. That's probably the same thing. Yeah, I mean, it's just this thing that. And it makes sense. It's sort of like the B-52 picture of like all the holes in the B-52 that came out. Yes, that's right. This is a way of capacity. That one, that survived. And the other one, it's sort of same vibe. Where it's like, oh, that is a fascinating analogy, actually. Yeah, if you haven't seen that. I have. Yeah, it's B-17. Yeah, I never thought about it in terms of startups. Yeah. Which is if you're not wounded in these particular ways. Yeah. Well, you didn't realize it, right? Because you didn't look at it. That was actually a good thing that we got you there. That's amazing. And that would be the thing. So one sort of called pressure. So like at one point most of the it's like if there's
This was at Twitter.
Yeah. Yeah. And so they did a segment. But you know, especially if it's the very first one. I'm really curious to see where you guys are going. What's that? Oh, you're doing that? Okay. Me too. What's he like? Yeah. Oh, Mark is today? Yeah.
It'll be on YouTube later anyway. So yeah,
Google. Let's go back. Google. Yeah.
It's like almost everything.
No. Who was Rocky for the shot? It's their fans. They almost killed it. No,
I have some that I inherited some TI bound volumes. There's people asking a big dollar for some. So there was a company, I don't know if they still exist, called DEC. Oh, I remember. Okay. So I'm working with some synchros and a control transformer servo. And I was searched eBay because I just bought a really neat control synchro. I'm building a panel. And came up in the list was some data books. Somebody selling 2 or 3 of those data books. They want $200 for those 3 books. They sent me like a discount offer of like $190. It's like, I don't want it that bad. I get $20 for it, not the rest of the year. It's crazy. Data books down their socket. Like you said, there's people who are very some of those data books have a real foundation to your papers or your explanations of certain things. The really good one was at Watkins Johnson.
Okay, so I hope everyone had a good lunch. You've been refueled and you are ready for round 2. We're reorganizing the schedule. Like I mentioned, we're kind of pushing things back a little bit because I went over this morning, and then we had some very, very interesting content throughout the morning. And so one of the nice things about running these conferences is we can kind of make some decisions on the fly to highlight the most useful content that we find there. And so what exactly it was helpful. And so what we're going to do is we're going to push all of the slots back by 1. So our next talk is going to be from Jeremy Gordon of Circuitly. And as we push things back by one. It's like a musical chairs. There's going to be one thing that falls out, and the thing that falls out for this conference is going to be Wayne's second talk. We had tagged him in twice, and he was gracious enough to say he'll be okay with presenting that talk at KiCon Europe in September. So. Booze.
I feel you.
You still get the recorded talk, and you still get the slides, so you still get the content, and you should totally come to Bochum. It's fabulous. If you liked KiCon in San Diego, you'll love KiCon in Germany. And if you're a West Coaster and you don't fancy heading over to Europe, there's also KiCon Asia in Shenzhen, and that is really a conference to see. That is a next level conference that happens in Shenzhen with our partners at Washoe. So that's how we're going to adjust the schedule for this afternoon. With those housekeeping details out of the way, let me introduce our next speaker. It is Jeremy Gordon. So you may or may not know that there's this thing called AI out there that people are starting to talk about. And as we had a couple of questions earlier today about how you might use this, there are plenty of opinions on AI, but very few informed opinions. We are very fortunate to have Circuitly and Jeremy Gordon here to give us an overview of how they approach making AI actually useful in a way that will potentially, I think, I'm getting a shrug, be useful to circuit designers. And at a bare minimum, we need to figure out how we use this, or it will figure out how to use us. So I really appreciate Jeremy Gordon being here to talk to us about his company, Circuitly, and their use, how they are connecting AI and KiCad. So please give a warm welcome to Jeremy Gordon.
Thank you, Seth. And thanks, everybody. I'm going to talk about AI, talk about a lot more than that as well. And mostly I'm going to be sharing a bit of the thinking around the design and architecture of Circuitly. Before I jump into the nitty-gritty of the talk, let's just start by answering the question, what is Circuitly? And maybe more importantly, why do we think that KiCon attendees and KiCad aficionados might care about that? So Circuitly is a KiCad compatible Git and web browser native EDA tool. As a longtime KiCad user and a software guy, I started Circuitly to be the KiCad companion that would let me work with the type of browser and Git-based workflows that I'd come to love from my software development career. In talking to a bunch of my hardware professional buddies, the ideas seemed to resonate with them too, and Circuitly was born. So whether these workflows and Circuitly's approach resonates with you as well or not, my hope is that you'll find some of the ideas in this talk interesting and maybe food for thought when it comes to your own EDA workflows. So real quick, what do I mean when I say browser and Git-based workflows? So for software, I really love an asynchronous workflow, the flexibility of working with a distributed version control system like Git. I get like a source of truth stored in GitHub or GitLab that I can go to for past revisions, to track experimental changes, and to keep me in track of changes I make in response to the occasional defect in my work. But I really want to work with files, but I also really want to have the convenience of sitting in front of any browser with nothing to install and have access to all my data within a few seconds. So I'm going to talk through a bunch of product and design decisions and our technical approach, more about our Git support in a minute. But before I get to that, I want to quickly level set on the rest of the big picture of Circuitly. So Circuitly is more than just a cloud drive for KiCad files with Git. It's a full-blown editor of KiCad files, including schematics, sheets, symbol libraries, symbols. Circuitly presents, you can see here, a tab-based interface with a stack of panels on each side, floating toolbars, modals, sort of the UI paradigms we've come to expect from both KiCad and browser-based software. Circuitly also supports boards, footprint libraries, and footprint editing. We aim to be a companion to using the KiCad native app, but also to support end-to-end EDA tool functionality, including generating files for manufacturing. There will probably, scratch that, definitely always be things that KiCad can do that Circuitly cannot do. Today, that list of things that Circuitly does not even try to do yet is long and includes things like 3D preview, simulation. Over the time, we're closing that gap. But despite that, as we heard from Wayne yesterday, KiCad development velocity is absolutely insane. So Circuitly will always be chasing new features, like even not stuff in 10, but some stuff in 9, like multi-channel design support that's not yet in Circuitly. As a companion to KiCad rather than an outright replacement, we think that's okay, as long as we do no harm to the KiCad files being edited in Circuitly. We think gaps and features are okay. Open it in KiCad. So in addition to native version control and collaboration features, we think there are opportunities for Circuitly to introduce other sort of more web-native features, and this is the kind of stuff that Seth was just talking about. A good example of this is Circuitly's Research Assistant. So I'm going to talk a bunch more about our Research Assistant a bit later in the behind the scenes in the talk, but for now, know that the Research Assistant is a opt-in assistant on a per workspace basis, and it is opt-in based on the owner of the workspace. It prioritizes privacy and intellectual property of yours, not ours. We don't train on user data or user actions, and we only work with model providers that have the same priorities as us. Okay, so now I think we have a pretty good level set on what Circuitly is. I'm gonna go real quick and just give you some background on me. I'm a software developer by trade, spent the first half of my career in console video games, so that my era is like Super Nintendo through PlayStation 3. I founded and ran 2 independent game studios, the latter of which was acquired by Sega, where I became the North American CTO. The through line of my career has really been building companies focused on building visual editors. So a little bit later, I co-founded a visual behavior development platform that was ultimately acquired by Twitter, where I ended up being the VP of engineering through the IPO. More recently, I co-founded a data-focused presentation company that was acquired by Medium.com. But software aside, I've always been passionate about electronics. My era of console game development was all about bit banging on the hardware with no OS. And I suppose that ultimately Forrest Mims III is probably to blame for my inspiration, and it's just never really left my blood. My love for electronics goes from building, I kind of like the smaller stuff, no surprise, game type things. This is a little Bluetooth and Wi-Fi enabled. It's an NRF, I think it's a 5240, little flash RAM, little LiPo battery health, little networked OLED screen. But more than just building stuff, it's also led me to many maybe ill-advised expenditures, pilgrimages to Shenzhen to go do some factory tourism. I'm a little bit chagrined to say I should probably have just gone down the road because I'm in the Bay Area, and so I am going to be visiting Sierra Circuits a little bit later, take the tour that I've been promised, right? Yes, yes, okay, great. Cool, so now that you know what Circuitly is and who I am, here's what I've got prepared for us to talk about in the rest of our time together. So first off, let's talk about KiCad compatibility. So one of the first key design decisions we made for Circuitly is that we would operate directly on KiCad data. No lossy import or export processes. So from schematics to boards, but also projects to themes, from symbol libraries to footprint libraries, Circuitly operates directly on KiCad data. So we've developed a KiCad-centric collaborative data model, and the way it works is it represents a superset of the released KiCad version data. We've also developed a set of KiCad file format parsers that read KiCad files into our data model. We remember the original file's version so that we can both save edits back to the correct KiCad file version, but also so when we're editing, we know to constrain the editor to what that version of KiCad supports. I'm sure we're all familiar with kind of like the Christmas morning feeling of booting up a new version of KiCad, and you open kind of an old file and it upgrades it and says, hey, when you save it, it's going to save it to the new version. And that is awesome and the right way to do a native app. We do not have that luxury. So if we open your KiCad 7 file or your KiCad 6 file, we will save it as your KiCad 7 or 6 file. But more than just file formats, Circuitly works with KiCad concepts. We know that most of us have heard about talks, and I think most of us have used many different EDA tools, and so there's a lot of ubiquitous concepts, symbols, pins, wires, netlists, but there are many concepts that are more KiCad specific, specific KiCad flavor. The relationship between sheets and sheet instances and reference paths, and we had a great talk about custom design rules. This stuff has maybe got some analogies in other packages, but KiCad has a flavor that I think most of us in the room and probably listening on the webcast have come to love. So Circuitly does not just understand KiCad file formats, but it also understands KiCad design paradigms. Support for KiCad versions does not end with schematics and boards. We also load the correct version of KiCad's global symbol and footprint libraries based on the schematic or board being edited. So whichever tab is current, whatever schematic or board or footprint or symbol you're editing, the Workspaces panel on the side will show you the appropriate KiCad 6, 7, 8, or 9 global libraries and shows you whatever your project libraries are for that file you're editing. Okay, but beyond just file formats and data models, we've put a ton of work into making Circuitly's renderer performant and look like KiCad, down to the pixel level. Several of us on the team have got a background in computer graphics. For me, I've kind of already talked about that. It's PS3 era games development, making level editors for open world games. Give me 1 second here. For one of my teammates, Joe, that's several years spent with the Blender Foundation, working on features including early support for subdivision surface rendering and editing. And we all know from using it, KiCad is no slouch when it comes to rendering performance, especially for those of us who remember before the hardware acceleration. It's been amazing. And we can load really complex boards like we were seeing the CERN board in KiCad and be performant. So we've spent a tremendous amount of time to allow Circuitly to keep up with that same kind of 60 frames per second rendering, but in the browser. So really that means things like TypeScript, C++ and WebAssembly, web workers, which allow us to use hardware cores, hardware threads, WebGL. This is just a little blurb about an algorithm we actually don't use anymore, which is a stencil and cover style algorithm, but we have a new vector-based algorithm that is more generalized and even faster for us. Okay, but just moving on, I want to kind of touch on a couple different other areas of Circuitly, give you some behind the scenes about how things work and how we think about it. And it's not lost on me that I'm talking to a room of mostly hardware developers, but I am going to talk some software stuff because I love it. I'll try to go quick. But one of the questions that I get a lot is like, okay, so did y'all just port KiCad to like JavaScript and stuff? Like, isn't that the sane way to do it? And the answer is no, most definitely not. Actually, unfortunately, because I have a really high regard for the KiCad codebase. But Circuitly is implemented from scratch in about 750,000 lines of TypeScript and C++, along with a couple hundred NPM packages. We have plans to open source significant portions of our codebase. Many members of our team, including myself, have spent time doing just that at large organizations like Twitter, Blender Foundation, Sega. And that's given us a healthy respect for the effort involved in doing a good job open sourcing something, so we want to make sure we do a good job with that, but we are committed to that. One of the early lessons I learned in video games is you don't just build the game and then like add multiplayer at the last minute. And similarly, with something like Circuitly, we have to design and architect the multiplayer in at the beginning, and so that's what we've done, and that's a big part of why we just can't port source code. It's also GPL, and we're not GPL, so that's another reason that we don't look at or use the KiCad source code for Circuitly's purposes. So like most all cloud software, and this part I'll try to go quick, but maybe Rose will nudge me because I love this stuff. But Circuitly's implementation is split into two parts. It's got the browser-based side and the back-end side. In our case, the browser-based side, we're looking at Chrome, Firefox, anything kind of WebKit-based. And on the back end, that's AWS for us. Our web app communicates with the back end over a mix of HTTP2 and WebSockets, and it travels through a set of Amazon-hosted content delivery networks and load balancers to get to the Circuitly services. This also allows us to use best-in-class security. All the Circuitly services stuff is off the internet behind all this Amazon front-end tech. We make pretty heavy use of distributed queues to help us coordinate things inside the Circuitly services, and ultimately we're storing stuff in databases and storage managed by Amazon. That gives us 4 nines resilience and crazy backups and multi-region stuff. It's pretty awesome. Last thing I want to mention about this architecture that's maybe not obvious, that's kind of cool, because our services are done in Kubernetes, because we're using pretty modern and typical cloud techniques, we actually can stand up an entire Circuitly cluster on our own local development environments, but also it means that it's not very hard for us to allow Circuitly to be deployed in a standalone, somebody else's AWS account, or maybe completely closed on their own hardware somewhere for the security or paranoid-minded, or both. So last little bit of back-end stuff, I promise, but we're a service-oriented architecture, so zooming in on that Circuitly services part, what we are is a set of Docker containers, written in TypeScript mostly, orchestrated by Kubernetes. So Kubernetes kind of orchestrates all these pods or services. We're somewhere between a monolith, single app, and microservices. We have only maybe a dozen or so different services, which we run multiple copies of each for resilience and based on load. So examples include the user service, which handles usernames and passwords, notification service for delivering emails, Slack messages, in-app notifications. The workspace service handles permissions and sharing. Document service, near and dear to my heart, is where the heart of our collaborative data model is. Render service is pretty fun. That one handles rendering everything from previews, thumbnails, PDFs, but also Gerbers. And then the Git service deserves a bit of a deeper dive. So I'm actually going to jump into that now. So combining Git workflows and browser-based editing, I mentioned that at the front, that's kind of the raison d'etre of starting Circuitly. Sorry, Lucy, if she's here, but my French sucks. We designed Circuitly to allow multiple users to collaborate on collections of KiCad projects asynchronously, meaning that they can all submit sets of changes and commits to services like GitHub or GitLab on their own time. So more than just a way to collaborate, this also ensures that users are in control of their own data. It's fundamentally KiCad files on Git. As many of you may know, Git workflows are not just about collaborating with others. The way I like to think about it, they're also for collaborating with past and future you, helping you manage design revisions, experimental branches, keep track of bug fixes, board revisions as you spin different revs. So I think, in some cases, people may think, I'm not collaborating with anybody. Yeah, you got past you and future you. Those are pretty tough collaborators, at least in my case. It's hard to collaborate with future me. But despite being a browser-based app, we present a file-based interface to users. So in Circuitly, users create what we call workspaces. That's our unit of thing, atomic unit. And a workspace contains a set of files like KiCad projects, schematics, boards, PDFs, markdown files, firmware files, whatever it is you're throwing into your Git repo. And on that point, Circuitly, every workspace in Circuitly contains its own Git repository. So this is a Git repository hosted by Circuitly. In Circuitly's asynchronous collaboration model, our vision of it is that every user creates their own workspace with their own clone of the upstream Git remote repository, which may be in GitHub or GitLab or maybe their corporate Git repository. So users edit the files in their own workspaces, commit their changes to their own workspaces, and then they can fetch updates made by their collaborators from GitHub or GitLab and use our side-by-side views so they can do comparisons, copy and paste between the two, resolve differences and conflicts. I was really excited to see that KiCad 10 has visual differences on the books. We also have a visual differences feature that is in progress. And so ultimately, all ways to figure out how do I merge conflicts with collaborators, whether they be humans or past and present, future you. Ultimately then pushing all these changes back up to the source of truth at GitHub or GitLab. So if our weird little startup goes away, all your stuff's KiCad in GitHub or GitLab. Back to the software stuff briefly. On the face of it, Git may seem like a pretty solved problem. It's open source. There's a very robust C++ library called libgit that's the canonical Git implementation used by the Git CLI. However, while Git was architected by Linus for managing kernel patches for Linux to store those in the cloud and trade them, Git clients were architected to do everything on a user's local hard drive. So due to this, it doesn't really work in the cloud to actually run Git operations on the back end. So we decided, because we're masochists, that we would implement a cloud-based version of Git from scratch in TypeScript, including the Git protocol implementation. We drew a lot of inspiration from GitLab's Gitly, which is a sharded, essentially Git service in the cloud. In very brief, we have our own thing called a Git archive. If you know about Git stuff, it's essentially like a Git pack file. And we have kind of cached partial Git archives with indexes on each Git shard in our Kubernetes cluster, and they can kind of stream back and forth to the source of truth storage in our servers. But of course, as I mentioned before, you're pushing and pulling to sources of truth like GitHub, GitLab, or corporate Git repositories. Okay, so while asynchronous collaboration with Git workflows, that was the founding thing I really wanted, it's not the only way that Circuitly users can collaborate with each other. So we also enable synchronous collaboration. So if Git our Git workflows are about being asynchronous, about doing things on your own time in your own space without anybody watching you. Our synchronous real-time collaboration is about doing things with others in front of others in real time. So this is basically like Google Docs. The way we think about this is while we want to spend like most of our efforts designing at our own pace in a safe space at our, without having anybody like second guessing us, we do occasionally want to invite other people into our space to pair with us in real time. And that's what our asynchronous collaboration does. Another key early decision that we made was to use conflict-free replicated data types as the basis of the collaboration in Circuitly. I'll go quick because, again, I recognize this is not a software group necessarily, but I love this stuff. In past startups, I've done a more traditional operational transform-based approach, which is basically what Google Docs is based on. And recently, CRDTs have gained a lot of traction for a number of reasons. I'll just go super high level about it, but updates can be made from collaborators in any order. They're idempotent. You can apply them more than once. More importantly, they do not require a centralized server. So updates can be sent peer-to-peer, which is great for latency reasons. But also really great for this is that we have the potential for easy offline mode, where we're storing all these CRDT updates in browser local storage while you're offline, and then when you come back online, we do all these changes get applied. So the other big advantage of using CRDTs is something that I think we heard a little bit about before lunch, just this idea of like what is hot, what is getting the attention, what's getting the effort put into it. We were hearing, I think, a little bit about how Altium feels like maybe it's falling off, hard to say, but with CRDTs, they are definitely hot. That is the thing that everybody's putting effort into, and so in specific, we use something called YJS, which is a really great project. It's very JSON-based, so what we do is a real-time synchronization between our custom data model, which is sort of the in-RAM version of, as I mentioned before, a superset of all the released KiCad versions. We synchronize that essentially in a JSON-y format with YJS conducive to CRDTs, and then that gets synchronized across into other clients, goes from their YJS into their Circuitly data model, and that's how we get the, you drag it, I see it kind of stuff. And then all that stuff, as well as being transmitted between clients, it's also going to cloud storage. So one thing of note before I move off of real-time collaboration is CRDT or operational transforms, whatever you pick, they're really great foundations. But one of the ways academics measure the quality of a collaborative algorithm is something called intentionality. And I think it's a really important thing to mention and something we've paid a lot of attention to. So the easiest way to think about this, in my opinion, is like if you have multiple collaborators working on a sentence in a Google Doc, you expect that that's going to be eventually consistent. Whatever the latency is and people's computer speeds and what's going on, you expect when everybody's done typing, eventually, they'll all have the same sentence. So intentionality is, yeah, but does that sentence make any sense? Like, is that sentence just a scrambled garble of letters? And we all see the same sentence, but it has nothing to do with what we were all typing. That would be poor intentionality. So there's a great potential for a visual application to have poor intentionality. For example, in the context of Circuitly, what does it mean for two collaborators to attempt to drag the same set of connected symbols or footprints? Like, do we average the two? Does somebody win? What? And what about all the wires? So basically, what we do in brief is something we call dynamic locking. When I grab and select something and start moving it, it'll show up as semi-transparent on somebody else's collaborator. They cannot themselves then select it. So it's a way for me to see like, oh, okay, you're messing with that. I probably shouldn't be. Lastly, our synchronous collaboration supports annotating schematics and boards with comments. We have a pretty robust comment system, allows Circuitly users to chat with each other, and if enabled, the research assistant, which I will talk about in a second. So there's threading, reactions, emojis, and this idea of resolving comments, both in-app notifications, but also email notifications, which is kind of important because if you have somebody you've sent your design to with just a URL, and they maybe are or are not a KiCad user, and maybe they're lightly engaged with you because you're begging them for help, they can just get that email, click the link, open it up, reply to comments, and if you comment back, what are the chances they're going to open it again? probably nil without, like Google Docs, getting an email back saying, Jeremy asked a follow-up question. So this is not new stuff. This is kind of tried and true design from many collaborative apps, whether it be something like Notion or Airtable or Google Docs, but we've got it. Okay, so on to what Seth was alluding to. Circuitly does in fact have AI. So as I mentioned before, there's these opportunities because we are a web native app to do these sort of more web native features. Not that you can't add AI to a native tool, but our research assistant is a good example of that. Now, I spent a lot of time working in AI adjacent fields. At Twitter, I was responsible for the search and relevance group. I did not directly manage it, but as a VP of engineering, it was in my span of control. And so I believe I'm pretty up on it, and that it's very fraught with pitfalls, that AI can be a mess. But I also believe it can be super helpful if you do it right. So the thing I mentioned before, and before I go any further, is Circuitly's AI features are all opt-in. So you have to choose to turn on the AI, not as just a user of Circuitly by itself, but on a workspace by workspace basis. So the owner of the workspace has to opt in for AI to be on for that workspace. And this is, again, because we take privacy and intellectual property super duper seriously. Okay, so when enabled for a workspace, Circuitly's Research Assistant shows up on a sidebar on the right, and it has essentially an electrical engineering focused agent that has access to the data in your workspace, which includes schematics, boards, data sheets. So what we have sort of a two-pronged strategy on AI for Circuitly. One is a research assistant, and the other one, which is not something we've released at all yet, or even to our design partners, is a co-pilot. And the way I would distinguish between those is the research assistant puts information at your fingertips at the time you desire to use the way you see fit. A co-pilot is maybe something you ask to help you do tasks. So our initial part of our strategy, the only thing that we are launching today, is the research assistant. So we've designed it to help provide input into design decisions and analyze work in progress. It will come as no surprise that the research assistant is large language model based. And as I mentioned before, I've been pretty involved in this space for a bit, and I've been tracking the rise of LLMs, and I'm not gonna lie, I've thought it was mostly not helpful for quite some time. I've been tracking it since 2012, which is the AlexNet paper, for those of you who are machine learning nerds, which is the convolutional neural network paper that kind of kicked off a lot of this idea of like, AI doesn't seem to work very well. What if we just threw all the data at it? And then magically it started to work really well, which was kind of shocking to everybody. Anyway, long story short, fast forward to, I would say, fall of last year, and some stuff really started to change, which is the size of the models and then the size of the context window. So I'm gonna go really quick here, but long story short on this, if we think of tokens as words, the context window is how much information you can dynamically give to the model. It has all this human knowledge baked into it, but without retraining it, without feeding it private data to bake into its model, how much kind of is the query? How much can you tell it? How much can you ask it? So we use a CAG-based architecture, cache augmented generation architecture, and what's interesting about this is that the context windows have gone from, call it early last year, maybe 1,000, 2,000 words, to now 2 million word context window, which means that we can feed this thing not just paragraphs of a data sheet, but we can feed it the whole data sheet. We can feed it not just fragments of a schematic and board, we can feed it all of it and still feed it War and Peace and have room left for it to think. So this is like game changing for a lot of AI tools, and it's why if you use things like Perplexity or some of these other research type tools, they've taken a massive jump. So if you were kind of, as most of us are technologists, keeping a pulse on things, if you were kind of keeping a pulse but took a little nap starting in September of last year, I would wake up and watch some YouTube videos and play around with some of this stuff because it just got crazy. So we've come along at the right time to benefit from some of that. So you can ask questions like, what does this circuit even do? And get bananas reasonable answers. It's still AI, still gonna hallucinate sometimes, but it's pretty interesting. And then baked into a tool like Circuitly, you get a lot of hyperlinked context and all kinds of fun stuff. I could talk on and on about it, and if you want to, come find me afterwards. Okay, so maybe wrapping up a little bit. This is a pretty big day for us. At Circuitly, we've been working on this for 2 years. We have a number of design partners we've been working with, but this has not been available. And as of now, we're making it generally available. We're launching it for the first time. It's an early look release. I'm mortified. I'm embarrassed. It's got bugs. It doesn't do things I think it needs to do. But what do they say? I think it's if you're not embarrassed, you're not launching soon enough. I'm embarrassed. We're launching soon enough, I think. Now, despite that, we do take your time very seriously, all of our users' time seriously, and we're committed to being responsive when it comes to bug fixes, improvements. We would not be putting it out there if we didn't think that there would be some value to folks. But it is, you'll have to be a little gentle. And as I mentioned, ultimately everything's in KiCad format, and if there's something Circuitly can't do, you can always open it in KiCad. So just sort of a little bit of nitty-gritty. This is really my love letter to the KiCad community, Circuitly as a whole. And this is what we're doing for early adopters, which is open source, always going to be free if you're doing open source hardware. No private projects, though. No private workspaces. On the commercial side, and you can do commercial things with the open source plan. This is a subscription-based model, obviously. The starter plan, no Git, so makes me sad, but that's the starter plan. Free, lifetime free. What does that mean? It means if you sign up, we're never going to charge you. Now, when we get simulation or when we do other future features, they may not be available in the plan that you have lifetime free, so you may need to upgrade. But if you like what's happening, and we value our early adopters, so we're going to try really hard to give you all the juice we can, as long as it doesn't break the Amazon bank. No Git workflows. Professional, $9 a month, 15-day free trial, and that one does have Git workflows. So we would love to get you to sign up. Tell us where we're full of shit. Tell us where things are not working. Tell us what doesn't happen. Tell us what you think we should have. Tell us what you like. That'd be awesome too. If you do sign up, we have a bunch of Circuitly hoodies. Anybody, first come, first serve, but anybody signing up gets a free Circuitly hoodie. So just come by and let us know that you signed up. Hit up Rose Wave. So this is Rose. And yeah, that's, oh, I should mention also, we have a student plan. We were actually in 5 universities in the fall, which was fascinating. I wasn't sure how we should market to students, and Mark Suster, our very lovely and helpful board member and investor, he said, don't figure it out. Give them a budget, tell them like no spray paint or vandalism, and turn them loose. And it was freaking awesome. So that was really great. So we do have a student plan as well. No commercial stuff for that. Anyway, that's my time. Thank you so much.
First off, thank you. I admit at first I was like, okay, how is this really different? But that was really interesting. As a fellow software person, I want to just give you a shout out that I did understand what you're talking about. That paper actually came up in my master's degree a couple years ago, so it is hot stuff. Question I had about the AI thing. I'm trying to remember the word, but we use AI a little bit where I work, but they had to pick a very specific model that was trained on very specific data for legal reasons. Can you speak to, like, first off, is your model something like built in-house? Are you using someone else's model? And where did you train data from? Do we have to worry about, you know?
Yeah, great question. So we definitely do not do that in-house. We are using OpenAI currently and Gemini, so we're switching between models. That's kind of the new approach, is to allow users to kind of pick which fundamental model is used. We are not training a model. We are also not fine-tuning a model. Both of those things are actually pretty out of scope for a startup like us. We are venture-backed, but we're tiny. We have 9 people, 4 engineers. So we are using the GPT-4o model right now. It's a reasoning model, which basically means like there's a feedback loop in it, and you kind of just ask the AI like, but why? And then it answers, and you say, but why? And it just keeps looping until it reasons itself into something interesting. So the magic for us is the instructions we provided and the context we provided. It is kind of amazing these models have got all human knowledge. So there is a fair amount of inbuilt stuff. We'll see in the future, but we're getting pretty amazing results out of that type of approach. So you do not have to worry about where it was trained from beyond what Google and OpenAI are training on, which is all human knowledge.
I'm curious, what does Circuitly look like in 10 years when you've been wildly successful? And what is the relationship with KiCad at that point?
Great question. One of the ways I think about Circuitly, and this probably goes to my game developer background, is I think about it kind of like a electronics CAD game engine. And Circuitly with KiCad is our first game. And we hope it's a hit game, and we hope everybody loves it. But we're interested in making more games on the same game engine. So as I look forward into the future, I really found Seth's talk at the opening inspiring, this idea of why KiCad's important, why it needs to live, and why it shouldn't be seen as a threat. And all those things resonated for me, and that's a big reason why I wanted to do this, pick KiCad first, and why I've used KiCad. So I hope that Circuitly's relationship with KiCad, whether it be sponsoring conferences, sponsoring development, contributing to the code base, I hope that we can have a great relationship going forward long into the future. But I also think there's an opportunity for Circuitly to have more personas than just KiCad. It would not be the kind of thing where you can open Cadence and save it as KiCad. I'm not as interested in that. It's more like being something that takes on that persona, Circuitly taking on that persona.
Thank you. I had a quick question about what it learns. So you've got 15 workspaces, for example, and you've got 15 designs in there. So when you're asking questions, is that per design, or has it learned all of your designs and so you can learn commonality? Thank you.
It's a great question. The real big answer is I don't know yet. What it does today, per workspace, only knowledge is siloed off to that workspace. A slightly longer answer is one of the things that we have in Circuitly that's not launched today, but we call them linked workspaces. So you may recall, workspaces are basically Git repos. And so linked workspace is the ability to have one workspace that links in the content from another. And if you think about it from Git terms, it's a submodule, a Git submodule. And that's how we get to shared libraries, being able to have a Git repo of libraries that you're referencing in. And at that point, there's question marks for us that we haven't answered yet, and we'd love to hear from y'all about, like, okay, so can the AI see the linked workspaces? Is that okay? Who gives permission for that? If you're using design blocks, which we don't yet support, but if you're using design blocks from another workspace, can the AI see those? Can it not see those? What does it mean to not see those? So lots of questions for us. Unfortunately, I have more questions than answers on that yet, but that's the kind of maybe giving you vibes about how early we are. We have one down in the front too.
So one of the possible uses, I think, for this is there are lots of companies that build microprocessors, widgets, etc., and publish reference designs. It strikes me that, for instance, you go to Analog Devices and they've got hundreds or thousands of reference designs, and they'll give you Gerbers or they'll give you something, but there's no clean way to peruse the reference designs without installing some specific tool. So it strikes me that marketing your public-facing web thing to corporations that can provide their design reference designs on your platform that are easily pullable off into KiCad or maybe other CAD translators into other CAD systems. I mean, I would probably, if you had that as a here are a bunch of companies presenting their reference designs on our platform, I might actually use that for my company. So that's just a marketing idea for you.
You're hired. Go on in the back.
Sorry. So I had a question regarding the AI upload. You mentioned there were 2 separate platforms supported. I've used occasionally these tools to try and understand. I'm not an EE myself, trying to understand things that I wanted to understand. I felt it's somewhat tedious describing these things in verbiage. am I correct in assuming that it uploads an image or a screenshot of the? Is that how it transfers the information? And then, if it's being uploaded as an entire image, is that in fact complete context? Because then you have the additional component properties, other sorts of information such as layout properties that might not be present on the schematic itself. How are you dealing with that kind of multifaceted feature of the design, both in terms of IP protection and the format that you're using to get the responses?
Walter, you're making me give away my secrets on a live stream. So great question. We do not give it an image. So we provide the AI with essentially, you could think of it as, it's not this, but you could think of it as like CSV data. So some of the magic behind like prompt engineering for AI is trying to get data into a format that you can hand to the AI and then trying to tell the AI what that format is. So it's pretty cool. I mean, it's sort of interesting. You're describing, we spend so much time as software engineers thinking about APIs and how do we call functions, and then here I feel like I'm basically describing to somebody in English how to call my function or what my data is. So we provided the data in a format that we cooked up that we've iterated on to figure out is consumable by the AI. But the AI doesn't know what it is, and so then we have to tell it. We have to say, oh, column 1 of the CSV type data is this, and column 2 is this, and then there's a net list. And as a human reading that, it's in English, but it's like a megabyte of that. It makes no sense. But to an AI, it loves it. So in terms of IP protection, though, we are feeding your data into Google. Now, they promise it's private and SSL and blah, 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 but this is where we have the no button.
I think I'm next. I'm interested in your comments about you needed to go through an analysis process where you derived the sort of conceptual structure of KiCad, and part of that was leading to a superset of the data model and so forth. How much effort was that? Was it easy to derive? And how did you capture that? And could that be fed back into the KiCad project in some way as an alternative aspect of documentation?
Oh, I don't think they want our stuff. But we reverse engineered it. So thank you to whoever did the big transition at 6 into kind of Khan's S expression stuff, like, oh, so much more rational than spaces. Thank you, Walter. So much more rational than spaces and tabs and whatever. So that made it really easy for us to generate a ton of conformance data that we do partially manually, partially automated, and then we're able to understand, kind of reverse engineer what is happening, because our deal has been to not use the source or look at the source to understand what's going on. And it's actually been really helpful, I think, for us, because we're able to kind of try to look at intent and not necessarily the long 36-year journey of why things are the way they are, but more, okay, what is it today and how does it work and why does it do that? And so, yeah, I'm not sure that would be helpful back into documentation. We also look at the documentation, which is, on the Creative Commons, so that's been, amazing. I know we're kind of probably running close on time here, right?
Maybe one more question. If you mentioned that you can import multiple versions and then export to that same version, can you? This is kind of a question for the internet audience, because I know someone's going to ask this. Can you open a KiCad 9 file and save it as a KiCad 6 file?
By accident right now, yes. In theory, yes. Of course.
That just multiplied your signups by.
Yeah. So the challenge there, as many of us know who have either written things that are working with the KiCad format, or I'm assuming the dev team is, there just are a lot of things that have been done. I'm only looking from the outside, but to rationalize things, to make things make more sense, to put content in the right places, like we used to have, kind of sheet instance references kind of at the end of a schematic file, and now they're embedded, and these things are you just see them, and it just, for somebody who's been looking at KiCad file formats for quite some time, I had a viewer program I did a while ago called Erie. It's just it's like a warm hug. But then, you have to support 6 still. So writing back and forth, some of that stuff is lossless, but the introduction of Bezier's, as I think Wayne mentioned, that was supported long before you could create it. But there are things like that that just aren't supported in certain versions. So it would become lossy. But that's, if people tell us that's something that they're excited about, I would love to put effort into it.
Okay, thank you very much.
All right, thank you. And special thank you to the organizers, Seth, and thank you, Wayne.
Okay, next up we have Chris Wilson. So while Chris is getting set up here, I'll give him his quick introduction. Chris has spent over a decade of his life designing low-power embedded systems for IoT and 4 years of product management in PCB assembly manufacturing. So he's taking IoT hardware products from prototype to production in numerous companies, from startups to Fortune 100 companies. So he would really love it if you would ask him about the first IoT hardware that he worked on that was donated to the Smithsonian. And today he is going to talk to us about how PLM can integrate with KiCad as it exists, and maybe how it could integrate better as it will exist in the future. Please give a warm welcome to Chris Wilson.
Okay, cool. Thanks, Seth. For those of you that don't know me, I'm Chris. I have a background, like Seth mentioned, in hardware engineering, and I did a brief stint in PCBA manufacturing. And now I run Common Ground Electronics, where I get to play with embedded systems and do cool projects for people. So I want to start with this quote. Some of you might be familiar with it. It's called Gall's Law. And it says, a complex system that works is invariably found to have evolved from a simple system that worked. And PLM can be a very complex system. I think a lot of people are familiar with it in kind of the enterprise environment. And so this talk is about trying to create a simple system that works with KiCad to set up a PLM workflow with the goal of being able to build open source designs. And so that has kind of a little bit of a unique set of constraints that I think a lot of people approaching PLM don't really typically come at this problem from. Goals. So I want to give you enough that you can get started with PLM in a weekend. And I also want to walk through a KiCad integration with a PLM tool called Aligny. And so we've only got 40 minutes. This is going to be a little bit of a quick kind of scratch the surface introduction to PLM. There's really no way to do like an exhaustive covering of all of the different aspects of PLM systems, or cover multiple PLM systems, but I just want to give you enough to kind of get a sense of what these systems are and how you might be able to get started using them with KiCad. Okay, so what is a PLM? PLM, Product Lifecycle Management, it's a process that combines best practices and software tools to centralize and structure product information over the course of the product development lifecycle. So that sounds kind of like a mouthful, but we'll kind of get into what that means. Every product that gets manufactured has a life cycle, and so it usually starts from defining the product requirements, going through a series of validation and testing phases, and then ultimately ramping up to mass production and going to eventually through service and end of life. And as you go through that life cycle, there's kind of this multiple cycles of this design, build, test, and learn cycle where you're iterating on this product over time. And each of those iterations have a lot of data that gets generated along with each of those iterations of that piece of hardware. There's part numbers that get generated, revisions, different parameters and specifications that are associated with each revision. You generate CAD files and drawings. You have a bill of materials that tells you what components go into that piece of hardware. And then you've got to manage suppliers, vendors, distributors. There's regulatory compliance aspects to that. So it's a lot of stuff that you kind of have to manage. And I think for most people, especially folks that are using KiCad, a lot of times this stuff gets stored in KiCad, in spreadsheets and Google Drive and random folders on your laptop and emails. And so there's like all of this kind of mix of places where this data is stored. And none of these places are really like the ideal location for this data. There's a couple reasons why it's not ideal. One is that product data is siloed. So for example, if you put manufacturer part numbers or vendors in KiCad, it's not super easy for another system to access that data. I mean, you can parse the files and pull it out, but it's not like there's an API where you can just grab the data that you need. And then that product data can also become outdated over time. So there's, manufacturers get acquired. If you put in Fairchild in your bill of materials today, and then you come back to those files later, you may find that they've been acquired by ON Semiconductor, or other things change about that manufacturing and supply chain data over time. And the last thing is that it's much easier to make mistakes with manual input. So you can see here, this was a design that I worked on a while ago. There was a copy and paste error between the value field and the MPN field, and we built the boards with SPI version of a chip instead of the I2C version, and nothing worked. So it's really easy to kind of make these small errors if you're storing data in KiCad and copying and pasting from one design to the next design to the next design. And that kind of brings me to kind of a more like philosophical slide about kind of what we should be kind of striving for here, which is that I think ideally your CAD design should really represent your design intent and not a snapshot of the current kind of supply chain data that we have today, which could change very easily tomorrow. So you can see there's like, in KiCad, you want to be able to say this design uses a 10K ohm resistor, plus or minus 5% tolerance, yada, yada. And then when you actually go to build that board, you want to be able to say that that part is actually going to be built with a Yago resistor with this part number, and we're going to purchase it from DigiKey or another distributor. So there's got to be a better way to do this, right? And people realize that, so they built PLM software. And there's a lot of options that you can pick from today. There's all sorts of different companies. Most of these are typically geared more towards enterprise deployments, but there's also tools for small and medium businesses and things that even makers and hobbyists can use. And so I will go over an example of one of those tools. So what does a PLM software do? PLM software is intended to be the single source of truth for product data. So it's a place where all of your part numbers are stored. It manages your revisions, your bill of materials. It has document control. One of the other things that it does is it enables teams to access that product data. So you may have a team composed of engineers and designers, product managers. Each of those different teams are looking to access information about the products that you're building. And then you can even have access for external vendors like your contract manufacturer, where you may want to be able to say, here's specific access to a design that your fab house or your contract manufacturer building your boards is going to have access to. There's also change management workflows, change history, so you've got kind of this audit trail for changes that are happening in the system. And then it also integrates with other tools, so PDM, MRP, MES, PIM. If you're sitting there thinking, what the heck is this guy talking about? I'm going to get into that. So there's a lot of these kind of 3-letter acronyms that when you first approach this are very kind of a little bit overwhelming. And so we'll talk about what these things are. So deciphering the alphabet soup. To give a very, very quick and short explanation of what some of these things are, product data management is an engineering tool, and it's designed to help, product data management, PDM, is an engineering tool that was kind of originally designed to manage and version design files, and specifically mechanical CAD data. And then you've got PLM, which is kind of a superset of that, intended to be a central hub for product data, approvals, lifecycle management. Then you've got material requirements planning, which is kind of more on the manufacturing side. That's got inventory management, purchasing, scheduling, and like demand planning tools. And then you've got kind of the big 900-pound gorilla, which is enterprise resource planning, or ERP. You probably have heard that term. And that's a tool that's kind of a superset of MRP, designed for kind of managing your business and supply chain logic. So that has tools for finance and HR and kind of running your entire business. So if we look at kind of how those things are kind of related to each other, PDM is typically a subset of PLM. PLM kind of grew out of PDM over time. And then MRP is typically either a standalone module or a module inside of a larger ERP system. More recently, on the ECAD side of things, Git has started to take over some of the functionality that a PDM would provide. So things like version control of design files. Some of that's kind of moving out of the PDMs, and you see people using Git and GitHub and GitLab for some of that functionality. And then finally, the integration of these tools. Oftentimes you'll have product data flowing from your PLM system to the MRP or the ERP system. So when you go to actually manufacture a product, your part numbers and manufacturing bill of materials, that will get transferred from the source of truth in the PLM tool down to the ERP or the MRP system. Okay, so let's get into the kind of the meat of this talk here. So this is really about integrating KiCad with a specific PLM tool, a tool called Aligny. And so I kind of want to start with like the end goal, which is what this is going to look like once we kind of walk through all the little pieces that you need to put in place to get this working. So the first thing is that we want to have all of our part data, all the product lifecycle data, stored within Aligny. So not having any unnecessary data stored in KiCad. The result of that will be that we get an automatically generated library of fully defined parts. And sometimes, historically, those have been called atomic parts in KiCad. What it means in the context of this talk is really that the parts have a footprint defined, a data sheet, a description, and an internal part number. And so that'll give us all of the information that we need to link those parts back to the kind of source of truth part data that is stored in the PLM tool. Okay, the kind of second piece of this is that we also want to be able to drive the creation of assembly bombs in the PLM tool from the schematic. So use the schematic as the source of truth for the parts that are going onto the bombs for like a printed circuit board assembly. Okay, so let's do a quick introduction to Aligny. I'm not affiliated with Aligny, but I just happened to kind of find this tool and found it to be really useful and capable of being integrated with KiCad. So that's what I ended up picking for this talk, but I'm hoping that some of the concepts that we go over here can be used with other PLM tools or You can even use Aligny with other CAD tools as well. Okay, so Aligny is a combination of a PLM and an MRP. So it has functionality of both, and it's kind of tightly integrated together so that you can use both the kind of PLM and MRP aspects of the tool kind of seamlessly within one user interface. It provides a part database, which they call the item master. It also has engineering change management workflows, quality workflows, and then on the MRP side of things, it has inventory management, planning, build management for managing builds of assemblies. It has supply chain tools, so you can do all of your purchasing and quoting through Aligny. And then it will let you also manage manufacturers and vendors, and it even has some kind of customer management stuff in there as well. So this talk is kind of solely about the very first piece of this, which is the part database. This is kind of the core piece that makes everything else in the list work. And it's basically the part numbers, the part data that drives all of the other kind of parts of the workflow. And I think this is the piece that most people in this room are kind of looking for as a starting point. Even if you're, a single contractor, you may not need change management workflows or, quality tools or a lot of the other stuff, but you might just be looking for a way to manage part numbers and bill of materials. And the part database piece in Aligny will give you that. Quick note on why Aligny, because there's obviously kind of a lot of options that we can pick from here. I was looking for a solution that was hosted. I didn't want to have to do IT stuff and host something myself. And I wanted something that was simple, that didn't require any custom development or a lot of configuration to get the system up and running. I wanted something that was kind of had out-of-the-box support for KiCad database libraries or HTTP libraries. I also wanted something that was ECAD agnostic, so something that could be used with KiCad today, but also Altium tomorrow, that wasn't going to be tied to a specific CAD tool. Something that I could play around with for a while, that had a free tier, that wasn't something that I had to kind of pay for initially, and was looking for something that had public access for open source projects. So I wanted to be able to publish a schematic on GitHub or on my website for somebody to download, and then have that schematic reference parts in this PLM tool, and not have that be a closed kind of ecosystem where you had to sign up for an account or log in or be part of an organization to actually access the rich part data that was stored in that tool. And then I also wanted automatically managed part numbers. And the only thing that I found that kind of really met all of those criteria at the time was Aligny. But there's also some work being done in PartsBox to try and get some of this stuff kind of built out. They just recently released support for HTTP libraries. So there's other things that I think are worth looking at now, especially as things change over the next year or so. Okay, so this is going to kind of move more into like a tutorial kind of description of how to actually get this set up. So hopefully you'll be able to kind of follow along. I'll publish these slides on my website. The link will be at the end of the talk. But you should be able to kind of follow along this and be able to get things set up yourself. Oh yeah, so the first step here, Aligny has a page where they have all of the kind of public organizations. They have private and public organizations, depending on whether you're on a paid plan or if you've got the free public account. And so if you go to this URL, you can sign up for an account, create a new organization, and then it'll ask you if you want to do a public or private organization. I would say you could start with the public just because it's free and it's kind of a good place to get started playing around with the tool. Okay, so the first thing that you see when you log in is the Aligny dashboard. Like I mentioned before, the focus of this talk is on setting up the item master. That's the kind of main parts database where you're going to store all of the data that we're going to be using for the KiCad library integration, and it'll be kind of your source of truth for part data moving forward. So yeah, single source of truth. It's a central repository that you can use not only in this system, but also in other systems. And it's backed by a relational database. So you get nice, like real rich relationships between the data and the tool. So if a part is referencing a manufacturer and that manufacturer name changes or the website changes over time, you'll have links that will be updated within the tool, and you're never going to have stale copies of data kind of lying around in your parts. Okay, so this is what a part looks like in Aligny. At the top here, you can see parts have a part number. They have a part type. There is a manufacturer, and this is a link to an actual manufacturer record in the system. And then there's a manufacturer part number and all the typical kind of additional, fields and data that you would expect from a part. You can have custom fields. So the fields in bold are the ones that come built in with Aligny, and then you can also add your own additional custom fields or custom part parameters for additional information that you want to store on a part. There's alternate part numbers. So these are other parts in the system that can be substituted for this part in certain scenarios. And then the last piece of this here is the where used section that will show you a list of assemblies that assemblies where this part is used. So if you're using this resistor on other boards or other assemblies that are getting built, you'll have a list of all the places in the system where this part is used. Parts have revisions. These will let you track changes to parts over time, and we'll talk a little bit more about this later. Because Aligny also has a MRP functionality, if you're looking at a part, you can also see information about the inventory of that part. So which warehouses have stock of that part will be listed in the tool. You can see in this case, we've got 1,000 of these resistors sitting in the JLC PCB warehouse. And there's also supply chain data about this part. So this is where you would actually set up the relationships between this specific manufacturer and part number and a series of distributors where you would actually buy this part. So here you can see we've got a relationship that says this part's available from DigiKey in different types of packaging formats, cut tape, tape and reel. You can also get it from Mouser and Newark, and also from LCSC. So there's a one-to-many relationship between a part in the system and the places where you can actually buy that part, and you can set up a lot of these different relationships in an easy way, whereas if you were trying to kind of shove this data into the KiCad fields, it's just much more kind of a manual process, and it's a lot harder to manage those records over time. Okay, so you obviously want to build out a big library of parts. How do you actually get a part into Aligny? Well, there's a couple of things you got to set up initially before you can create a new part, and we'll walk through some of those right now. The first thing is a part numbering scheme. So Aligny will automatically generate part numbers for you if you set it up to do that. And there's a lot of ways to do this wrong, where you can kind of end up in situations where, for example, with intelligent part numbering schemes, you end up with parts that kind of don't really fit in one specific category or another. So my recommendation would be, if you don't have specific requirements and you're just looking for a place to start, start with a non-intelligent part number scheme, just a series of numbers. Let Aligny generate those for you, and pick something around 6 to 7 characters long. That's kind of where the human mind can keep all those characters in your head, and start it with a 1, because if you start with 0, Excel is going to truncate those part numbers when you stick it into a spreadsheet. Okay, so part types. These are kind of like categories for parts. It's a way of organizing groups of parts in Aligny. And it also lets you set up behaviors and groups of parameters that are associated with specific parts in the system. So you can say, all chip resistors have power rating and tolerance, and all chip capacitors have a dielectric characteristic. So you can set those up in Aligny using part types, and then assign characteristics to those part types. And then the last thing here, and this is going to be important when we set up the part libraries in Aligny, or the part libraries in KiCad, is custom parameters. So KiCad's going to ask us for a symbol to associate with this part and a footprint to associate with this part. And this is how you would go in and set up a custom field. In this case, it's just a string that's called KiCad symbols, and it has a name and a description, and then a list of part types that are associated with that, so that you can say this field needs to show up on all of these different part types that we've set up in the system. Okay, so you've gone through, you've put 100 parts into Aligny, you're ready to go and place those into a KiCad schematic. How do you actually go about getting those parts that are in Aligny to show up in a library in KiCad so you can actually do something cool with them? So KiCad has this cool feature called database libraries. And the way that they work is it essentially takes data from a SQL database that has a bunch of records or kind of rows in the database that describe each part. And then each of those rows will reference an existing KiCad symbol and optionally an existing KiCad footprint to kind of merge all of that together into a part that gets placed into the schematic. And Eli talked about this in his talk. This is exactly the same kind of mechanism that was happening with the HTTP libraries. It's the same thing, just in this case, we're going to be using a SQL database to drive this instead of the HTTP libraries feature. There's a series of inputs that KiCad needs to actually make this work. And so we'll walk through each of these in detail so you kind of know where they're coming from. So the first thing that we're going to use is a SQLite database. And that actually comes from Aligny. They provide a tool called the Replicator. It's a Windows application that you can run that will essentially create a local SQLite database on your computer from your parts in Aligny. So every part that you have set up in Aligny will get downloaded and synchronized into a SQLite database in a location that you specify, and you can tell it to update that daily on a certain schedule, or you can also refresh it whenever you want manually as well. And the download link for that tool is right here. And if we look at the schema for that database, you can see there's a parts table, and then it has all of the fields and the custom parameters that we defined on the Aligny side. So anything that you had put in as a custom parameter will show up within this database. And then also, if we just look at the data in here, you can see that all the parts that we have defined in Aligny show up in this database with, here's the key piece, the part number associated with them. Okay, so I kind of glossed over, there's this ODBC driver thing. Eli mentioned this as well. It's essentially a abstraction layer so that KiCad doesn't have to know how to talk to every single type of database management system. It can just talk to this ODBC driver, and then the driver handles all the kind of messy details of interacting with different types of databases. So for SQLite, the one that we're going to be using here is this SQLite ODBC driver. You can just download it from this website and install it. And if you get everything set up correctly, you should see the driver installed in this ODBC data source administrator. I don't have a Linux machine that runs KiCad, so I couldn't show an example of that. But there's instructions at the end of the slides for Windows, Linux, and Mac OS. And the key thing to pay attention to is this driver name. We're going to use that when we get into the configuration file, because you've got to be able to point the configuration file to a name that matches that driver name. Okay, so the second piece we need is this database library configuration file. This is that KiCad_DBL. And this is a JSON file that tells KiCad how to actually map the fields in the SQLite database to fields on the symbols that it's going to generate in the KiCad schematic. So it's simple enough that I can actually just walk through the whole thing here real quick. This screenshot here is just showing kind of how I set up my KiCad library that uses this database libraries feature. So I have a folder called databases that has the SQLite database, and then a folder called symbols that has the KiCad configuration file. So I'll actually, since I'm running a little bit low on time, I'll skip walking through the individual details of the configuration file. This is all documented on the KiCad website. So all the individual details here you can look up in the KiCad documentation. But it's basically just this JSON file. It says look for the SQLite ODBC driver, and here's a link to the database file. And then you'll go through and set up which fields in the database map to specific fields on the symbols in KiCad. So skip through this here. One quick note, so I end up creating template libraries that I used for the symbols. So if you can imagine if you have 1,000 resistors, all of those resistors are going to use the same symbol when it actually creates the database libraries. And so these symbols have kind of placeholders for the fields that are going to get populated by the database libraries here. Let me skip ahead a little bit. One thing to note, when we generate the symbols, I showed that there was a link back to the part in Aligny, and the replicator database doesn't actually generate the database with that URL pre-populated. So one easy way to get that URL to show up is by adding a custom parameter in Aligny that has a link to that part. And then at the end of the slides that I'll publish, I'll show another method of doing that uses a SQL command to automatically generate that link instead of having to put it in as a custom parameter. Okay, so the last kind of piece of this puzzle is to add that KiCad database libraries configuration file into the symbol library table. This is just like you would add any other symbol library into the system, and this is what KiCad uses to generate that list of symbols when you actually go to place a part in the schematic. Okay, so now if you were to go up and hit the add symbol button in the schematic editor, KiCad would pull that information from the database, automatically generate this database library, and you can see here we get a list of parts that are with the part number associated with them. Those parts have a footprint defined, a datasheet link that links back to the part in the Aligny database, and it has a description and all the information we need to kind of connect that part in KiCad to the actual real source of truth in Aligny. The cool thing about this is that you can do parametric part search in Aligny. So you can say, show me all the resistors from Jago that are chip resistors that have a tolerance between 5 and 10%. And then you can search for those parts, get the part number you need, and then when you're in KiCad, you just go back into the search filter, punch that number in there, and it will filter the list to give you the exact part that you're looking for. You get nice links between KiCad and Aligny. So even in PDFs, you can click on a symbol in the PDF, and you get a link back to that part on the actual part page in Aligny. And then, how am I doing on time? 2 more minutes, okay. So I'll wrap up with this here. Once you've got parts that are placed in the schematic, you obviously want to build something. You're probably building a circuit board. So in this case, we'll walk through an example of how to actually take the parts from the schematic and import those back into Aligny to create a bill of materials for that board that you can then use in Aligny to represent the BOM for that board. And you can then share that with an external vendor, like a contract manufacturer, who's actually going to go and build these boards. So this is just an example, kind of simple design, one that I can fit the whole bill of materials on a slide here. So you can kind of see there's your basic bill of materials export from KiCad. The main thing to note is that it has an IPN column, and all of those part numbers are the same part numbers for the parts in Aligny. So when you go to import that CSV file into one of the part assemblies in Aligny, there's this mapping process where you'll map the part number column from the CSV to the IPN column in the CSV file to the part number in Aligny, and it will automatically match up all of those parts, import them, and create that bill of materials in Aligny for you. So it's kind of this nice workflow of placing parts in the schematic based on the Aligny database, and then exporting the bill of materials out of KiCad and using that to create the assembly BOMs in Aligny. So I think that's a good place to kind of wrap up. There's some additional things here that I don't really have time to cover, talking about best practices for revisions. You can download the slides and check those out. And then a couple limitations that I just want to kind of mention before we wrap up here. So there's currently no way to place different schematic symbols for a single database part in KiCad. So one reason why you might want to do that is you have an M.2 connector. You want to be able to use that with SparkFun's micromod system or PCI Express M.2 specification. Those symbols have different pinouts, and there's currently no way to kind of pick which symbol you want while keeping the same part number and same footprint within KiCad. And then the second one here is really similar, being able to pick from multiple footprints for an existing database part. This technically should work, but I ran into some bugs that haven't been resolved, and I'm not exactly sure why it's not working in some cases, but there's an issue here to track that. That should be a supported feature and just didn't work when I tried it. Couple usage limitations on the Aligny side. So the free public tier, one of the big things to point out is it's limited to 1,000 parts. So if you know that you're going to be doing designs with a lot of parts, or you have a parts library that's bigger than 1,000, you can definitely upgrade to a paid Aligny workspace, but just kind of a note on the limitation for the free tier. This last note is just a note here saying that the replicator database that gets generated by Aligny only has a single parts table. KiCad database libraries has a feature that will let you map different tables in a database to different libraries on the KiCad side. And so this is just a limitation on the Aligny side that it only generates a single parts table. So when you do this integration, you end up with a single library in KiCad that has all of your parts, but there's no way to separate that out into like a library for resistors and a library for capacitors and separate libraries. So that is one limitation with the system. A couple additional tips. You can check these out if you download the slides. And that's it. Thanks. Oh, sorry.
Hi. You mentioned early on in your slides that part of what you're trying to capture on the schematic is design intent.
Mm-hmm.
But it seemed like the way the talk went, you went in the direction of suggesting that what you're putting on the schematic is a super specific part number as fully defined in Aligny, which seems like that's the exact opposite. So I'm wondering if there's some portion of this that where you can actually use design intent on the schematic and map that to here's the current selection we chose to fulfill these, and so later when the when that goes obsolete or whatever, it's clear the parameters that need to be fulfilled for some replacement part.
Got it. Yeah, that's a great distinction you're making. So Aligny has a limitation that the way the tool is set up, it only allows a part number to be associated with a single MPN. Some other PLM tools have what they call approved manufacturer lists, which will let you map from a single part number in the system, like a generic part number, to multiple different parts from different manufacturers. The way that Aligny approaches that problem is they have, I think I mentioned it earlier, but there's that alternate parts association on every part in the system. So you're right. In this case, you would be placing a specific IPN in KiCad that's associated with a specific manufacturer part number. But then once you're in Aligny and you're going to go generate that manufacturing bill of materials, there's a way to export a report alongside your BOM that you could give to a contract manufacturer that says, this is the part that's been picked for the kind of prime part that's been picked for this assembly, but here's a list of approved alternate part numbers that can be used separately if you can't purchase the part that was intended. So it's not a perfect solution, but that's the way that Aligny has chosen to kind of implement that in their tool. Does that answer the question?
It's kind of disappointing, actually.
Yeah.
Because what happens is that over the years, because the design intent, what happens is that over the years, because the design intent was not captured, but rather a specific part number, every time the thing goes obsolete, the person doing the replacement doesn't know which specs are crucial. So we get ever escalating specs. And so the products improve by having higher and higher spec parts put on them. So,
yes.
I mean, this one doesn't solve that particular problem. But
yeah,
that's
I think
fine.
the way that there's two ways that the design intent gets captured. One is the description of the part gets copied over into KiCad, so you would see anything that you put in the description field would be there to kind of capture the intent. And then you can always look up that part in Aligny to see what are all the parametric specs for that part that was originally spec'd.
Right, but you don't know which of those specs are crucial.
True, that's true, yeah.
Yeah, the original specs need to stay in the schematic design and somehow get managed. Everybody has the same problem.
Yeah. But I think you would have that problem anyways, because if you, let's say you pulled in a part that has, 5% tolerance and whatever else in those parameters, and you place that in a KiCad schematic, unless you make a note saying all of these parameters are important, or these two parameters are important and these ones aren't, you still kind of have that, it's still a little bit ambiguous about what was the critical parameter for that part versus what just happened to be accidentally imported as well along with it. So I think that it's a documentation issue partly that says this is the thing that was critical for this design if you really want to capture that in the schematic.
Well, I would argue it's a problem with formalizing the process the engineer uses to specify stuff.
True, yeah.
It's like required versus other specs that came along for the right.
Yeah, that's a great point.
And so, like, that's part of product lifecycle management or product documentation management. And so there's a niche there to be fulfilled yet.
Yep.
Quick question for you. What's your thoughts on using Aligny with intelligent part numbers for the internal part number system?
Yeah, so
pros, cons, etc.
Let me go back here. They have a couple options. Go back to the part numbering scheme.
I mean, I've seen organizations flip-flop back and forth between those philosophies, and
yeah,
big area of argument.
There's pros and cons. Aligny has a limited subset of options for part numbering schemes. So you can do completely manual. You can do auto increment where it just increments numerically. You can give it a manufacturer prefix. So you can say all the parts with a specific manufacturer have the same prefix, or a part category prefix, where you say all resistors, all capacitors have the same beginning prefix.
Capacitors, types, and
Yeah,
subtypes.
right.
Yeah.
And I think different organizations have different requirements that will drive what your part numbers need to be, whether those are customer visible. In my experience, I have seen intelligent part number schemes kind of end up with a miscellaneous category where things that don't quite fit the other categories go to live. And I've never seen it work perfectly. I think a safer option is just kind of these generic unintelligent part number schemes, but you may have requirements, customer requirements or marketing requirements that kind of push you in a certain direction, or even manufacturing requirements where your manufacturing team might want to have, you know, those prefixes so they know this part is supposed to be a resistor, and you know, they can do some kind of sanity checking for things.
Great. Well, thank you so much.
Yeah.
Okay, thank you. If there are further questions for Chris, he will be out in the coffee reception. We'll have a quick break, get up, stretch our legs, and we'll come back for our final segment of the afternoon.
Oh, really?
Yeah, I mean, I'm not obviously a professional enough at this, but like, I just thought that I kind of lost my opportunity, which wasn't even at
Lost your opportunity what?
with Octopart kind of.
Oh,
that wasn't
yeah.
even. It's not even what all this does. You know,
Yeah,
it's way more. But,
yeah.
it's super cool.
I mean, the problem I see it is, let's say I'm doing a prototype design.
Mm-hmm.
I've got a trimming resistor that's 1.03K. I find I'm gonna send it to JLC PCB to have my prototype, so I stuff the LCSC part number in there.
Mm-hmm.
I change the value 4 times in the process, and the last batch is perfect, and then I give it to manufacturing, and they're gonna put DigiKey, Mauser, Jaego, you know, whoever part numbers in there, and now, you know, it's almost like for things like generics, like caps or stuff like that, you almost want a wizard. You want a wizard that says, I want to place a precision resistor here, and if it's in the part system already, it uses it. If it's not, you know, that's the step that's always screwed up right there.
You're saying a wizard that would help you to
For instance, I've got, you know, every 1% part number except 1.03K, right? And I'm using that now. Well, all the other part numbers have got DigiKey, Mauser, and Jaego, and somebody else in them. So now that I have a 1.03K resistor, there's going to be a standard part number that I would, you know, I'm not going to go pick Barnes if everything else in my universe is Jaego, right? And so Jaego has a format for a specific, you know, you can, from a Jaego part number, you can determine what the value is, and from the value, you can determine the Jaego part number programmatically. So when I add that part, you know, as an engineer, I should put my value in, and then the company standards for saying, okay, he wanted a 1.03K resistor.
You wanted to generate the Jaego
I
part
wanted to
number.
generate the Jaego and the DigiKey and the Mauser and all that other stuff, because someone's got to do that, and it's algorithmic. It can be algorithmic for generic, a lot of generic stuff.
You're right. A lot of the manufacturers have a
until they don't. So when you're first putting parts into Aligny, is there a semi-automated way of doing that where you're using Excel exports or KiCad exports?
You can do CSV type import, and you can also do API. So if you write a script and you write stuff in another system, you can write something that will migrate all of the data over using the API, or you can export it as a CSV and then import it in. Both of those.
I built, what was nice was KiCad, once I understood how it worked, we probably had it working. The footprints, basically, if you import into KiCad, I think some of the layers get flopped, like a lab layer and something else. So I'm having him write a script that goes through the file and says if it's on.
That's what I was asking about, because I You need to have automation to like for example, Allegro uses regions for things like recording. I don't want regions. I want outlines. So I had to create a script to go through the library and find every region on the mechanical layer and convert it to an outline. But not if it's a cutout and not if it's like, right? And so like, and ChatGPT is useless at that stuff because it's Delphi script and the documentation, there's a lot of documentation outside of the website.
They just haven't.
Things kept changing and they didn't update the documentation. So like at version 19 they went to an arbitrary number of mechanics and there's still, most scripts use enum data type for the mechanical layer.
It's broke. It's like,
You can't use it. But once you realize there was one knowledge base article that was translated from Russian to English that roughly indicates you can iterate every layer using a numerical index.
Let me turn on Hannah's special lights.
This is too bad they didn't. Well,
And there's undocumented PCB server functions that are helpers to get the layer number as an integer from the name or things like that.
Let me just confirm the number.
probably like the thing about KiCad, I mean, not that you still have to do work, but it's at least you're not totally blind. Like, so all my 0805, so Altium has a thing in their IPC generator where you can give it a spreadsheet.
Yeah,
And I made
I've used that.
all of the
Cesium
0805s
is
with
down
all the
again.
heights and all of the IPC
Bonus points for
densities,
having it
but
be back up to the next
the thing when I bring to KiCad, the ref is
Down here in San
I want
Diego.
it on the fab layer to be the right size
Overlaid.
in the middle.
Yeah.
So last week Nathan, he figured out, he wrote a Python script in KiCad that auto compute and said, okay, now make a new bounding box. So we're making a scrubber that it's not gonna be perfect, but it's gonna get, it's 90% there.
I think
but
I'm talking first and then
at
we're gonna do
least
this.
He's wicked smart. At least it's documented that you can pull stuff out of that file with
Four.
Okay, I want
Just
something
4. So we'll remove the side ones.
I agree with that.
I want them in fab layer, I want it in the middle. It's not perfect, but it's close enough where I'm not 100% happy, but I'm happy enough to fix it. But at least you have a shot. Like it's like you don't have to dig too deep for the docs. But it's still a work in progress, but it's getting productive.
They second too.
Yes, it's magically called your break time. Because I was asking Eli for a set of understanding on something here, and he was explaining to me. No, we haven't had a chance.
Use your schematics, or don't make me watch a murder.
Yep.
That was my first design review.
There's almost two levels. There's review that, okay, not perfect, get ready for those things. Usually actually, even the footprints. But then there is, let's actually work backwards from the side. One thing I've been doing is there's like a main library, but establishing the first Rev A, you use a local library, and nothing can go in the main library until you put one revision with it. Because in KiCad, it's actually pretty easy to use those local libraries, so they can eliminate like the sandbox. And then, once you validate, because like I have a rule that there's a couple other colleagues that if they send me something, I know it's wrong.
Did you use
Because
No.
they're, well, they're asshole one too, but the KiCad libraries are pretty good, with good filters, but I
See you
don't
on
know.
Monday?
Or maybe it did work, but they know the difference of the requirements, so I wanna.
So our library here used to take the AB division.
But, like, if you
arbitrary parameters and
You probably could.
yeah, and just
It's the same. I mean, that's basically what we do with language. It's just like extra.
because there is a difference too if you build it 10 times versus it's been soldered 10 times.
Right. But for that, that's sort of the IPC style language. It's like, okay, you're picking the one that you're not.
And even that naming, it's more of like, I care, did it, like, 'cause even I had IPC things that were goofy, because they were, it's like, I think everyone, and this is where, like, people are pure in software, come PCB design saying, well, we use libraries, like, I'm like, well, you can test something in a millisecond. In PCB world, you might not know for 6 months.
Right.
Like, it's true, so you just look defensive. You're like, and I also, here's my other rule, all right? The ultimate decider, like, who gets to approve, is the person who stayed the weekend with the exact link straight to trace. Like, because when you do that enough, it sucks. And you learn to avoid it. In other places I've been that have a librarian, I'm like, I appreciate it, but are they the ones staying the weekend? If you're the one staying the weekend, you make sure it's right, because you're.
I've seen enough librarians where it's like, if you're just trying to.
Yeah, but I think it's exponential too. Like, once you start getting enough, it sucks when you're one track. But I'm also of the opinion that it's somewhat useless, except for like, I like the 0603 jelly beans as you're building that filter, but the switching converter, like, once you build that once, if you use it again, you kind of copy the whole schematic of Delta, so like, you don't pull the LT yada yada from the library, and maybe you change the resistor, and so, like, to me, what I'm, at least with KiCad, how they have these design blocks, like, I'm kind of, that to me is,
reduces the importance of libraries. Just have a local library.
and I want the thing that should get a lot of review and you get is that library was simple, and that's the thing that you want someone just, because to me, like, even with PDM, I wasn't frustrated, because it's so rigid, you have a search.
Oh, okay.
Oh no. I kind of know every library design, they have it history, but how does a new say, what's,
Like, are you able to keep in contact with the satellite still? Or?
I want to be able to, like, use an LLM privately on our own database to say, hey, kind of, I want to do this. Yeah, or just, I want to do a switch and power converter, like, what are some design, I remember things, but that doesn't help me, we just started next week. That's where I see the value of, like, the open nature of the file format.
I've been seeing them the next week compared to since last
I don't want it rigid
changed the
like
board
most
like probably
PDMs where it's like, I want to
I'm a revision D right now, and I started doing layout today.
Just to know where the repos that have
done next week. The idea is like next week I'll have the bomb done and the river.
That's at least my vision.
Because
I'm seeing it come together. Because that,
I remember John did his thing of peripheral
he's just screwing it
with like a WizNet.
The execution of
he finished it,
isn't that bad.
so he's gonna get it sent off next week.
Should be on the
If not,
schematic.
has sent it already. But
Take a while.
this summer we're doing.
If you're by yourself, you always like, this. It's nice to have a team, but then you might have some disagreements, and you spend a lot of
At least for the first batch.
Once you decide, it's like, okay, make
The hardware I did select was great. Really awesome.
The other fun part is what goes on the
We're selling using ALC for our manufacturer. And so if we want to order parts that they don't have,
maybe that's on
they
top,
have to.
like,
Yeah, so first you gotta ship it to them, and so we decided, okay, let's change it. And I had to redo the design again with those. It wasn't super hard, like just take
hardship of finding, oh, this chip was docking the right way, you need the extra resistor here, there's this weird aspect. How do you capture that? No, so everyone knows, yeah, yeah, and make sure you have a big, so one thing I do, I do this somewhat as a joke, but I did this about 20 years ago. Let me see if he'll just come up here.
Hundreds of dollars per board is what you'd expect for.
And I actually have a way of
here in the US.
see if I translate it.
Once you've gotten that board,
It's not translated.
it's much cheaper to have a
I come bugs it.
that first board.
I don't know why.
Why is that? Because they need to establish a
Bugs it. I'm gonna have to bring up Valentin to know.
Okay, so
I just brought him into the KiCad image. So okay, so here's a typical thing. Is like you Rev A. You have bugs in it. You have patches. You go to Rev B. What I noticed when I worked for like the Navy lab, they were like, we want top page with like patches. Yeah, but it's so dense. It's like I need some dynamic range to determine what's really important. So like I was kind of the road. We need a human factors analysis of how do you indicate what's important more than just and so I noted bugs. And so I wanted to things that are so important that I want your eyeball to go into directly to. Oh yeah, here's one. I know Bugs is on here because I was terribly embarrassed that I did this. That's Bugs. He actually gets bug 1, bug 2, and you make a bug bomb. That comes out of it. Like this is a board as a rush. I flopped. I think I did it here. I also did the debug. This didn't flop because I was under such duress to get it out. But so Bugsley, and he's just funny, and it's not meant to be like he's someone. It's meant to be okay. When you're in this Rev A, Bugsley's there to say, okay, look at me, I'm big and ugly, like. But the real intent was a way simple you could draw, like it's annotated, so you could probably create a bug bomb that'll have a description of the bug. So it's not quite a database, but you get a.
So the way we've been tracking design is actually more of a software approach where your main branch will get at least just the latest version of your design. So like saying, I want to have text with this. Whenever you go to fab, that's like that fab version. And then any commit you make off of that, you can annotate with reload.
Yeah, and that's.
And then you can add attributes that you can add and say, okay, this is bug 1, and then just play it.
Yeah, so it's interesting, like this hardware is a little different that you end up having to come up, let me see if I can find something. Yeah, this one is, this is audio focus. So one thing, before Git was a thing when I knew Subversion, there was some debate over, if you go from like Rev A to Rev B, should that be like a new branch and it should be in the same folder? Like in software.
Wait, Andrew, I feel like I owe you a bunch of work on Orson stuff. I'm Alnus, right?
Oh my God, Alnus! I didn't recognize you.
I'm so sorry, I didn't recognize you earlier too. Yeah, so I'm very sorry. I know I promised.
You are a terrible person.
Yeah, I am. Really awful.
Okay, folks, we're about to get started. Just a quick note, if you were here on Wednesday for the training session, I have your certificates. I am down in the bottom right here. Please do stop by and grab your certificates from me before you take off. Please do come by and grab your certificate, and we do want to make sure I get that to you. Not everyone got them at the European conference. I ended up mailing them out, and I will tell you, my post office did not like mailing certificates. They went out 3 times and came back twice. So I'm hoping that the third time they actually reach there. So I would like to hand this to you directly. So without further ado, our final talk. So I say our final talk because following this, we're going to be doing the KiCad Roundtable discussion. But our final talk today is going to be from Andrew Greenberg. He is going to talk to us about actually useful schematics. So I appreciate the "actually" in here. Andrew is a physicist and electrical engineer by training, but today he has spent over 20 years in medical device, embedded systems, and aerospace engineering fields before becoming a senior instructor at Portland State University. So please give a warm welcome to Andrew Greenberg.
So I'm not going to go long. In fact, I hope to end early and go super fast, and I'm going to talk really fast. I invite you to yell at me during the actual talk, because that will be interesting, because I have a lot of really silly opinionated things, and I'm really curious to see what you think. So I've done a lot of things. You guys have all done a lot of things. Solar cars, satellites, rockets, medical equipment, except stuff like that. The one thing the talk I actually want to give is this one. Which is we have an entirely open source CubeSat kit that we pioneered at Portland State University that's built on KiCad. And so it is, just going through it, there we go. You might notice the purple-ash park boards. That's the 1U CubeSat right there. That's the Onshape model for it. And we have a 1 through 3U, and everything was designed by undergraduates, which means everything catches fire and everything is terrible. And we've gone through a bunch of different revs. We have a back plane, and we have all these different things, and blah, 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 blah. Wouldn't that be a cool talk? Yeah, nope. All right, so who works on open source projects? All right, this is for you. I am sick of your stuff. And you need to shape up. I've been in industry for a long time, and then I started working as a senior instructor, which I've really enjoyed. But one of the problems is that I have to teach students KiCad. And then I have to work with these industry capstone projects when they're seniors with all of these, mostly open source kinds of things. And so I have students who are trying desperately to use open source projects like Arduinos or whatever. And I have to deal with, like that was last quarter. These are all different. Some of these have circuit boards. Some of these are proto boards. Some of them are really cute. Like they have little LED lights. This is a dice that you roll and charges on a little base station. There's some music stuff. These are all KiCad projects. And all of the schematics are garbage. Capstones. So what I hope to do today is just talk about schematics and talk about all of you working with me to make your schematics better so that when my students use your stuff and when I contribute to the open source and when you come to our open source, we have some, what's the right way, beautiful schematics, useful schematics, schematics that we can look at and use right away. Okay. So you all know that it's a schematic, nodes, and nets, and you have a net list, right? We all know that. We all use KiCad. So there you go. Yeah? I mean, we're done, right? So just to push this a little further, who knows about Skittle? Yeah. So Skittle is hilarious. It's Python code that makes your schematic. So screw your schematic. Yeah, no, So, okay, but why? Why do we use visual schematics? Well, because you've got 4 billion years of eyeballs behind you. And yes, you can see tigers in the grass really fast, but you can see other things really fast. And so that's why we use schematics. It's a visual language. You ready? What was that? You took one look at it and someone said that was a LED and a resistor and that's it. You didn't even have 100 milliseconds and yet you saw that and you parsed it, right? So you ready? So that was impressive. Let's try it again. You ready? I'm gonna go slower this time. What was that? Come on, guys, what was that? You guys are electrical engineers. Come on, let's go. It's a voltage divider. So this is why schematics matter, which in less than 100 milliseconds, you could parse a voltage divider with a capacitor filter, but you could not make heads or tails of that. So I want blink-like comprehension times on our visual schematics, because a good schematic should standardize, simplify, modularize, and communicate function, all in a blink of an eye. So I want to go back and talk about stealing stuff from other people. So if you've not yet read The Visual Display of Quantitative Information, thank you, from Edward Tufte, you need to go pick up a copy. I'm sure there's free PDFs on the web, but it's actually a beautiful book. And it's really about graphic design. It's about the fact that white space is the most powerful separator. Yes, we'd like to put things in boxes, but boxes are visual noise. We have too much junk, and the more white space we use, the faster we can see stuff. Visual flow. When you read a schematic, your eyeballs go certain ways. Are you actually taking that into account when you lay out your schematics? And there's meaning where you put stuff. In architecture, and the dang computer science people stole this from them too, we have this idea of the design pattern, an easily understandable modular repeating pattern. So for us, it's not necessarily a function call or a binary sort or whatever. We have these ideas of the voltage divider, of the follower, of the inverter, right? These are things that we should be using, and we should be building these design patterns so that you can blink at something and understand what's going on. So if you remember the Stranger in a Strange Land, the idea of grokking, right? Understanding what's going on in a blink. That's what we want to get to. All right, so what's that? Yeah, it's differential, right?
It's a dual op amp.
Yeah, it's that.
With a horrible TI.
Yes, yes. Shh, don't say that. All right. So the point is that this is a perfectly valid schematic, but it's not useful. It's not a design pattern. It doesn't allow us to see what's going on in the blink of an eye and see if it's correct or not. So that's where I want to get to. I want to get to something that communicates data and power flow, is simple and clear, and obsessively well labeled. Now, if you just do schematics for yourself, I don't care about you. You can do whatever you want to do. The only people I care about are the people who are going to actually publish their schematics, and we're going to read them, right? So I'm going to say some controversial stuff. If you just make schematics for yourselves, you don't get to respond to me. But if you publish stuff and you disagree, I want to hear. Okay. So the first thing is that stuff flows left to right. Amen. So thank you. So inputs on the left, outputs on the right. If you can. It never actually works like this in practice, but you should try that, right? And if you can't do that, you should follow a path. And you should follow a path that has enough white space to actually let your eye follow the path of the data or the power, right? So here's an example. It's not a great example, but you can see we have a radio chip right here. And you can kind of see that you can see little arrows right there. So you're kind of going through here, going through there. There's an output over here. So you've got your inputs to the radio over here. It's bidirectional, so everything's kind of messed up and everything. But it's at least you can track it with your eyes. The second thing is stop it with the power symbols. Grounds point down, negative supplies point down, and positive supplies point up, always. Please don't do that. Another thing is, this is really, really lazy of us. A lot of us use the actual physical packages of the part as the schematic symbol. Do not do that. Yeah. And the reason for that is because that's useless, right? It doesn't tell you anything about the actual electrical connections. What we want is this. We want to know where the power and the ground is. We want to know where the inputs and the outputs are, where we connect the crystals. This is just useless. You know, that's what the layout is for, literally the layout, right? So occasionally I'm wrong. And sometimes the actual schematic is the layout, but it's very RF-y and very weird. That almost never happens. Use white space. So right now we tend to put all of our little circuits in boxes and things like that, and that's fine, but that's not as good as using white space. If you have a really tight schematic, use boxes. You want to be able to group things so that the person who's reading your schematic know that those symbols are together. Please label the blocks. I think I'm missing a slide. Hold on. No, I'm not. The other thing is please minimize the number of sheets. On the other hand, don't minimize the number of sheets. Don't be Olamex. I love Olamex. There is no reason that you need to fit all of this on one page. We are not printing this out anymore, right? So the idea is let's use the minimum number, but at least let's group things like the power supply and the connector and things, right? So we always use 11 by 17 sheets because we're not going to print it out, but you know, it's up to you. And if you're running out of white space, just add a sheet, right? Group, but don't make me page through 8 different sheets for no reason. Block diagrams are super great on your root page, and now we can actually make block diagrams that matter. So with hierarchical blocks, so this is an actual root page. It's a battery charger module. You've got external power coming in into a charge controller that goes out to the host system. You've got a cell interface down here, thermistors down here, and a microcontroller that controls all of it. And this is a block diagram. It's not a great block diagram, but it's a block diagram, and it's part of the schematic. I think that's really cool. And I look forward to seeing how far we can push this so that our block diagrams become useful. In general, please use wires and not labels for connections. And this goes back to the visual nature of schematics, which is I can see that this is connected to that in way less time than I can find where VN USB is around this. And yes, I can hit Control F, but now I've just lost 20 seconds hitting Control F and zooming around to find it, where it took less than 100 milliseconds for me to just see that this was connected to that. So when you can, use wires. You can label your wires. We love labels, right? But use wires when you can. Sometimes you can't, right? It's off sheet, or it would be really awkward to run like, you know, this one label, one wire all the way around. That's fine. That's what global labels are for. Please do use labels. They're really helpful. And that's just because you can just reference them. Again, you know, we're gonna look at this flow, but wouldn't it be nice if that was a label down there as well, just so we could see exactly, and then we could match it up and just do double checking, right? All really, really quickly. In general, please don't do this. Don't use labels for off-sheet labels or labels that jump across between symbols. And the reason for that is that's text. I can't tell what that is. That could be anything, right? That's a global label. That's a label that's going somewhere. So please do that. Also, please turn on the sheet references, the intersheet references. You can go to schematic setup, blah, 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 blah. And now I know that those two things are going to sheet 1 or sheet 5. And I can jump around, and I know sheet 1 is the connectors. It goes off to the connectors. So I immediately know that without having to look it up. Please use actually useful power supply names. VCC is not useful. VUSB is very useful. 5 volts might be useful, but VUSB might be even better, because who's actually read the USB spec? Yeah. You know what's going on here, right? USB is 4.5 to 5.5 volts. It's not 5.0 volts. It's not guaranteed. The other thing is try and use the sort of standard engineering paradigms, right? So we've got min, typical, max, right? So I've got, here's my USB voltage. It's typically 5.0, but can be minimum 4.5 to maximum 5.5. And I'm typically pulling 35 milliamps, and at the most I can pull 500 milliamps. That statement right there is so much more information than 5V, right? That actually gives you actionable information. Even just having a text comment that says a 1 amp supply, right? That already tells you a lot about what's going on in this circuit. So here we go, we've got V-bus, it's 9 to 19 volts. Oh my God, okay, I'm really glad I know that, right? V-bus is not useful, but 19 volts is useful. And that goes off to 3.3 volts at 2 amps max. Okay. Right? Those are clues. Those are clues so we don't make fire eventually. Undergraduates love fires. All right. Please use the text feature. Use all the text features. You guys are artists. You are circuit artists. Please continue the artistic tradition by marking up your boards. For example, tell us what we should expect at test points. That would be nice. The other thing is, when stuff is weird, please leave us a note. Pins 11, 12, 13, 21 are intentionally left floating. Pin 9 and 10 are both inputs and are intentionally shorted. WTF? That's okay, but that's fine. I said it, so now you're like, okay, so that really is a thing. All right, that's fine. I've called out. Now I don't necessarily have to go look, because I've told you this weird thing is right there. Also, do you see that right there? Look at that. That's telling us which way our RF is flowing in this bidirectional radio. That's really useful, because now I can trace this out and I can see what part of it is the receiver, what part is the transmitter. And that's just a little arrow, right? These kinds of clues are really important to the person reading your schematic. Okay, I have to show you this because this is literally the worst schematic I've ever seen. It's so bad that it's kind of good. So this is the evaluation board for the MAX 2769, which is a SDR GPS system. So they literally did everything wrong. I'm so proud of them. I think it was a grad student at Maxim. All right, so check it out. First of all, what they did wrong, they made it a package, right? That's not useful. Then, actually, you want to see something fun? I think I have it open. There, that's the same chip, right? You can see the digital inputs over here, the RF inputs over here, the digital output over here, which the power supplies are. Now, here's really fun. Where are the power supplies? Okay, where's VCCIF? Is it right there? Yeah, it's a net label. That's exactly right, because that's ground, right? It's bypass to ground. Those are bypass caps. So we have to go look at VCCIF. So now instead of knowing where VCCIF is or what the voltage is, I now have to look up VCC. Sorry, I'm just taking you down this horror. Oh, there it is. Oh, but it goes to VCCA. Okay. So I'm going to look for VCCA. There it goes, there it goes, there it goes. It goes all over the place. Oh, okay. It's a max 8510. It's a 2. Oh, they don't even tell me what the voltage is. I happen to know it's 2.85 volts. Right? But now I have to go look up that sheet, and that data sheet, and I have to go find out it's a 2.85 volt. So I've just wasted 5 minutes trying to understand something that should be absolutely trivial. What I should be trying to understand is all the weird RF magic going on, right? But no, instead I'm dealing with this damn schematic. So, and it actually just gets worse. I love this thing. So this is kind of fun. This is an old style tech Series 422. And what I just love about this is it's got like, it tells you stuff. This is the oscillation frequency thing. It's hard to tell on the screen, but that's a little image of the scope output. So that you know when you look right there at 0.5 microseconds per division, that's what your scope should look like when you probe it. That's so cool. And it's really nicely laid out. And I would tell them, hey, you guys, instead of using 0 volts, you need to use ground symbols and things like that. But it is beautiful, and it was hand-drawn, so I forgive them. All right, schematic checklist. Make sure your power is distributed through supply symbols. All supplies point the right way. Important nets are descriptively named. All these things, right? So I have linked to this an actual checklist, and I invite you to grab it. At the end, I'll give you a QR code so you can get directly access to this. And what I'd love to know is I'd love to have you guys look at this and add comments. Comments are turned on, and let me know what I missed. Right? There are some things on here that are really more like almost like ERCs, like MOSFETs oriented correctly with respect to the body diode. Who's done that wrong? Oh, come on. There's more than of you than are doing that. That kind of thing, right? Like, you know, make sure you've got your bypass capacitors. Design for fail, group components in separate modules, power supplies, that kind of thing, right? So this is a checklist that I've run through several hundred undergraduate students to good success. And I would really love your feedback on what I'm missing here and what you would do different. With you want to go around it, or what are you saying? Oh, no more than 3. Yeah, okay. Oh, okay, that's good. See? Right. Well, that's up to you. Good. That's it. I wanted to be really fast, so I just cruised through this. That's the thing. Please go ahead and grab this. That links you to this Google Slides, and then from there you can get access to the link to the checklist. And it's got my contact information on it. I'd love to hear from you. Anything that you can tell me about what your pet peeves are for schematics and for this kind of open source thing so that we can understand each other better, I would love to hear. And then eventually we're starting a website and we'll probably start posting these rules and try and kind of get it out there a little bit more. And I'll post that in a KiCad forum or something like that eventually when that happens. Anyway, that's it.
Anyone have any questions?
Oh, I thought they were going to be. It's going to be dangerous.
I love this, and I really appreciate what you're doing. And I'm curious, just because this was one of my pet peeves, and Eli and I were just joking about it too. People need to freaking read and understand IEEE 315. You can download it from a million places. For free. It's been around since the 70s, but it standardizes every electronic and electrical symbol for use on schematics, and everything has a purpose and a reason for existing, including the circle on a transistor.
It's like a tuxedo.
If the transistor is in a discrete package, the circle indicates it is in a discrete package. It has a meaning, and it must be used, and people freaking leave it out all the time. It pisses me off.
Just a quick note, KiCad does not endorse pirating IEEE 315. You can purchase it at the IEEE website and support IEEE. They're a wonderful organization. Thank you.
Yeah, I'll get it. That's great. I didn't actually even know that existed. This is great. What was it? Crossed wires, no more than 3, right? This is great.
So, right here on the. So I noticed you briefly talked about block diagram schematics.
Yeah.
But you also use a lot of global labels everywhere. So where do you draw the line between hierarchical and global?
Oh, I don't draw the line. I see them as equal. And we use hierarchical labels when we're doing it in a hierarchical sheet to make that block diagram. That's relatively new for us. We don't usually do that. That was one of the very first designs where I pushed the poor undergraduates to do that. And it worked out really well, I thought. I don't actually care. In fact, if it were up to me, the hierarchical labels and the global labels would be almost indistinguishable because it doesn't really matter. They're still all connected. I know that they have different properties because you can wire up the hierarchical labels differently than the global labels. But as a schematic reader, I don't care, I think is the right way.
I think I'm next. Are you familiar with the post on the Stack Overflow EE forum titled Rules and Guidelines for Drawing Good Schematics? It's by a relatively high poster named Olin Lanthrop.
Huh. Sorry, it's a Stack Overflow?
Yeah, it's on the EE section of Stack Overflow. It's Rules and Guidelines for Drawing Good Schematics. And I like it because it mostly agrees with me.
That's great. No, I've done lots of searches, and I have no idea how I did not hit this. So yeah, that's great.
Okay, just a quick question for when you like import symbols, either from whatever library you're using or from whatever website you might be using, to reflect an easier to read symbol while still, like, I guess, being true to the component package. Do you tend to go in and edit the library symbol and then hide all the excess pins and then, but still make them, I guess, connected? So like, I know sometimes I'll make them all the same pin number, even though they're representative of multiple pins on the package, but they're just one on the symbol. What do you usually do to kind of make it look nicer?
It depends. I think that Jason said it best, which is that if you're doing something safety critical, then it's really good to actually display all those things. If you're doing something like us, for the love of God, hide it. And then just keep poking the up button on the feature request for the Dan KiCad guys who have not implemented that yet, Dan KiCad guys.
It's coming.
I bet.
Hey, okay, so I go back and forth all the time with do I make this microprocessor look like the package or do I make it kind of grouped, right?
Yeah.
And the reason I go back and forth is because I want things to be really easy to troubleshoot on the bench. And, you know, if you have that visual representation of the package, then it's a little bit easier to troubleshoot. So like and I do go back and forth depending upon what I'm doing. It's you know, kind of sporadic like that. But what do you think about that?
This is great. This is great. I have like 100,000 KiCad things open. Let me see.
So while I was looking, what I do for that is I take a screen grab of the pinout from the data sheet and post it in as an image next to the microprocessor.
So here's why I think that doesn't matter. And I think that you're actually shooting yourself in the foot. And the reason why this is not a good example, hold on, I know I have one in here that's RCS. Okay, all right, fine. I'm okay with that. Oh God, now I have to go back to where I was. Nope.
Especially on quad packages too, it's hard.
Yeah. God, now you got me all screwed up. Okay, screw you. I'm gonna do this. Okay, so here's why. When you're doing the schematic, what matters is the actual. Does anybody else hear that siren, by the way?
Yeah, it's another building over.
Okay. When you attach them, you only care about the actual functionality of the schematic. You care that this pin goes to this transistor, right? And in KiCad, when we're debugging a system, I'm going to do this. I'm going to hit tilde, right? And then I'm going to Alt-Tab over to here, and it's going to show me where that circuit is. And so I don't actually care. Right? This is not useful to me because my actual layout is going to be much different than that. And what I care about here is the electrical rules and the electrical connections. And so I encourage you to not do that. And what you'll start to find is you start to use the layout to probe the layout. And you use the schematic just to understand what's going on electrically. And then it doesn't matter anymore. Like, it's just so easy to go back and forth. This actually doesn't help you. It may help you debug when something goes wrong, but it's much more likely for you to screw up a connection when you're doing that package thing. And so we're trying to get the best of both worlds. understanding the connections in the schematic versus the layout and the flow on the board. I hope that was helpful. Yeah.
Yeah, so I'll add a few things that I like to do. I think one is, it's funny that this is coming up for the second time today, harness your inner Ben Franklin, everything in moderation, including your moderation, right? So you want to like rigidly follow rules until it just utterly doesn't make any sense.
Right.
And so to that extent, when I think of these things, when I write code, I leave books in there to explain what's going on. When I make my schematics, I leave all kinds of comments all over there, and I'm not doing it for someone else. I'm doing it because I will look at it at some point in the distant future and not remember any of it. Last week, I looked at some code that I wrote a year ago, and I've had the same response that I've had when looking at other people's stuff, where I went, oh my God, what crap, right? And immediately found 3 bugs and removed about 100 lines of code by rewriting it. And so to that extent, when I drop down resistors and capacitors, I don't just say, oh, it's 10K. I say it's 10K, it's 5%, it's got this much power before it's going to go up in smoke, and this is its package, which is super important when you got your scope in your hand, your scope probe in your hand, and you're looking at your circuit board. Am I looking for an 0201? Am I looking for an 0402? Now, again, my Ben Franklin, I don't really necessarily do that on a microprocessor, right? I know exactly where I'm going to find that one. But for discretes, inductors, capacitors, diodes, I do 11 by 17, and then if I print it out, it comes out on 8.5 by 11, whatever.
Yeah.
But at some point, you're sitting there and you want to find these parts right away. And the more you put down on there, the more you're going to know why you picked it to start with 2 years ago when you made that board, And so, I've certainly caught myself putting down a power level for a resistor and then putting the package on and realizing that package can't possibly dissipate that much power. And you catch it immediately. So that's my 2 cents.
I can't believe I did not put a note about putting standard parts on every sheet, right? That I missed that, and I'm really glad you said something, because you should absolutely have this, right? So that you know what, if you don't make a note, you know what you're dealing with.
Oh, I just wanted to add there are some. Oh, okay. Some exceptions. The feedback pin on a switcher, I've never seen anyone's symbol put it on the left, even though it is technically an input. It's always on the right in every data sheet.
But that's okay. That's right. That's absolutely okay. That's like, so when we say inputs on the left, outputs on the right, that's still technically part of the output circuit, right? Because it is the feedback from the output to the switcher.
I've done it both ways.
It is. And so, again, in moderation, right? Like the flow of that circuit is inputs on the left with all the enables and slow start and all that stuff over here, and then all the output crap and stages on the right, right? So yeah, I don't think that's wrong. Yeah.
One other thing I like to do is sense wires, have them at 45 degrees at the point of contact at where they actually sense the voltage. Makes it look kind of like a
sense wire.
Yeah.
That's good.
Can we go back and look at your Tektronix 422 schematic for a minute?
Yes, we can.
Okay, 0 volts and ground are not the same net.
We have a earth ground there, earth ground there. I don't see another ground. Do you see another ground?
No, but you were commenting, I think, about the 0 volts coming in on the left, right?
It's probably a star ground on the power supply side.
That's not ground.
One of them's down, one in the middle. One of them's chassis.
Ha!
So this
That's
is
good.
quite
Okay. Thank you. Yeah. Okay.
It's quite common in old schematics, and I'm troubleshooting an old Tektronix optical intensity meter right now, and I measure different biases to different grounds in the system.
So if that's not ground at 0 volts, that's just a 0 volt line.
It's a circuit ground, circuit reference 0, back to the power supply.
Which is different from ground. How?
It could be different from the chassis ground.
Well, of course. Yes. Yeah. That's fine.
But it's not ground.
So you and I disagree on ground. Because I say ground. Right. Well, there's the ground reference for the power supply, then there's the ground reference for my circuit. That's the ground reference for my circuit. So I claim I could take that, and then I could have the ground reference for that, which would be GND or not power supply ground, right? So yeah, I might disagree with you slightly, but that's a beautiful disagreement, not a terrible disagreement.
No, but I agree with you that they drew a lot better schematics.
Yeah.
Okay. Well, one last question here.
Yep.
Just a couple more suggestions, I guess. Art of Electronics has an appendix on drawing good schematics that's pretty in line with what you've said. You could
really?
add that as another reference. I'm bringing this one up because you didn't do it in your schematics, and I think you should.
Yep. Good.
Symbols should have a colored background. They shouldn't be a transparent background.
Yes, they should. What?
You pulled up at least 2 schematics.
Okay, but they were undergraduate schematics.
Yeah.
They were okay. All of my schematics have yellow blocks in them. Yeah, no, that's great. I love that. Great, thank you guys.
Okay, thank you very much. I saw that there were a couple more suggestions. Please go to the QR code that was shown earlier. We'll show it one more time here. And drop some suggestions in. And thank you again, Andrew. Excellent. Okay, our final session for today is the developer roundtable. So I'm going to kind of shoo the various KiCad developers and documentarians and anyone else that we have here up to the front. And let me pass the microphone over to Karcher.
Excellent. All right, we'll get started here. Thanks, Andrew. Let me get that YouTube up on my laptop. Good point. All right, one moment. All right, all of them are on. We're ready to go. All right, so I think we have to limit this to 2 hours, right? That's the plan. How much time do we have, Seth?
I'm not leaving until Sunday, so I got some time.
Okay, good. We all got time. Excellent, excellent. All right. So I think a good start, maybe we want to just introduce ourselves here.
I'm Mark Roshko. I've been working on the KiCad project for probably over 10 years now. It's been a while. I handle pretty much everything related to Windows. I added the CLI system, the job sets. I've been doing other miscellaneous things, and I just kind of been all over the place in terms of what I work on. But yeah,
3D models.
Yeah. Oh, I also did the websites 10 years ago, and like everything you see was actually created a long time ago, and all those kind of things.
Right. Yeah. So we said this earlier, but if anyone is interested in a web design job, we have a website from 2012 that would do. We're happy to pay you to upgrade the website.
Hey, I was going to work on that one day.
I've heard that for a few things.
All right, we have to keep the intros moving.
Right. So my name is Seth, and I work on a number of things in KiCad. I also try to organize various community events and bring people together to discuss and develop and improve KiCad.
My name is Wayne Stamball. I'm the lead developer for the project. I've been in that role since 2011, and I've been with the project since 2007, so I've been around for a while. And my fingers are all over a little bit of everything in KiCad. Primarily, I do a lot of the under-the-hood stuff. So like all that crazy instance data stuff that happens in the symbols, you can blame that on me. But yeah, the original file, a lot of the file format stuff is me. Love it or hate it.
It's me. The coding standards, I wrote that. So for those of you who are familiar with when you contribute to KiCad, you have to follow our coding standards. You can also blame that on me too. Yeah, I've been at it for a while. So yeah, my fingers on a lot of bits and pieces of KiCad.
I'm Graham. I do things kind of here and there for the project, but mostly I write user documentation. So I maintain the user manual and the getting started guide. I've been doing that since I think right before version 6 came out. So a few years now.
All right, thank you. Maybe a good first question too for the group is, Wayne, you were about to share a little bit about some schematic block primer, right? Would you like to maybe condense that down into 30 seconds?
Yeah, I'll try to. It's hard to, without the visuals. It's gonna be a little tricky. But the short story is the whole design block thing is basically being able to capture little circuit snippets and put them in a library with a little bit of metadata so that you can, give them a description and a fancy name. It's pretty straightforward. If you're familiar with working with symbols and footprint libraries, then you'll be familiar with working with design block libraries. They're pretty much this. When you create a new library, you're going to see the same dialogue you get. So that's going to look pretty familiar. Right now, there's a couple of caveats. You can't have a sheet inside of a design block because that references another schematic. If you click a sheet and say save it to design block, it will save the contents of the sheet, right? So whatever in that sheet will become the design block. Now, the nice thing you can do is when you copy that block, you can either copy it as the circuit or you can make the whole block a separate sheet when you're bringing them back to your schematic. Yeah, that's probably like the 10,000 foot view. There's some of the editing, the library management tools, since it's a fairly new feature, the library management tools are crude. Like right now, basically you can delete. If you want to move stuff or copy stuff, it's a file. You got to open up your, whatever the file manager is on your operating system and move stuff around. And the one thing I haven't actually found this out because I didn't write this piece of software, but I found out that it's not folder change aware. So if you make changes to the folder and you have the schematic editor open, the libraries won't update. So you'll have to shut it down, reopen it to get the libraries to update to any changes you made on the file system. So that's the 10,000 foot view. And I can tell you that the management tools will be fleshed out over time. There's also the PCB part of that. The PCB design blocks is already in the development branch. Right now it's hidden behind an advanced config, so you got to turn it on with setting a flag in a file. For those of you who don't know, we tend to hide things that aren't as done as we'd like them to be behind advanced config. But if you're really, really interested in using that, we can give you the incantation to turn it on so you can use it. So
you can parameterize them too. So the other feature that you missed, I think. When you add a schematic design block, you can parameterize different values and stuff.
Yeah, and you can link them. You can link so with the new design, I left that out. But yeah, in the schematic editor, you can link it to a board design block, and those two will go together. So when you put the schematic part in your circuit, the design block will end up in your board, and then obviously it'll tie into the multi-channel tool. I don't know if that's done yet, though. Is that done yet? No. Yeah, I don't think so. But the goal is hopefully before 10, that you'll be able to now use sheets, and now you'll be able to like one block, and everyone will be identical with the multi-channel tool. And then so if you make edits using the multi-channel tool, you'll be able to just repeat those over the other blocks. So.
It may not be readily apparent from the description, but there are a number of software developers in here. The equivalent is we are building a standard library. Yeah. Right? We're building the ability to build a standard library. We're putting that tooling in place in order to allow the community or yourselves to build a library of verified best practices that can be then utilized. And as we abstract out these data into higher level ideas, we make that entry into circuit design faster and easier for students, and and we can implement Andrew's suggestions for appropriate schematic layout. So these tools end up becoming like your C++ standard libraries or your Python standard libraries that allow you don't have to be able to implement a sort routine or a quick sort routine by hand anymore. You just say standard sort, because 9 times out of 10 that's what you want. And maybe there's a time when you want something different, but if you're just doing a proof of concept, you're doing your MVP, being able to toss a verified or a best practices block in there and move on to the interesting problem you're trying to solve gets people into circuit design faster and hooks people, allows them to build their competency and build their ideas in a more robust fashion. So this is all about building out that community and that practice.
Before we get to the more interesting questions, which are yours, and I am monitoring the chat online, so if you do post a question there, I'll take a look. Maybe we could just start with Graham, and if you could just share maybe the most interesting or surprising thing from this conference. If you could share a little bit on that, and you can't pass from Graham.
Maybe this isn't surprising so much, but I do kind of pay attention to tools in the industry, but a lot of people are pretty fed up with Altium, which is it's interesting to see, I think.
Wayne, what do you got?
Oh yeah, I mean, it's I always enjoy coming to listen to these talks. The Altium thing doesn't surprise me because I hear from people all the time about it, so it reminds me a lot of the Autodesk thing with Eagle. I enjoyed some of the talks. I know Mike's talk, the LT Spice guy. He's been around for a long time, and interesting information. Somebody who's got a depth of knowledge in a very kind of arcane subject. Simulation is pretty heady stuff. For those of you who've spent any real time doing it significantly, it can be a lifetime study just doing that. So I found that really interesting because there's a guy that's been there since like almost the very beginning of simulation. It's been around. It's pretty impressive to see somebody with that kind of depth. I was just overhearing him a conversation, and he was writing down how to do looked like it was something to do with switch mode power supplies, just a simulation on a napkin off the top of his head. I mean, that kind of like depth, I would have to go look up. How you do that again? He just was like off the top of his head. Yeah, that's how you do that. You don't see that too much in this industry. I've been around for a while. That's a rare thing to see. So that was fun. And always, I love these things just because I get to hear everybody's comments and opinions, and people always come up and say, I have far more positive input when I come to these things. I get relatively little, comments, negative comments. It's almost always positive, and I think seems to be universally true. So I enjoy this.
Thank you. Yeah, keep going around to finish.
Right. Most surprising. Boy,
there are a few of them.
Organizing these things, I learned that Pepsidace is a hell of a drug. So, no. In all seriousness, I am continually impressed by the depth and breadth of knowledge in our community and the willingness of all of you to share with the wider audience your experience and your knowledge, and it just really gives me hope for the future of electronic design, for the future of KiCad, that we are on the right path, and that this ideal of open development and open collaboration is the way to go, is the future. And so I appreciate you all being a part of that.
Well, for me, it's really beginning with the fact that we became an Altium support group, but not customer support. But it was great to see the experiences and point of views people have from the Altium perspective, migrating professionally, but also in general, people are very eccentric about their topics. They talk a lot. We go over time just because everyone's great, and in general, like people who show up at these events, you guys are awesome. You guys care about the trade, be it hobbyist or professional, and it's fun stuff to see and learn, and even to talk to you personally, one-on-one.
Oh, I'd like to go back. I did have one real surprise, that I wasn't the only redneck engineer from Pennsylvania. I don't think that's happened in all my conferences yet that I've been to. So that was kind of a nice surprise for me.
Critical mass. Yeah, I'm not on this panel, but I've very much enjoyed the questions, right? And I'd like to be walking the mic around here. Tassine's here too, and we'll be able to walk the mic around. If you have any questions for the panel, maybe grab that one just in case. If you have any questions, if maybe you're from Pennsylvania and you want to share a little bit. Or
Yeah, this is more of a technical question, but it's something Ben brought up. He had a question yesterday, and I ran into this, and I think it's just kind of a weight game, but like on Windows, you can't really get that cool dark mode because of WX widgets. And is there like a timeline? It's not probably under your control, but I was curious. When are we not second-class citizens?
Well, it's funny you should mention that. That is actually kind of under our... So how we went to the developer of WX Widgets, which is our framework, and we asked him, we said, how much would it cost for you to put dark mode on Windows? And he said, right? And so we gave him a couple examples. Like Notepad++ does it, and a couple other open source examples. And he looked at me, he said, this is the most hacky, underhanded, like Microsoft doesn't support this at all. It really only exists. But if you really want it, I'll do it. And so he came back, gave us, said, here's how many hours it'll take. And we paid him for that. And he put it into WX. It's not in 3.2, which is the stable release right now, but 3.3 should be released any day now.
Yeah. And once 3.3, well, he already tagged the release candidate
RC1, yeah.
RC1 of 3.3, and I'm waiting for the final tag, at which point I will move the Windows nightly builds to WX 3.3, and you'll just get the dark mode with that, which does work, because I previously tested this months ago when the WX Widgets developer put it in. I gave him some feedback, and you'll have that to enjoy.
Thank you.
Excellent. If you have any more complaints too that you want to hear that are magically fixed already, that's great. All right. Take that.
You mentioned, Wayne, the design blocks, and I was just curious if any of you guys have thought about ways to make it easier for people that are just, like you mentioned, being able to go to a library and drag and drop like a pre-built schematic block. And I know we have some things like ERC which can do checks on that, but I was curious if you thought more about like more robust checking, where somebody who's coming in, maybe new to electronics, tries to hook up, a power supply to one of these predefined blocks. Are there ways to do more advanced checking on the like electrical side to see, am I doing something stupid? Like how do I check this more thoroughly? And are there things that you can add into design blocks to like make that process happen, I guess?
Yeah, I suppose, as Seth said, that we would like to, over time, have people contribute robust, already qualified blocks. So hopefully that wouldn't be necessary in the design block system. Yes, obviously you'd probably want to do that before you created a block out of that subcircuit. Hopefully that would be done ahead of time. I suppose, but the problem is with subcircuits, they tend to not to be connected to anything else. So you're just going to generate a bunch of ERC errors over the things that aren't connected. I mean, I suppose we could do some basic ERC checking inside the design block for what's connected to something, but everything else would be, we don't know because it's not connected to anything. I can't give you any input-output error checks or anything like that. You know, if you accidentally you had two outputs you took a design block that had an output and you tied it to an output on your circuit, obviously that's not a good idea, having two outputs driving against each other. So you would not know there was an error until you used it in your circuit. So,
quickie hack hat on. Could you put a global label on all the outputs where there was like supply, just as a standard to show people roughly what was expected? That might maybe help as a quick fix.
Yeah. So just a quick heads up on that. If you go into the design blocks, it's just a folder. And there's going to be two files in there. One's going to be a JSON file, which is obviously your metadata, your properties, and any of the optional stuff. There's a dialog. You don't need to populate that manually. But you also notice that there's a KiCad _SCH file. Well, guess what? It's just a schematic file. You could open it up in the schematic editor and edit it to your heart's content, right? You could add notes. You know, any of the things that you can add in the schematic editor, you can add to a design block, right? Now, I'm sorry, you're not in a microphone, so yeah, there you go.
Sorry, I just wanted to contribute to the previous question, which was asked regarding like how that could be made easier in the future. I know you guys have got so much on your plates, but it was just a suggestion from my programmer hat on. Is it possible to just have a default of throwing a global net in there for things that might be like a power net or something, and then that way it would be very easy for people that had no background to recognize, okay, that's fundamentally incompatible, don't plug it in?
This sounds like a standardization issue. So just as you have different libraries that have different levels of hand-holding that will check, that we wouldn't want to require something like that, but we certainly want to support the ability to create it. And so once you create it and you document it, right, with a standards document of how your library of schematic design blocks is created and what a user of your library should expect, then that becomes a de facto standard that the users of your schematic library will then be able to rely upon. But KiCad, from KiCad's perspective, we want to be able to support that use case, and we don't want to require that not you does that as well.
Yeah, it's a bit like this. It's a bit like the symbol. Do I draw a symbol that looks like the footprint, or do I draw a symbol that looks functional? You know, functionally blocked. We're not going to tell you how to, lay out your design blocks. That's completely
even though there's a right way to do it.
Yeah, that's a completely you decision, right? So yeah, I'm not KiCad in general, and I'll say this now because a lot of people I'm not a one true way guy. I've never been. If I set 10 engineers down and tell them, hey, design this, I guarantee I'm going to get 10 different workflows. And so I'd rather not pin somebody down to a predefined workflow, and then everybody else who has a different workflow gets frustrated or upset by it. So in that regard, yeah, you're free to define your design blocks any way you want, right? That's going to be limited to whatever you can add into a schematic. You're going to be able to put all those things in a block. So if that's the way you want to define your blocks, that's great. If somebody else just wants that open-ended stuff and I just want to plug this into my whatever I'm working on now, but they've already have it fully qualified, then they may not care about that.
On a tangent, with the internationalization, very good progress. It's amazing to see how many languages are done. With the intent to include schematic blocks and have a library, does that mean, given that we've just been told very heavily to include appropriate documentation in text format, that will be moved into the translation scope?
I think we also should be clear that I don't think at present there's any plan for a KiCad organized design block library.
Yeah, I think that's accurate. That isn't to say that we can't generate it in the future. Our librarian team right now, they're fantastic and they're making awesome progress, and they have a backlog a mile long because there are a lot of contributions there. If a new person / team were to stand up and say, this is something that I feel passionate about and want to maintain, and we see that being maintained over time, we'll say, hey, would you like to, if this is useful to the community, would you like to maintain this with us? Would you like to coordinate more closely with us? And we did that with the 3D models library, for instance. It was maintained by an amazing contributor named Maurice for years, and he took it on from a previous contributor, and they kind of maintained it separate from the project for years and years, and eventually it just became so important to us that we said, let's work together. Come in as part of the overall library team, so that we can coordinate and make sure that features match with what is being what work you're doing. And so I could see that kind of process going on, but like I said, that was years that the 3D models were maintained externally. Maybe a little bit shorter if there were commitment and interest, but it's not something we're going to bootstrap.
To the actual question, though, of documentation and internationalizing documentation, I think that would be challenging with the current system, getting that into WebLate.
Yeah, I don't think that WebLate is an open source project. Maybe we could pay them to support KiCad things if that were a desired outcome. I think the easier way to go about that would be just to, if there's a need to maintain a library in English and a separate library in Russian or Chinese or whatever translated language, because your local engineers speak that language, and all of the comments that are in the diagrams are useful for that, then I think you just maintain a separate fork or a separate repository that mirrors the original repository, pulls updates, but then applies the translated comments. So I think you'd just maintain it as separate fork.
Yeah, I mean, this isn't exactly the same, but for example, the symbol libraries have a lot of metadata attached to them, and that's all in English. We don't translate that.
Right, and there are symbol libraries maintained in Chinese, and localized Chinese libraries will exist, which is probably easier and a more sustainable workflow than trying to apply a translation, because our translation engine is I-18, and that does not actually apply. We'd have to write a translation engine for KiCad symbols, which sounds like maybe out of scope. I think people might want a KiCad feature first.
I will add also, it's just going to be kind of boring for someone to want to actually translate all the symbol metadata, because there's just so much, and it's kind of, it's like, transformer, comma, push-pull, comma, and, some other things like that. And it's just repeated over and over across symbols in different forms, and someone would have to go through every single one of them. And it's already hard enough to get people to want to translate what we have, and it's great because we have some great translators. but they would probably really not stick around if they wanted to start doing that.
This sounds like an excellent application for AI.
Actually,
finally.
Do the work none of us want to do.
Right. I'm going to quickly squeeze in an online chat question here. One thing that I was missing when introducing KiCad to friends and colleagues is the missing tutorial inside the application. I was thinking about a limited visual tutorial. Is this feasible? Anyone who wants to?
So we've discussed related things. These we had a number of years ago. We had a discussion about rich tooltips. This is kind of the same sort of thing where you right now we have textual tooltips, but rich tooltips could display like an animation of exactly what this tool does. And that sort of framework of overlay and showing tool action is kind of, I think what they're referring to is like a getting started where you dim the screen and focus the attention over here and say click over here. Okay, now click over here. Notice what we did, sort of thing. So we've discussed it. It's possible. The requirement there, it turned out that the work level requirement was relatively high, and it was slightly adjacent to our defined mission. So those of you who don't know, you can look at the KiCad website. We have a defined mission. KiCad is first and foremost meant to be a tool for professional circuit designers and engineers. So that is when we have extra time and when we have extra capital, that's where we focus our time and our efforts on the tools that professional engineers need to get their jobs done. Now, this is more of a let's bring new people, fresh faces in, which is also important and like I was saying, adjacent to primary KiCad mission. So it's something that we could take on if there were, say, an educational institution or foundation that saw a high value in that and wanted to contribute manpower or funding to develop that sort of introduction. That's something we could definitely take on, but it's sufficiently intensive, sufficiently work intensive that the actual implementation would need to have secondary funding outside of the normal donation path.
I just wanted to encourage you in an area that I've worked in defense, that you always try to make it easy for the product to be configured so that the libraries are not used, so that the customer would always only be able to be assured of relying on their own libraries. For example, a defense application being developed in a secure area, something like that, they're going to insist that it only be used with library symbols, maybe even footprints that they have approved themselves for that purpose. And so if they were to get an update of the product or whatever, some normal use of the product, and suddenly it would change that configuration or assume that it should go to the default installation libraries or something, in that environment, that would be quite catastrophic.
Well, initially, we have to configure something. There is on initial, if you're doing a clean install, in other words, there's no config file for that current version, you get a message. Use the default library table. If you have a specific library table that your corporation uses or your institution uses, you can, if you go down and say, use a custom one, and then you point to the custom library table, it will not install the default. That's just the default. That's all that it is. It's not what you have to use. And even on, like I said, on startup, you're free to pick your own footprint and symbol library tables. You don't have to use KiCads. That's just what we default. That's what we point to. After that, we don't even, like I said, even in the very first time, you can just say, nope, I can't use that. Here's mine. So, yeah, that's already available. Now, sometimes I know you people will not read that dialogue that pops up, but if you do that and hit OK.
You people?
Yeah, obviously, you're gonna get the KiCad defaults. I mean, that's what we install by default. We have to default to something. Otherwise, if we left everything empty, everybody be going, no symbols, no footprints. So you just have to be cognizant that when that pops up, and you'll get that every new version. So when you upgrade from 8 to 9, it'll say, do you want to pull from your previous version's configuration? If you do, you're going to get whatever, like say when you go from 8 to 9, you're going to get your 8 configuration in 9, and then the defaults for whatever are in 9 that's not in 8. But so if you already have your version 8 library tables pointing to your own symbols and footprints, you say yes there, you'll just be using those in 9.
One thing that I think we could do better on, and I think we've talked about this before, is getting back to that dialogue after you've configured KiCad. You can do it by blowing away your configuration manually, but I don't think there's currently a button to get back to it.
Button.
Is there a button now?
There is a button.
There was.
Okay, all right.
It might only be in nightlies, but there is a button that says reset tables.
Okay.
So that'll pop that dialogue up and let you blow it away a second time.
I've also had a plan for a central first run startup dialog, which had some back-end code that still needs to be adjusted to make it work. But, because right now, if you open the schematic under the first time, you'll get the prompt for the schematic tables. And maybe, a few weeks later, when you finally do your PCB layout, it'll then ask you about the PCB tables. And it's kind of, separated, and you can kind of mess up there. So my plan is eventually you'll just get one dialog that asks you all the various first run startup questions. What do you want to do for your library tables, both schematic and PCB? Do you want to subscribe to update notifications? Do you want to do the update? Whatever other features we have, actually, I don't remember.
Bug reporting or whatever.
Yeah, bug reporting, the Sentry crash monitoring. Yeah, but that's a to-do item.
I'm going to squeeze in one more online question here. Is there an API yet to manipulate schematics and these design blocks, or will I have to actually write it?
No.
Oh, wait. I heard that they're going to write the API for
Okay, let me write that to them real quick.
Are you volunteering? Yes.
So unfortunately, John Evans, who is our API guru, is not here to answer this. So John, please correct me if I get this wrong. But right now, we have one major technical blocker to getting that API exposed for schematics, and it is down to this difference between footprints, which are exactly the same in the board and the library, and symbols, which are not, because symbols in the library have all of the units, and symbols in the schematic have some of the units. And so we have these two different elements, and working with those two, or managing the transition between those two, is sufficiently technically problematic that we need to solve this in order to facilitate that API, because one of the design requirements that we set for ourselves with the API is that it has to be stable. We will not take away API functionality or change existing API functionality without a defined deprecation timeline of multiple revisions and a path forward. So this requirement is born out of the pain that some plugin developers currently feel when upgrading versions, and certain functionality modifies itself due to how we are using Swig to expose the internals. So we don't want to implement one thing and then get around to fixing that underlying issue, and then suddenly our API no longer matches the fundamental symbols, the actual data that symbols in the library versus symbols in the schematic represent. So that work's in progress. It is, if there is magical YouTube commenter who is interested in working on this, please do get in touch with the team. We are very interested in having that sort of contribution working with us toward that goal. We'd love to get that exposed for V10.
Excellent. So last question here. This would be for each of you, maybe starting on my side here, is what do you look forward to most in the next year to come with KiCad in our community?
I'm actually not sure, because I got a bunch of things I'm working on. You'll get 3D PDFs soon, so you could export 3D PDF files just like the competing CAD software who shall not be named.
That works.
We have a number of projects in progress at KiCad Services right now for various customers that will be implemented in V10, and these are going to be, I think, extremely valuable to people. We have a graphical editor for the design rules, so you won't have to type them out anymore if you don't want to, or at least for a large number of them, you can design them graphically. We have flat schematics coming. We have we're working on a number of functional upgrades to net listing, and we have an additional project for well, I'll let Wayne go on to his additional project. I have an idea of what Wayne's going to say, so I'm going to let him go on.
Well, part of my KiCad Services work is variance, but before variance happens, I have to fix the way we save instance data. If anybody knows how that works, you probably know more than I do, because it's very arcane and very complicated, which is going to be a pretty big file format change in the way we handle it. And that has to be done before we do variance, because variance will be instance specific. Because if you reuse a sheet, you're going to have to be able to assign variant information to each instance. So it does complicate things a bit, but to be honest, I've been trying to find time to do the file format changes for a long time now, and because it needs to be done. It'll clean things up a lot. It'll probably be a little bumpy at first, but so that'll keep me busy. And then there's hopefully on a side burner, there's another KSC project coming along that, did we get approval for the snapping, or is that still in progress? The schematic snap, didn't you say we were doing schematic snapping, or was that something different? So there's been a request. You know how how we have the cursor snapping in the board editor? Somebody wants that kind of snapping in the schematic editor.
If you're watching and that is your job, I definitely remember it, and we're working on it.
Yeah. And of course, there's a lot of smaller projects that I want to get done for 10. The pin list was one of them. Instead of, right now we have an ugly hack where you got to stack a bunch of pins on top of each other to have a single connection for an FPGA with 45 power or ground pins, right? That's a pain. So pin list is just a matter of being able to define a range or a comma separated list of pin numbers. You got one pin, and then it just fans those out to the footprint. So that's on my list. And of course, I love going to KiCons. I look forward to those. It's kind of what I'm always up for even though travel's kind of a pain, I just love coming to these things.
When's the next one? We're going to pitch.
The next one, Next KiCon is in Bochum, Germany. It is coming up on September 11th through or 10th
10th through the 12th.
September 10th through the 12th in Bochum, Germany. Bochum, for those of you who are not aware, is an easy ride from Frankfurt Airport. It is right on the ICE line. Or if you take a hop over to Stuttgart Airport, it's even closer. But for those of you like me who like riding trains, you should definitely fly into Frankfurt and take the train. Stops right in Bochum, and it is such an amazing town. The day before the conference, we do a beer walk. So where we have a local tour guide who walks us around the town and in true German fashion shows us all the places where they make beer. And then we obviously taste the beer.
We don't just walk around and look at the places where they make beer.
So no, it's a really good time. We do work very hard during the KiCons to ensure that both the content is nurturing to your mind and the food and beverages are nurturing to your body. So we want to entertain the whole of your person. So please, if you have a chance and you're at all interested, come out to the one in Germany, or alternatively, if you prefer, the KiCon in Shenzhen is also absolutely amazing. I think that one is November 17th. It is the third week in November, Wednesday, Thursday, Friday. All of this is on KiCon.KiCad.org, and we'd love to see you there. These are two very different events. You will see it is very different from KiCon US, and they're both very different from each other. We are a highly localized organization. There are people on the KiCad team that we only get to see in KiCon Asia, and there are people on the KiCad team that we only get to see in KiCon Europe. And in each of these areas, we see how people are building circuits, and it's not like you're doing it here. It is, and just
the ground goes up, right?
That's right. The ground. That's only in Australia. So
I want to make sure Graham has a chance to finish the question too, and then
I'm going to go back to V10 features.
There we are.
There's a lot of DRC stuff that I'm pretty excited about. The visual editor that Seth talked about. Length tuning is unified, which is a long time coming. So that's really great. And then there's some automatic component classes that I'm pretty excited about. And then one little thing is that symbols can be jumpers now. So if you have a push button with 2-pin 1s and 2-pin 2s, you can mark the symbol so that they're connected internally in the symbol, and DRC won't complain at you anymore, which is great.
Beautiful.
So for everything that this panel does, can we give them a big round of applause?
Thank you.
And I know, Seth, you had some things you wanted to share too.
Sure. So I need to give a big thanks to the team here at Qualcomm Institute. I've heard from multiple people how wonderful the acoustics are. That is all down to a team of people who are literally up there in the booth watching this whole thing. They're not even electronics engineers. They're up there for the entire conference. This isn't magic, right? This is human intervention, making sure that these microphones aren't squealing, making sure that you're hearing everyone speaking. The lights are, I'm not sure if you notice this, lights come up, the lights go down, the cameras are switching around. Really, really top-notch folks. And so thank you very much to Qualcomm Institute and UCSD and Karcher.
Yes. And I just want to say thank you to everybody out there who, I know you're all KiCad users, and it's pretty humbling to look all the way back from where we started to where we are now. It's really fantastic, and it's because of you. I mean, without a user base, we'd be nowhere. So I think it's a tribute to people who help give feedback and continue to encourage the use, evangelize, spread the, I always hear people, I got this person to use it, or I got this guy to use it who was a long time hardcore this user. And so yeah, keep up the great work, everybody. I really appreciate it.
So one real quick before one more thing, I am going to send out a survey to everyone who registered for the conference, and I would really love feedback. We want to make this is going to happen next year, and I want next year to take all of your feedback to make this an even better event for next year. So I promise I'll make it relatively short. It won't. But fill out the form. Get back to us. And I think Jason, are you back there somewhere? Yeah. So Jason is headed down for tacos afterwards, and down to Old Town. So after action, if you are interested in going around and chatting a little bit more about circuits and KiCad, Jason in the blue shirt is the man to talk to, and he's going to lead the way into Old Town. Sorry for diming you out here, Jason.
I just want to take a minute to let everybody know. So I don't fly out till Sunday, so I had some things that I might want to do tomorrow. But if somebody makes me a better offer, let me know. I'm always willing to sit down and talk all things KiCad. Tonight I don't have anything planned, so maybe I'll go do the taco things. But feel free to join. This is why I come to KiCon, is to meet the people that use KiCad. So take advantage of it while I'm here.
All right. Thank you all very much.
Thank you.